Hello, and welcome to Programming Fundamentals, the first course in an Introduction to Programming in C. I'm Drew Hilton, and I hope you are ready to learn a lot about programming.
And I'm Ann Bracey, and would also like to welcome you to this course and specialization. I'm excited that you have the chance to come learn to program with us.
And I'm Genevieve Lipp. I learned to program in C from Drew and Ann's book that this specialization is based on, and can tell you firsthand that it is a great way to learn. You don't need any prior background in programming, just an eagerness to learn and excitement about thinking through problems.
As Genevieve just mentioned, this specialization is great if you are new to programming. You might be thinking about learning for a wide variety of reasons. Maybe you want to become a professional software developer. If so, this is a great starting point. We're going to build solid fundamentals that will serve you well in both C and any other language.
Or maybe you want programming skills to use in some other discipline. I know a lot of social scientists and natural scientists who have found programming necessary to analyze the data that they have to explore the problems in their field.
Some of you may have already taken an intro course and be looking to expand your skills. This can be a great chance to both build your programming skills from solid fundamentals and to learn a new language.
Another great reason to take this specialization is if you are taking a computer organization class, either on Coursera or in school, and don't have the C programming background to excel. This specialization is a great way to come up to speed on those topics.
So what's special about the way that we are going to teach you? We're going to start from the very beginning. A lot of programming courses assume you can just figure out how to write code from seeing a few examples. We aren't going to do that.
Instead, we're going to teach you a step-by-step approach to solve programming problems. This 7-step approach is a great way to tackle any programming problem, from smaller ones that you will use as practice in this course, to large complicated ones that you will use in real-life situations.
We're also going to teach you how to read code as well as how to write it. After all, how can you write if you can't read? For every piece of syntax that we teach you, we are also going to teach you the semantics, what exactly the code does. For any code you write, you will be able to execute it by hand, saying exactly what every line does.
Which goes hand in hand with the principle of no magic. We're never going to tell you to write or do a thing just because. Instead, we want you to learn that everything in programming is about well-defined rules which you can understand and follow or even execute yourself.
So, where do we go from here? The rest of this course is all about computational thinking. You'll learn a lot of important concepts: how to design an algorithm to solve a problem, how to execute a piece of code by hand, and the everything is a number principle. These will lay the foundation for you to start writing programs in C in Course 2.
Speaking of Course 2, that is where you will learn to use a variety of tools that are important to develop your code. You'll learn things like how to turn your code into an actual program that the computer can run, which is called compiling. You'll also learn about testing and debugging, finding and fixing mistakes in your program.
In Course 3, you will learn about ways to store more complex data using pointers, arrays, and strings. If you don't know what these are now, no problem. We'll explain them when we get there.
And in Course 4, we'll learn how to interact with the user in the system, as well as how to dynamically allocate memory when you don't know in advance how much data you have to work with. So, let's get started. Let us briefly take a look at an example algorithm and how you might follow its steps yourself. We don't need to know anything about programming to do these steps. We just need to be able to do some math and keep careful track of what we are doing. This algorithm does not accomplish a really useful task, but gives us a simple example to start from. The algorithm says, given a non-negative integer n, so it is parameterized over n. We need a value of n to actually do these steps, so let's pick n equals 2. We're also going to want a place to write down the output that the algorithm produces. That is, everything that we are told to write down, we will write in this output box. We need to keep track of where we are, so we are going to use this green arrow to remember what step we are currently on. We'll start at the start. The step right after the arrow says to make a variable called x and set it equal to n plus 2. N is 2, and 2 plus 2 is 4, so we want to note that x is initially 4. Our next step calls for us to count from 0 to n. We will want to give a name to the number we are counting so that we can use it in our other steps. Here, we decided to call it I. As we count, we are going to repeat steps. We've used indentation here to indicate which steps are repeated for each number we count, as well as explicitly noting in the step after that you do it when you finish counting. We start with I being 0, since that is the first number we said to count. Our next step says to write down x times I. 4 times 0 is 0, so we write down 0. Our next step says for us to update the value of x. What is its new value? 4 plus 0 times 2 is 4, so we would update it to be 4. It's already 4, which is fine. We just keep its value as 4. Now we have reached the end of the steps that we said to do as we count. We need to go back and count the next number, so we move our arrow back to the top of the steps we are doing for each number and make I the next number we would count, in this case 1. Now we begin doing these steps again with I having the value 1. What is x times I now? 4 times 1 is 4, so we write down the number 4 in our output. Next, we're going to update x again. This time, x plus I times n evaluates to 6, so we're going to change the value of x from 4 to 6. We've again reached the end of our repeated steps, so we need to count our next number. We go back to the top, and then count our next value, which is 2, and make that the value of I. We said to count from 0 to n, and n is 2. So are we done counting? In these steps, we said to include both n's, so we are going to do these steps when I has the value 2. So we go in and do the repeated steps one more time. Now, x times I has the value 12, so we write down 12 in our output, and we go to the next step. Our next step says to update the value of x again. Evaluating x plus I times n, we get 10 this time, so we update the value of x to be 10, and move past that step. Once more, we've reached the end of the steps we want to repeat as we count, so we return to the step where we said to count. When we return here, we look at our steps and realize that we've already counted all of the numbers we were supposed to, 0, 1, and 2. So we are done counting. Now we want to go to the steps after we finish counting and do them. This one says to write down the value of x. X currently has value 10, so we write that in our output. Now our arrow is at the end of our steps. There's nothing left to do, so we are done. 0, 4, 12, 10 is the sequence of numbers that this algorithm wanted us to generate for n equals 2, which we see in our output box.
In this video, we're going to test the algorithm that we just wrote. We're going to be counting from 0 to n, and n is a variable. We're going to draw boxes for each of our variables to keep track of what value they currently have as we step through our algorithm. As we begin, n has the value 5. The other thing we're going to keep track of is the output of our program. Here is a box labeled output, and every time we write something down, we're going to write it into this output box. Finally, we're going to use a green arrow to keep track of where we are. Right now, the arrow is right before the line that says count from 0 to n, which means we haven't done this yet. Now we can start. The first thing we want to do is count from 0 to n inclusive and call each number that we're counting I. Since I is a variable and it's going to start with the value 0, we create a box to hold I and its value of 0. Now we enter the next step. The next thing we're going to do is write down n squared minus 2 times I. We have a little bit of math to do here. N is the value 5 and I has the value 0. So this gives us 25 minus 0, or 25. And again, we're supposed to write this number down. So we place this number into our output box. Now this process is going to repeat again and again. Now I is going to have the value 1. Once again, we're going to compute n squared minus 2 times I. This is the same as last time, except I has the value of 1. This is 25 minus 2, or 23. We write that to our output box. Now we just completed I equals 0 and I equals 1, and we're trying to get all the way to I equals 5. So now we're working on I with a value of 2. Once again, n squared minus 2 times I, which is 25 minus 4. The value is 21. And we will write this to our output box. Now we're working on I with the value of 3. We're going to write down the number, n squared minus 2 times I, 25 minus 6, which is 19, into our output box. And we're going to keep doing this, for I having the value 4, which is 17, for I equals 5, which is 15. I keeps getting larger each time we step through our algorithm. When I equals 6, however, we're going to stop because we're only counting up to n equals 5. At this point, we've finished the entire algorithm. And the good news is that our answer matches what we were expecting. The sequence of numbers is, in fact, what we were hoping to produce.
In this video, we will develop an algorithm for a particular pattern of blue and red squares on a grid. We're going to start with step 1, doing an instance of the problem, and in this instance, I picked n equals 3. So the first thing I'm going to do is work the problem by hand without really thinking through exactly what I'm doing. That is, I'm going to do it right, but I'm not going to try to write down what I did. Once I've done that, I'm going to do step 2, where I write down exactly what I did in a step-by-step fashion. The first thing I did was put a blue square at 0, 0. Then I put a red square at 0, 1, another red square at 0, 2, a blue square at 0, 3, a red square at 1, 1, blue at 1, 2, red at 1, 3, red at 2, 2, red at 2, 3, and finally a blue at 3, 3. Now I'd like to generalize these steps. Step 3 of the programming process, and if we look at the steps, we can see there's some repetition and counting behavior, which is going to help us generalize these steps into an algorithm. These first 4 steps have x equals 0, then we have a group of 3 steps for x equals 1, a group of 2 steps for x equals 2, and finally a single step for x equals 3. So we're repeating somewhat similar steps as we count x going from 0 to 3. But exactly what we do varies. We color the squares blue, red, red, blue for x equals 0, or red, blue, red for x equals 1, so the color pattern is something we still have to figure out. Also, how many steps and the y-coordinate of each varies. Let's look at the y-coordinates first, coming back to the colors in a minute. If we look at this first group of steps, we see that the y-coordinates go from 0 to 3. If we look at the second group of steps, we see that the y-coordinates go from 1 to 3. And in this third group, 2 to 3. So it looks like, in general, we're counting from x to 3. If we ignore the colors for a moment, we can take this group of steps and say, we count from 0 to 3, calling the number that we count y, then put a square of some color we'll figure out later at 0y. And we can write similar steps for each of these other groups. And now we can use patterns in these steps to generalize our algorithm further. Each set of steps is the same, except for the x-coordinate shown in bold, and these vary in a nice counting pattern. That is, we can say count from 0 to 3, call each number that we count x, and for each of those numbers we'll count from x to 3 and call that y, and we'll put some color square at xy. But this is only true for n equals 3. A clue that we have not finished generalizing is that the steps do not depend on n at all. We know that the pattern will be different for different n, but this is not reflected in the algorithm we wrote. We need to make it more general. How could we do this? We might just realize it, but if we don't, we can go back and repeat steps 1 and 2. If the pattern is hard to figure out, we may have to do steps 1 and 2 many times. So for example, if we went back and performed step 1 for n equals 1, we end up with this pattern. And when we do step 2, we write down these steps. If we go through the generalization process again, we see that we come up with these steps. Count from 0 to 1, call it x, count from x to 1, call it y, then put a square of some color at xy, which is very similar to n equals 3, except this number has changed. For any n, we count from 0 to n based on the pattern from our examples. Now we have a more generalized algorithm. Of course, we need to figure out what the question marks are for the colors. To do that, we can go back to the colors from our n equals 3 example. We had mostly red squares with some blue squares, so we should figure out the pattern for when a square is blue. I've thrown away the red ones, so we can just look at blue for a pattern. This pattern may be a bit subtle to see with only 4 pieces of information. You may have figured it out, but if not, what could you do? Well, it might be easier to see with more information. Looking at n equals 5, we have more blue squares to consider. Now you look at the pattern and see what you come up with, and this is mostly your ability to look at numbers and find patterns. If we add the x and y coordinates together, we see that they are 0, 3, 3, 6, 6, 6, and 9. So the pattern here is we draw a blue square if and only if x plus y is a multiple of 3. Now we can go back to our algorithm and specify if x plus y is a multiple of 3, we put a blue square at xy. Otherwise, we put a red square at xy. This algorithm looks pretty good, but we will want to do step 4 and test it, shown in the next video. In this video, we will test the algorithm for a pattern of blue and red squares on a grid. Remember that testing is going to make us more confident in our algorithm, since generalizing is one of the harder parts of the programming process and is prone to errors, such as leaving something constant that should be a variable. We need a grid to draw on, an arrow to keep track of where in the algorithm we are, and a box to list our variables in. Let's use 2 for our value of n. We make a box for x and start counting at 0. Then we make a box for y and start counting at x's value, which is 0 here. Now we need to decide if x plus y is a multiple of 3. It is, so we go inside the if statement and put a blue square at 0, 0. Now there are no more steps for this iteration of y, so we continue counting with y equals 1. 0 plus 1 is not a multiple of 3, so we enter the otherwise clause and put a red square at 0, 1. There are no more steps for this y, so we'll count the next one. 0 plus 2 is not a multiple of 3, so we'll put a red square at 0, 2. We continue counting and y is 3. But we were only counting from x to n, so we don't do any of these steps. And we continue counting for x, so now x is 1. We're going to count from 1 to n and call that y. 1 plus 1 is not a multiple of 3, so we put a red square at 1, 1. Incrementing y, 1 plus 2 is a multiple of 3, so we put a blue square at 1, 2. We're done counting for y, so next we count our next x. Counting from 2 to 2, 2 plus 2 is not a multiple of 3, so we put a red square. We finished counting for y, so we count for the next x. We're done counting for x since we only want to count to n, which is 2. So we're done with the counting. And we finished executing this algorithm. We are done, and we found the answer we expect. We can say our algorithm at least works for n equals 2. We're a little bit more confident in our algorithm because we've shown it to be correct for at least one value of n. That was not what we used to come up with it. If we wanted to be more confident, we would have to test it more thoroughly. As always, testing can't prove that it's correct. It can only make us more and more confident.
In this video, we're going to step through the process of designing an algorithm in the context of the following problem. Here we have a 16 by 16 grid, and we're interested in drawing a blue rectangle of particular height and width located at a particular starting XY location. So to begin with, we'll just look at a specific instance of this problem. Let's suppose that the starting point should have the x and y coordinates 7, 9. The width of the rectangle should be 8, and the height of the rectangle should be 4. Now, to do an instance of the problem, we're going to look at our starting point and simply draw that rectangle. You can assume that you have some kind of a blue pen, and you're just going to draw this rectangle as the problem specified. Now we need to take a step back and write down what we just did. The first thing that we did was start at point 7, 9 and draw a horizontal line the length of 8. Next, we draw another horizontal line of length 8, starting at 7, 10. A third horizontal line that starts 1 point higher, and finally a fourth horizontal line starting at 7, 12. Let's step away from the drawing and look at the actual lines we've written out, describing what we did. You'll notice that this is a very repetitive process. The only difference in these 4 steps is the y-coordinate. The y-coordinate starts at 9 and stops at 12. The reason that we start at 9 is because that's the starting y-coordinate of our rectangle. The reason we stop at 12 is because we're interested in drawing a rectangle that has height 4. So we're going to draw 4 horizontal lines stopping at y plus height minus 1. Now that we've inspected these 4 steps, let's try to write an algorithm that will generalize them. Recall that we were counting up from y to the value y plus height. Now, this was actually an exclusive y plus height because we counted 9, 10, 11, 12. We did not actually go all the way up to 13, which is y plus height. We're going to call this number I, and then for each of those values, we're going to draw a horizontal line of length 8, starting at the coordinate 7i. Why are we drawing a line of length 8? That's because it's the width of the rectangle. So we can go ahead and call this width. This way, we will be able to use our algorithm for rectangles of different sizes. And why are we starting at the x location 7? Because that's our beginning x coordinate. So we can call that x. This way, our algorithm will accommodate all values of x. Now this part seems a little bit complicated. We're going to draw a horizontal line of length width, starting at xi. It's actually fine for this step to seem a little bit complicated. We'll just call that a different programming problem. We're going to assume that we either already know how to draw a horizontal line of length width, starting at xi, or we can solve this as its own programming problem, beginning with steps 1 through 4 all over again. For this exercise, we're just going to assume we know how to perform this step. The last thing we want to do is add a little bit more precision because we wanted the line to be blue. So our algorithm needs to specifically say that we are drawing a blue line of length width, starting at the location xi. Test this algorithm for yourself. Give yourself a value of x, y, a width, and a height that you want to test out, and see whether this works for you. As a final note, some values of x, y, width, and height will cause you to draw off the grid. In this case, we're going to assume that nothing special happens and that doing nothing in response to this is the desired behavior. Later on, we'll look at ways of handling errors and corner cases in a more sophisticated manner.
In this video, we're going to work the problem of finding the closest point out of a set of points to some other given point. We'll start by doing an instance of this problem by ourselves. To do that, I've begun by drawing a Cartesian coordinate grid and choosing a set S of points, which you can see here, and another point P, which is 1, -1. We're going to find the point in S that is closest to P. The first thing I'm going to do is to draw my points on my Cartesian plane. Now I can begin working through this. First, I need some domain knowledge. I need the mathematical definition of the distance between 2 points, which, if you don't remember, is the difference in the x values squared plus the difference in the y values squared, and then we take the square root of that. So the way that I would do this is calculate the distance between P and 2, 7. And I would come up with 8.06. Then I would compute the distance between P and 10, 5 and come up with 10.82. The first point was closer, so I'm going to keep that. This point is 7.07 away, so I'm going to keep the new closest point so far. This point is 7.81 away, so 8, -2 is still closer. This point is 5.66 away, so we have a new closest point. This point is 9.06 away, so -3, -5 is closer. This point is 9.22 away, so -3, -5 is still closer. And there are no more points to test, so -3, -5 is my answer to which point is closest to 1, -1. If we visually inspect this picture, that seems pretty reasonable. It looks like the closest. Now I write down exactly what I just did. I computed 1 squared plus 8 squared, took the square root, and got about 8.06. I computed the square root of 9 squared plus 6 squared and got 10.82. And I compared 10.82 to 8.06 and said 8.06 is smaller. I computed the square root of 7 squared plus negative 1 squared and got 7.07. And I compared 7.07 to 8.06 and said 7.07 is smaller, so this is a better choice. Then I compared the square root of 6 squared plus negative 5 squared and got 7.81. I compared 7.81 with 7.07 and got that 7.07 was smaller, and so on, and so on, and so on. And then, when I got to the end, I gave my answer as -3, -5. These seem like reasonable steps, but we actually glossed over something that we did in the process of writing these steps down. It is very important that we write our steps down carefully, because if we're missing steps, we're going to miss them when we go to generalize and end up having a problem. Here's an important clue. Look at this step, where we give an answer of -3, -5. When we go to generalize, we're going to ask, why did we use -3, -5? Then we're going to notice we don't see -3, -5 anywhere else. The fact that our answer seemingly comes out of nowhere indicates that we're missing something. We did some step without consciously thinking about it and writing it down, and we need to fix that before we go on. We may notice this now. We may notice it when we go to generalize, in which case we need to come back and fix it. Why was it that we picked -3, -5 as our answer here? Reviewing our last steps, the last remaining dotted line of length 5.66 is what we were keeping track of, our best choice so far. We started at 0.27, then we went around and updated it each time we found a shorter distance. However, as we wrote our steps, we never mentioned the point that went with the shortest distance so far. We should go back and fix our steps to include that. We start with a best choice of 2.7. When we got to 8, -2 and decided 7.07 was smaller, we updated our closest point to 8, -2. When we got to -3, -5 and found that 5.66 was smaller, we updated our best choice to -3, -5. Now, this answer at the end makes sense. It is whatever our best choice was last. Now we're ready to generalize, which we'll do in the next video. In the previous video, we carefully wrote down the steps we followed in working a specific case by hand. In this video, we generalize the steps to finding the closest point. Looking at our steps, some of them are similar, but we need to make them match up. Each of these colored boxes contains similar steps. First a computation, then a comparison. We also have some steps we only do sometimes, and we need to figure out under what conditions we do them. We also have some steps we only do at the start and the end, and we're going to need to generalize the numbers in those. So the first thing let's do is make these similar steps match up. Why are we computing 9 squared plus 6 squared here, 7 squared plus -1 squared next, and so on? If we look at our picture, the 9 comes from delta x and the 6 comes from delta y, the difference between the point 10, 5 in set S and 1, -1, the point P. The same is true for all of these other numbers, the differences in x and y between points S and P. So we might rewrite all of these steps to have the points S1, S2, etc. up to S6. We'll call the first point S0 when we get to the starting step. Programmers often like to start counting from 0. The first substitution gives us S1's x minus P's x, quantity squared, plus S1's y minus P's y, quantity squared, then the square root of the whole thing. Now, the result of this computation won't always be 10.82 or 7.07, so we should give these a name, such as current distance. But when we do this, we're going to have to keep track of each time we use this number and update them too. That is, if we change the first occurrence of 10.82 to current distance, then we need to make this line compare current distance to 8.06. But some of these numbers are used in other ways, so these are going to need a different name. Here, we've replaced the value for each computation with current distance. Notice that the only times we update the best choice are when current distance is smaller. That means we must have been keeping track of the best distance so far, which we now need to update as well. Now, we update the best distance when the current distance is smaller, and we can use the value of best distance for comparison with future computations. Let's look at the first 8.06 we compute, and consider the other places it occurs. The computation can be achieved like the others using S0. Since this is our first computation, it might as well be the best so far. Then we can replace the other instance with best distance, making the steps match. To continue generalizing, let's look at the points for best choice: 2, 7, 8, -2, and -3, -5. Each of these is the particular point we're looking at, so we can replace those with S0, S2, and S4. Recall that we only updated the best choice when the current distance was smaller. We can make each of these steps the same by including instructions to compare current distance and best distance each time, but only update best distance if current distance is smaller. Now we do the same steps for each of the points. Each colored box is the same as the others except for what point we're looking at, S1, S2 through S6. That means we can express this as a repetition where we count from 1 to the number of points in S exclusive. We'll call each number that we count I, and we'll compute the distance from the ith point in S to P. If current distance is smaller than best distance, then we'll update best choice to SI and best distance to current distance. We haven't changed our steps for the start or end, but we should generalize the point we give as our answer. The answer is not always going to be -3, -5. Why did we say that? Well, the answer was the best choice when we finished counting. So in general, we'll give an answer of best choice. The only other thing we need to do is consider a corner case. What if S has 0 points in it? In that case, we give an answer of no answer exists. This corner case was not revealed by the example we just worked, but it would have come up through testing. Working an example with 0 points, we would have had a problem during the first step of our computation. So we report no answer exists and skip all of these other steps. So here is our algorithm. You can test it yourself. Later on, we'll learn how to translate this into code.
In this module, you will learn to read code and execute it by hand. Why would you want to do this when you could take a quick syntax lesson and start typing? Think for a moment about when you were first learning about written language. Did you learn to write before you could read? Probably not. Recognizing a word or sentence and attaching meaning is easier than formulating your own. You've probably misspelled a word or made a grammatical error expressing an idea that you could read just fine. Programming is much like this. You need to read for understanding and understand exactly how code is executed before you can write good code of your own. It's also easier. Reading well will help you make fewer mistakes as you go, but also help you troubleshoot when your code does something you did not expect. My background is in mechanical engineering, and in my undergraduate program, we used MATLAB for computational tasks. Despite excellent instruction and thoughtful exercises, many students, myself included, would spend hours debugging code, mostly by guessing and checking. Never once did I draw a picture of what I thought was happening or execute even a line of code by hand. And I probably couldn't have because there were a few things I didn't understand fully. While teaching, I've seen students make similar mistakes. Finding the cause of an error message is a treasure hunt, one that might take much longer than someone spent writing the code in the first place. Often, we know what we want a section of code to be doing, maybe even what we think it's doing, but unless you can be sure, you cannot be confident in your result, and you'll likely spend more time debugging than you want to. Here is an algorithm for a function we'll talk about later in the course. You can see here that each step of the algorithm changes something about the state of the program. Here are the same steps implemented in code. Do not worry if you do not know how to read this yet. The point is that the code needs to change the program in the exact same way as your algorithm. If the code is doing something different, we need to change it to match the algorithm. This is why learning to read code is so important for writing it. In this module, you'll learn to understand what statements do, both the syntax or grammar of a language and the semantics or meaning a statement has. You'll also learn how to keep track of the state of a program, where you are, and what functions can see which variables. To do this, you will learn how to draw pictures of exactly what is happening according to a set of rules. Once you can do these things, writing code will come easier, and when you do have a situation when your code does not do what you expect, you'll have a set of tools you can use to investigate your program to see what it is doing.
We are going to start learning to execute code with the most basic statements in C and build up to more complex statements from there. Here we have two variable declarations, one for an int called x, followed by one for an int called y. If we execute the first statement, we will create a box labeled x. The variable x is uninitialized, so we will place a question mark in the box for its value. If we execute the second statement, we will create another box labeled y, which is also uninitialized. Uninitialized variables are bad as they lead to bugs in your code which may be hard to find and fix. Now let's look at another example which initializes the variables. Here, the first statement declares an int called x. Executing it behaves exactly as before. We have made a box for x, which has an unknown value in it. However, the next line of code assigns 4 to x. Executing this line puts a 4 in the box for x. Now x is initialized, and we know that it has the value 4. The next line shows the declaration and initialization combined in a single statement. Executing it both creates a box for y and puts the value 6 in that box. Of course, variables are only useful if you make use of the values that they have. Here, the code first declares x and initializes it to a 4. Let us execute that statement. Next, it declares y and initializes it to x plus 2. To perform this statement, we must evaluate the expression on the right-hand side of the equals sign. X is 4, so x plus 2 is 6. We create a box for y and put a 6 in it. The last statement creates a variable z and initializes it to y minus x. As you might expect, you would take the value of y, which is 6, and the value of x, which is 4, and subtract them to get 2. You would then create a box for z and initialize it to 2. Okay, great. Now you know how to execute code with variable declarations and assignment statements. Now that you know a little bit more about expressions, let's see them in action. This code example starts with a declaration of an integer variable called x, which behaves exactly as you already have seen. Next, we initialize x to 4 plus 3 times 2. As you know from math, times has higher precedence than plus, so this expression evaluates to 4 plus 6, which is 10. So we put 10 in the box for x. Next, we declare another variable y of type int and initialize it to x minus 6, which is 10 minus 6, which is 4. So we create a box for y and put 4 in it. The last statement says x equals x times y. Sometimes novice programmers expect statements which look like this to behave like algebraic equations, where you might solve for x. However, that is not what happens. Instead, you follow the rules you have already learned. The right-hand side evaluates to 10 times 4, which is 40, and you put 40 in the box for x. Now let's see another example. Before we work through this, take a moment to see if you can figure out what the values x, y, and z have at the end of this code fragment. Okay, let's step through it. First, we declare and initialize x. Next, we evaluate x times 3, which is 6, and initialize y to that value. Next, we compute y divided by 2, which is 3, and initialize z to that value. The last statement says x equals 2 plus z mod 2. Since the 2 plus z is in parentheses, we compute that first and get 5. Next, we compute 5 mod 2. Remember from your reading that 5 mod 2 means that we divide 5 by 2, but take the remainder, not the quotient. So this expression evaluates to 1. So we update the value in x's box to be 1. Okay, great. Now you should be able to evaluate code involving a wide variety of mathematical expressions.
The next piece of C that you are going to learn about is functions. To see why they are so important, let us take a look back at our closest point algorithm. There are 2 places here where this algorithm computes the distance between 2 points. Why is that important? Well, we need to do the same computation twice. Without functions, we would write the same code twice, and that is just in this problem. What if we have other problems that also need to compute the distance between 2 points? We have a few examples of other problems that would need to compute the distance between 2 points, but there are many others. We could rewrite the code each time, which may not seem like a big deal for something as small as computing the distance, but we want to avoid duplicating code whenever possible. Every time we rewrite code, we run the risk of making mistakes and introducing bugs into our program. Furthermore, it is really boring to rewrite the same code again and again. Instead, we should abstract the computation for distance out into a function of its own. Making distance its own function means we can reuse that algorithm any place we need it without rewriting it. How would this work? Well, our closest point function would, in its code, call the distance function. That is, it would ask the distance function to perform its computation. To do this, our closest point function would first pass in parameter values specifying which points the distance function should compute on. The distance function would execute its code, doing whatever statements are in it according to the rules you are learning. It finishes when it comes up with an answer, which returns back to the function that called it. When it returns, the distance function is done, and the calling function continues its own execution, making use of the answer it got from the function it called. So how is this helpful? First, we can reuse this distance computation anytime we need. We don't have to rewrite it. We can just call the distance function to compute the distance between any 2 points. Whether we need to compute the distance at the various places in the closest point function or in some other problem we are solving doesn't matter. We just call it. The other important benefit of functions is the abstraction. Abstraction is the separation of the interface, meaning what something does, from its implementation, meaning how it does it. Once we have written the distance function, we can just make use of it without thinking about its inner workings. As you build larger and larger programs, abstraction becomes more and more important. You aren't limited to 2 functions either. You can have many functions, which can call as many other functions as they need to. For example, suppose our closest point function were part of a much larger program which has information about various types of locations and uses that information to give us the nearest location of a particular type. You might end up with something like this. The main function, which is where all C programs start, might call a function to find the store nearest point 4217, passing in parameters to specify this information. That function might then call another function to find all locations whose type is store. The getByType function could then return back a list of locations for stores, which findNearest can then use. It is totally fine for findNearest to then call another function, such as our closest point function, to find the point nearest the location we want. As we previously discussed, closest point can call distance to compute the distance between 2 points, and it will return back the distance it computed. Of course, it is totally fine for closest point to call distance as many times as it needs, getting back the answer for whatever points it passed in. When closest point finishes its computation and figures out its answer, it returns that value to the function that called it, which then finishes its computation and returns its answer to the function that called it. Okay, great. Now you have the high-level concepts of functions, Let's dive into their syntax and semantics in C.
Okay, now that you have the basic ideas of function call semantics, let us see them in action. We have three functions here, my function, f, and main. As you have learned, we start execution of a program inside of main. We've drawn a frame for main and are ready to begin executing its first statement, which declares the variable a. So we create its box inside of the frame for main. Next, we're going to set a equal to the value of the function call, my function, of 3, 7. To evaluate this expression, we need to create a frame for the function that we are calling. In this case, my function. This will hold the parameters and variables of my function. Next, we pass the parameters to my function. We create a box for each parameter with the names coming from the function declaration, x and y. We initialize these by copying in the values of the expressions that were passed. Here, 3 and 7. Next, we need to note where to return when we finish executing my function. This location in the code is named the call site, the place where the function was called. We'll note it with marker 1 in the code and put the same marker in the corner of the frame. Finally, we move the execution arrow into my function and start executing code there. Here, we declare and initialize z, evaluating the expression 2 times x minus y. The values for x and y come from the frame for my function, 3 and 7 respectively. So z will be -1. Now we have reached a return statement. Return statements tell us to leave the current function, returning to the call site noted in the frame. They also tell us the value to return to the caller. The first thing we need to do is evaluate this expression to obtain the return value. Here, the expression is z times x, so we evaluate -1 times 3 and get -3. Next, find where we should return. This is the call site we noted in the frame. Then we copy the return value back to the call site. The function call evaluates to this return value. We move the execution arrow back to the call site and destroy the frame for the function we just returned from. Now we are back in main. The call to my function evaluated to -3, so this line behaves like a gets -3. We finish that assignment putting -3 in a's box. Our next line again has a variable declaration and a function call. We make a box for b and go through the same process to call f. We make a frame for f and pass parameters. This time, there's one parameter in whose value is a times a, which is 9. We note where to return and begin executing code inside of f. Our next statement is a return statement, but the expression involves a function call. So we have to evaluate that call before anything else. We start with a frame and pass parameters. X gets the value of n, which is 9, and y gets the value of n plus 1, which is 10. We note the call site. We'll use 2 this time since we are already using 1 somewhere else, and move the execution arrow to the start of my function and start executing code there. We declare z and initialize it to 8. Now we are ready to return from my function. We evaluate z times x, which is 72. Then we find the call site noted in the frame and copy the return value there. Finally, we move the execution arrow back to the call site, destroying the frame for my function. Now we pick up where we left off in f, using 72 for the value of the call to my function. We evaluate 3 plus 72 to get 75. Since we are evaluating the return statement, this is the return value of f. So we find the call site and copy the return value there. Then we return to that call site, destroying the frame for f. Now we can finish the initialization of b. b gets 75. Lastly, we reach the return statement for main. When we return from main, the program exits, so we are done. In this video, we show an example of how you can use the printf function to print output to the terminal. We have our usual frame for main, as well as a box for output, and the execution arrow is at the start of main. We begin by declaring and initializing a to 42. Then we reach a printf call. We're going to print the string hello world. It will just print this string directly. There are no format specifiers at all. So our output is hello world. The next printf call will print the string a. Note that this prints the literal letter A, since it is enclosed in quotation marks and is therefore a string literal. This has nothing to do with the variable A. So our output is A. And we return 0 and exit main. What would you do if you wanted to instead print the value of the variable A? The F in printf stands for formatted, and there are several format specifiers you can use to format your output. In this example, first we declare and initialize integers a to 42 and b to 7. Then we reach a printf call with a format specifier. In this case, %d. %d formats integers as decimal numbers, and you'll learn later about other format specifiers. %d means printf will look at the corresponding argument to see what integer it should format as a decimal number. In this case, it is given variable a. So it prints the decimal representation of the number 42 in the location in the string where the %d is. The next call to printf has two %ds. The first refers to b, the next argument after the string, which is 7, and the second of these refers to a plus b, which is evaluated like any other expression. So it's 42 plus 7, which is 49. So the output is b is 7 and a plus b is 49. We return 0 and exit main. Another important thing to know about printf is escape sequences. An escape sequence begins with a backslash. The most common one is \n, which means new line. This printf call has two \n's, so it should print two new lines after hello world. This statement declares and initializes b to 7. This printf call has a \t in it, which means a tab. It is useful for lining up output. The output is, my answer is tab 7. We return and exit main. This introduction has shown you a few uses of the printf function, and you will see more later in the course.
Now let's see how to execute code with conditional statements in it. Here we have a function f, which has some if and if-else statements. As always, our program starts its execution at the beginning of main. The first statement declares a variable a, so we make a box for it. Even though this statement initializes a, it's going to take us several steps to compute that value, so we're going to leave a's value as a question mark until we compute the value of f of 3, 4. To evaluate the call to f, we make a frame passing the values of the parameters. We note where to return to and move the execution arrow to the first line of f. The next line of code is an if statement whose conditional expression is x less than y. We evaluate that expression and find that 3 less than 4 is true, so we move the execution arrow into the then clause of this if statement and continue executing. The next statement is a call to printf, which you are familiar with. We write x less than y in our output. Next, we return y plus x. This follows the same rules you have already learned for return statements. We evaluate the expression to get the return value, which is 7. This is what the function call will evaluate to. And now we return back to the caller, destroying the frame for f. Now we are ready to finish initializing a, since we know that the call of f evaluated to 7. So a is now 7. We are now ready for the next line of code in main. We make a box for b and call f, passing in 7 and 5. We once again want to evaluate the condition x less than y. However, now x is 7 and y is 5, so x less than 5 is false. We find the close curly brace for this if statement and see that the if statement has an else clause. So we move the execution arrow into the start of the else clause and continue executing from there. First, we execute the print statement. And then we reach another if statement. This if statement is nested inside of the else, but that does not affect the rules of how we evaluate it. We see that the conditional expression is false, so we look for the close curly brace of the if statement. There is no else clause, so we move the execution arrow immediately past the close curly brace and continue execution. There are no more statements inside the else clause, so we move the execution arrow outside of the else clause and keep going. Now we have a return statement, so we evaluate the expression x minus 2 to find that the return value is 5, which will get returned to the place that we have noted. We return back to the main and destroy the frame for f. Then we finish the assignment statement. Now we are at the return statement for main, we execute that, and exit the program.
In this video, we're going to execute code with a function g that contains a switch case statement. As always, we begin with the execution arrow at the start of main. For the statement a equals g of 10, 4. We make a box for a since we're declaring it, then we create a frame for the function g, and populate it with the values 10 for n and 4 for x. We make a note of where we are and will return to when the function is complete, and enter function g. We have a switch statement. X plus n in this case is 4 plus 10, which is 14, so we find the matching case label, case 14, and transition our execution arrow inside that case and begin executing statements there. The first statement we encounter is a return statement, n minus x, 10 minus 4 equals 6. As always, when we encounter a return statement, we're going to make a note of the value to return and leave the function that we're in, going back to the calling function and destroying the frame. We finish the assignment statement with a equal to 6. Now we reach int b equals g of a and 2, so we create a box for b, draw a frame for g passing in the arguments a, which is 6, and 2. We note our position and enter function g. Here our selection expression is 2 plus 6, which is 8, so we're going to go into the case for 8 and begin executing statements there. The first statement we encounter is x equals x plus 1, so we update the box for x to have 3 instead of 2. Now we fall through to the next case. There's no break statement here, and we don't worry about the fact that there's another case label. We just keep executing statements until we reach a break. The next statement is n equals n minus 1, so we're going to update the value of n to be 5. And now we do reach a break statement. This break statement is going to take us out of the innermost enclosing switch statement, the boundaries of which are here. As we'll see later, break could take us out of other constructs, but in this case, it'll take us out of the switch statement that encloses it, and we begin executing code after the switch. The next statement we encounter says to return x times n, which is 3 times 5, which is 15, so we return 15, return to main, and destroy the frame for g, and assign 15 to b. Now we have int c equals g of 9 and b, so we create a box for c, a frame for g with arguments 9 and b, which is 15, and note where we are and enter function g. Evaluating this expression gives us 24. Looking at our case labels, we have 8, 0, and 14. None of those match 24, so we use the default, which matches anything that's not named explicitly by another case label. We'll jump into the default case and begin executing statements there. We do x equals n, assigning 9 to x, which brings us to a break, which takes us out of the inside of the switch statement. We now return x times n, which is 81, back to main. We finish our assignment and return 0 from main, exiting the program.
In this video, we're going to demonstrate the execution of code containing a while loop. As always, we begin with the execution arrow at the start of main. The first statement declares a variable x and initializes it by calling g of 2 and 9. Inside of g, we declare the variable total and initialize it to 0. And then we reach a while loop. The conditional expression of this while loop is a less than b, which in this case is 2 less than 9, which is true. So we enter the body of the while loop. The next statement is total plus equals a. Remember that this is shorthand for total equals total plus a, so total is going to equal 0 plus 2, which is 2. We assign 2 to total, and now we have a printf statement. A equals %d, B equals %d new line, where the first %d converts the value of A to a decimal number, and the second %d converts the value of B to a decimal number. This prints out A equals 2, B equals 9. The next statement is A++. Recall that this is shorthand for A equals A plus 1, so we're going to do A equals 3. B minus minus is shorthand for B equals B minus 1, so we're going to do B equals 8. Now we've reached the closed curly brace of the while loop, so our execution arrow jumps right back up to the top of the while loop, right before the conditional expression to determine if we should enter the body of the loop. Evaluating the conditional expression gives 3 less than 8, which is true, so we enter the body of the while loop again. We do total plus equals A, 2 plus 3 is 5, so we update total. Then we're going to print A equals 3, B equals 8. We're going to increment A by 1 and decrement B by 1. We reach the closed curly brace at the bottom of the while loop again, so we jump back up to the top. 4 less than 7 is true, so we enter the body of the while loop. Total plus equals A, printf A equals 4, B equals 7, increment A and decrement B, jump back to the top of the loop. 5 less than 6 is true, so we enter the body of the while loop. We execute each statement in the loop as before. Now, however, when we get back to the top of the loop and evaluate our conditional expression, we find 6 less than 5 is false. Our execution arrow skips over the body of the loop and begins executing statements immediately after it. The value of total to return is 14, so we return that to main, leaving function g and returning our execution arrow back into main, where we can now complete our initialization of x with x equals 14. We then continue executing statements in main. We print out x equals 14, and we return 0, exiting main and leaving the program.
In this video, we're going to execute equivalent for loop and while loop code. A for loop is sometimes called syntactic sugar because it allows you to write a more compact code for counting, a common programming idiom. Let's look at their similar anatomy. Both have an initialization statement. In the for loop, it follows the for keyword, and in the equivalent while loop, it is just before the beginning of the while loop. The conditional expression is the second piece following the for keyword, and the piece inside parentheses after the while keyword. The increment statement is the third piece following the for keyword, but an equivalent while loop would increment inside the loop body just before the closed curly brackets. Finally, any statements that happen in the body of the for loop could also happen in a while loop before the increment statement. Let's see these two equivalent loops in action. As always, we begin with our execution arrow inside main. We initialize y to 1 and n to 3. Now the syntax of the for loop has the int I equals 1 initialization just after the for keyword, so we'll pause the execution arrow there as the while execution arrow on the right enters the open curly brace and initializes I, changing the state of our program in the same way. The purpose of the curly braces is subtle. Since scope of variable I is limited to the for loop, the curly braces restrict the scope of variable I to this box. Otherwise, its scope would be the whole main function, and it would not be equivalent to the for loop version. Looking at the conditional expression, we see 1 less than 3 is true, so we enter the loop and begin executing statements there. Y times I is 1 times 1, which is 1. Next, we'll increment I to 2 and return to the top of the loop. Checking the conditional expression, 2 less than 3 is true, so we enter the loop and evaluate y times I, which is 1 times 2, assigning 2 to y. We'll increment I to 3 and return to the top of the loop. 3 less than 3 is false, so we move the execution arrow to just after the loop. Respecting the scope of I in the for loop, we also exit the curly brace after the while loop, destroying the box for I since it is now out of scope. Finally, we return 0 and exit main.
In this video, we have an example of nesting. In function f, we have a while loop with an if statement inside of it, and inside of the if statement, there's a for loop. The important thing to remember with nesting is that there's really nothing special about it. We follow the same rules we've always seen. We begin with our execution arrow at the start of main, and the first thing we're going to do is call f, passing 3 for A and 8 for B. We create a frame as always, and we're going to remember where we're going to return and begin executing code inside of f. Since A less than B is true, we're going to go inside the body of the while loop. We print A equals 3, B equals 8, and then we reach an if statement that checks if A mod 2 is 0. Remember that % is the mod operator, which computes the remainder when you do division. 3 divided by 2 has a remainder of 1, so 3 mod 2 is 1. A mod 2 is not 0, so this conditional expression is false, and we skip over the if statement. A++ increments A to 4, and B decrements B to 7. Now we've reached the end of the while loop. So we jump back to the beginning and test its condition again. A less than B is true, so we enter the body and print A equals 4, B equals 7. Now when we look at A mod 2, 4 mod 2 is 0. 0 equals 0 is true, so we enter the if statement. Now we have a for loop. Is going to declare an int I and initialize it to the value of A. So we make a box for I and set it equal to 4. We then test the condition of the for loop. 4 less than 7 is true, so we enter the body of the for loop. We print I equals 4. Then we perform the increment statement, assigning 5 to I, and return to the beginning of the loop. We check the condition again. 5 less than 7 is true, so we enter the for loop again. We print I equals 5. Then we increment I to 6 and return to the beginning of the loop. We repeat this process. 6 less than 7, print I equals 6, increment I to 7 and return to the beginning. This time, 7 less than 7 is false, so we skip past the for loop, leaving the scope of I and continue executing. We're now at the end of the if statement's body, so we resume executing right after it. We increment A to 5 and decrement B to 6, and now we're at the end of the while loop. So we jump back to the top. A less than B is still true, so we enter the body. We print A equals 5, B equals 6. We check A mod 2. 5 mod 2 is 1. 1 equals 0 is false, so we skip the if statement. We increment A to 6 and decrement B to 5, and return to the top of the while loop. 6 less than 5 is false, so we skip over the body of the while loop, reaching the end of the function. This causes us to return to main. The only thing left in main is the return statement, so we return 0 and exit the program. In this example, you're going to learn how to execute code with a continue statement in it. Here, we have a for loop that has a continue statement inside. With a for loop, when you execute a continue statement, the loop increment is performed with the continue. To see this, let us first convert this for loop to the equivalent while loop. Here, we've taken one step in the conversion process, moving the variable declaration before the loop. To move this closer to being a while loop, we've moved the increment statement I++ to the end of the loop. But notice that we also put I++ right before the continue statement. Now we have finished changing this for loop to an equivalent while loop. Since I will go out of scope at the end of the function anyways, we can get rid of the extra curly braces that we wrote here without changing our code's behavior. Now we are ready to begin executing. We begin by calling our print remainders function, passing in -2, 4, and 5 as parameters. We then declare I and initialize it to low, and reach our while loop. I less than high is true, so we enter the while loop. I equals 0 is false, so we skip past the if statement and print 5 mod -2 is 1. We increment I, and now have reached the end of the while loop. So, we go back to the top of the loop. I less than high is true, so we enter the loop body. Again, I is not 0, So we skip the if statement and print out 5 mod -1 is 0. We increment I and then return to the top of the loop. I less than high is still true, so we go inside the loop body. However, now I is 0, so we enter the then clause of this if statement. We print that we cannot divide by 0, increment I, and now reach the continue statement. The continue statement just takes us to the start of the loop again, right before we check the loop condition. So we move the execution arrow back here. Now we just do the next loop iteration as you would expect, since I is 1, not 0, printing out a message and incrementing I. We do the loop again with I being 2, printing out that 5 mod 2 is 1. And finally, one more time through the loop with I being 3. After this last iteration, I less than high is false, so we skip the body of the while loop and return from print remainders. Now we return from main, exiting the program.
At this point, you've seen a lot of C syntax and learned the semantics of it, how to execute it by hand. So far, the only type you have seen is int, as in int x equals 3. You're probably wondering about types and what exactly int means, or, for that matter, what exactly a type is. In the upcoming lesson, you're going to learn the answers to these questions and many other things about types. All of this is going to build on one key principle of computer science. Everything is a number. Computers can only operate on numbers, so all data has to be represented numerically. Types tell the computer how to interpret and operate on the numeric representation. As you progress through this lesson, you will learn about other built-in types besides int. You will also learn about implicit type conversions and explicit type casting, as well as how to make your own types to represent whatever data you need to work with. In this video, we're going to execute some calls to printf using a variety of format specifiers so you can see how to print types other than int. First, we initialize a char letter to be G, an int neg number to be -1, and an unsigned int age to be 33. Next, we come to a print statement. Printf will look for any format specifiers, and in this case, it has a %c telling printf to look at the next argument and format it as a character. It prints, my name begins with G. The next statement has the familiar %d, and we've seen before that it will print neg number as a decimal integer. The next statement prints the value of age as a decimal integer, but the next statement uses the %o format specifier telling printf to print the value of age in octal or base 8. The final statement has a %x telling printf to print the value of age as a hexadecimal or base 16 integer. What if we change things around a bit and use format specifiers that seem strange for the types of data we are passing in? We start the same way, but now our print statement uses %d to format letter. What will happen? Well, remember that everything is a number. Letter actually has a numerical value, which is 71. This numerical value is what actually gets passed to printf. Printf has no idea that the 71 value it receives is originally from a char, so it just prints 71. Next, we print neg number, which is -1, as a hexadecimal number. If you work out how -1 is represented with a 32-bit signed integer, you will find the hex value is FFFFFFFF. Our next statement uses %u, which formats an integer as an unsigned decimal number. But we are passing in neg number, so what will happen? Remember that everything is just a bunch of bits to the computer. If you take the binary representation of -1, which is 32 ones, and interpret it as an unsigned 32-bit integer, you get the largest possible 32-bit unsigned integer, which is about 4.2 billion. Our last print statement uses %c to format the integer age. What happens here? Well, again, everything is just a number, so printf will print out the character whose numeric representation is 33, which is the exclamation mark character. What if we work with floating point numbers instead? Here are some more printf calls that use floats and doubles. P1 is a float, 3.141592, and P2 is a double that contains more digits of pi. The first call to printf uses the %f format specifier to print P1 as a floating point number, The next call has a %e, which means print P1 in scientific notation. Note the e plus 00, which means times 10 to the 0th power, or times 1. If we were to print 100 pi using scientific notation, we would get e plus 02 for times 10 to the 2nd power. Next, we have the format specifier %.10f. The .10 between the % and the f means to print 10 decimal places. When we do this, we get a slightly odd answer. Where did this 0258 come from? This comes from the fact that floating point numbers can't represent every possible number precisely. C rounded 3.141592 to the nearest representable floating point number when it performed the initialization of P1. When we print P1, it converts that number, which is actually stored in P1, to a decimal representation. If that is confusing, it is okay for now since we will not do much with floating point, but if you find yourself writing real programs with floating point, you need to understand how all of this works to avoid subtle and dangerous problems. Next, we print P2 with the default formatting for a double, which prints 6 digits after the decimal, rounding the last one. Our next printf prints P2 with 10 digits after the decimal. Here they are all what we expect. Why is this different? Doubles can represent more numbers more precisely than floats can, so the inaccuracies of representing this number do not appear in these 10 digits.
Let's take a look at some example code that shows when implicit conversions happen and how you have to be careful about types. First, we make an int called n hours and initialize it to 40. Next, we make n days and initialize it to 7. Next, we have a float called average, which is initialized to n hours divided by n days. Both n hours and n days are ints, so this is integer division. We have 40 divided by 7, which for integer division results in 5. Now, since we are assigning an int to a float, the compiler will implicitly convert that integer result to a floating point number. But it does that after the division, so we end up initializing average with a value of 5.0. Then we print out that 40 hours in 7 days is 5.0 hours per day. This is not the right answer, so let's fix this code. Here we've made one small change to the code. We have explicitly cast n days to a float before we do the division, which is called out with the red underline here. We start the same way. N hours is created and initialized to 40, and n days is created and initialized to 7. However, now things go differently. The divisor of this expression is now 7 cast to a float. So we need to evaluate the integer 40 divided by the floating point number 7.0. Computers divide integers by integers or floating point numbers by floating point numbers. So the compiler has to implicitly convert 40 to a floating point number before doing the division. Now we are doing floating point division. 40.0 divided by 7.0 equals 5.71. We now initialize average with this value, which means that when we print out our results, we get the correct answer. Now you have seen both implicit conversions as well as explicit casts. Casting is something you use when you need to. However, you should use it sparingly, only when you think through what you are converting between and why.
You just read about how everything is a number. But let's see how this principle applies to some things that may not seem like numbers at first glance. Strings are numbers. You have seen literal sequences of characters before, such as hello world. But did you think about how the computer stores them as numbers? Each character occupies some of the computer's memory. We'll talk about exactly how much later, so you can think of each character conceptually in a box. In terms of hardware, though, the computer stores each character as a number. You can look up the decimal or hexadecimal values of different characters in an ASCII table, and you can see the decimal values of these particular characters here. Of course, the computer stores them as binary numbers. One fun consequence of computers storing letters as numbers is that we can do math on them. This principle underlies most modern methods of cryptography. Another thing that may not seem to be a number at first is an image, like this one of some flowers. This image is made up of about 1 million pixels, which each numerically represent the colors in the image. To see these pixels, let's zoom in on this small section of the image. Here, you can see the image magnified several times. You can see how this image looks blocky or pixelated. This is what the image actually looks like if you could look that closely. Note that if you try this yourself, you might end up with something that looks much smoother like this. Most image software will apply algorithms to smooth out the pixelation when you enlarge an image. You have to turn that off to see the original pixels. Let us return to our enlarged image that shows the original pixels more clearly. If we look only at a subset of this image and blow it up even further, we can see and talk about the individual pixels more easily. Here are 16 pixels from the original image, which had about 1 million pixels, just to give you an idea of how much we have zoomed in now. This dark purple pixel has a red value of 55, a green value of 27, and a blue value of 75. Meanwhile, this golden pixel has drastically different RGB values, 166, 136, and 41, giving it an entirely different color. Sound is another important thing that computers process. As I'm talking, you can see the waveforms of what I'm saying. The computer encodes these as numbers and sends them to the sound hardware, which uses them to determine how to move the speaker, generating the desired sound. There are many other types of data you might want to represent and compute on. You'll learn about data that is formed from sequences in Course 3. For now, you're going to learn about structs and type defs.
In this example, we will see the semantics of a small piece of code which works with this struct rect_t. This struct represents a rectangle with 4 ints, left, bottom, right, and top. And here is some code which declares and uses a struct rect_t. As always, we start execution at the beginning of main. The first statement declares a variable of type rect_t called myRect. We will draw a box for this variable inside of main's frame and label it myRect. However, unlike other boxes we have drawn, this box has 4 other boxes inside of it, one for each field of the struct, left, bottom, right, and top. As we have not assigned any values to these fields, these boxes are uninitialized, so we have placed question marks in them. The next line says myrect.left equals -4. This is an assignment statement, so we must find the box named by the left-hand side. The first part of this line names myrect, which is the entire large box. However, it says .left, which names the box labeled left inside of myrect's box. Remember that dot means inside of. So now we will put -4 into this box. The next line behaves similarly, except that we are putting 1 into the bottom box inside of the myrect box. And likewise for assigning 8 to the myrect.right, and assigning 6 to myrect.top. Now we are going to print some information about this rectangle. Again, myrect.left names the left box inside of the myrect box, so we will pass -4 to printf for the first %d. And we will pass 1 to printf for the second %d. So we will print that bottom left equals -4, 1. We will then do a similar thing for the top right. Now you have seen the semantics of declaring and using structs.
Here we have a struct declaration for a rectangle. When you declare a struct, the struct tag, in this case rect_tag, identifies the struct's type, but by itself is not a type name. When you want to name the struct type, you have to include the struct keyword like you see here. Many programmers find it tedious to write struct everywhere they need to use their struct types, so they use typedef to define a new type name for the struct type. One way to use typedef with our rectangle struct is shown here. The typedef keyword says that we are going to make a new name for an existing type. The new name in this case, rect_t, comes last in the declaration, and the name of the existing type comes between them. Notice that here, the existing type is struct rect_tag. Now we can just use rect_t as a type name. It is an alias, or another name for struct rect_tag. There are a couple other ways we can do the same thing with typedef. We mention them all so that if you see one or the other ways in someone else's code, you will not be confused. We can combine the struct declaration and typedef into one statement. This follows the same rules we just discussed. The new name rect goes at the end of the typedef statement, and the existing type goes between the new name and the typedef keyword. It just happens that here the existing type gets declared in the typedef statement. The third option is the same as the previous one, except that the struct tag is omitted. This makes a struct with no tag and immediately aliases this struct to rect. Typedef has uses beyond just structs. Sometimes we are writing some code that deals with RGB values for pixels. In this hypothetical example, we initially use unsigned ints to represent the red, green, or blue components of each pixel. But what happens if later we realize that it would be better to use an unsigned char, since RGB values can only be between 0 and 255 and we don't want to waste memory? With the way we wrote the code, we have to go find every single place that we used unsigned int to represent an RGB value and change it. We can't even use the search and replace functionality of our editor, since there may be other uses of unsigned int that do not represent RGB values, so we don't want to change them. Such a change is tedious and error-prone. In fact, one important rule of programming is to write code so that if you have to change something, you only have to change it in one place. Now suppose we had originally written our code this way. Here we used typedef to make RGBT an alias for unsigned int, and then used RGBT as the type name everywhere we needed to talk about an RGB value. With this code, if we want to change the type we use for RGB values, we can just change the typedef statement and everything else will change correctly. As a side benefit, this helps the readability of our code. Anyone reading the code can tell when a variable, parameter, or return value is an RGB value, since its type is RGBT. Typedef can be great to make your code easier to modify and easier to read.
Now we're going to show you how to define and use your own enumerated type. At the top of the screen, we take a color-coded threat level of a standard security system and encode it into an enumerated type. There are 5 possible levels: low, guarded, elevated, high, and severe. We can refer to these levels using exactly these words throughout our code. Next, there are 2 helper functions whose definitions we will show you later. The first function is print threat, which prints the string associated with a particular enumerated type. The second function is print shoes, which prints whether a person is required to take off their shoes given the current threat level. Our main initializes a threat level, prints it out, and then calls these 2 helper functions. Let's take a closer look at our enumerated type. C creates a correspondence between each of these words and an integer value, so low has the value 0 and severe has the value 4. Notice how the function printThreat can refer to these levels using exactly these words throughout its definition, making the code much easier to read. PrintShoes does this as well. Inside the main, we declare a new variable of type threatLevelT called myThreat. We initialize this variable to the enum high, which has the integer value 3. In order to print out the current threat level, we call the function printThreat. We create a stack frame for printThreat in which the argument myThreat will be referred to as threat. We mark the call site location and step into printThreat. Inside printThreat, there is a switch statement which checks the value of the threat and jumps to the corresponding case. Here, we're jumping to case high. Inside of this case, we print orange/high, and the break exits us from the switch statement. Now we return to the function that called printThreat, which is our main. Upon returning, the stack frame for printThreat is destroyed. Next, we execute the call to printShoes, creating a stack frame for printShoes in which the argument myThreat is referred to as curThreat. We mark the call site location and step into printShoes. Inside printShoes, there is an if-else statement. The if clause tests whether the current threat is greater than or equal to elevated. In this case, we're testing whether 3 is greater than or equal to 2. Since it is, we step into the then clause, print out the message, please take off your shoes, and exit the clause. Now we return to the function that called printShoes, which is our main. Upon returning, the stack frame for printShoes is destroyed. Finally, the program exits the main and its stack frame is destroyed. Notice how much easier the code is to read because we've used an enumerated type. If instead we had an int called threat level with values 0 through 4, the code would be littered with a lot of numbers whose meaning might be unclear to the reader. Enumerated types make it easier to read, write, and modify code.
My name is Evie. I study at the Duke University for the MEng program, aka Master of Engineering program, and I'm studying electrical and computer engineering. It's a really awesome experience to be a student in this university and in this program, and I learn a lot here. For some new programmer, people may think that programming is totally magic, but actually it's not. Everything is following the logic and have to make sense in the programming world. So first, you need to trust the logic rather than just think random things. And then also for the programming, planning is something that you have to really take into consideration. So rather than just put some random things and pretending you're working in front of a screen and like typing things on a keyboard, you actually need to first make plans, draw pictures, and seriously think about what you need to do, and then implement things in the programming world. So, and also in Duke University especially, the professor and all the courses is very well planned and designed. So trust all the course project you have to do and do it step by step. You will finally be an awesome programmer. There's tons of projects I've finished in the whole program. One thing I really want to talk about is the UPS and Amazon project I've done in the server software class. So basically what's happening is that one team need to in charge of the UPS system and another team need to in charge of the Amazon system, and we need to design the protocol all together to make everything work. This project is very special for me because it actually mimics what is happening in their industry life. Because in industry, there's no way you can finish a whole system by yourself or even by one team. So what is very important is that you need to learn how to communicate with other team and design their protocol altogether. So during the whole developing process, we actually need to change our protocol step by step and finally get to the perfect one. The process is a little bit painful, but finally when we put everything together and find the whole system is work perfectly, it's a really good and inside peaceful and happiness. For those students who are struggling in finding a job or an interview, I totally understand what you're feeling right now. I know it is hard, but trust me, you'll be fine. I think for the most important things about finding a job is not about how can I pass this interview, but how can I be a great software engineer. To achieve that goal, all you need is to practice, practice, and practice. Following all the course project and all the advice from all those professors, because they have their experience and they know what their industry would need. Once you get more and more comfortable to be worked as a software engineer, the job will just come to you.
You've learned a lot about thinking through algorithms with the 7 steps, the syntax and semantics of C, and the everything is a number principle and how it relates to types. We're going to take a moment to underscore the importance of being specific when you write an algorithm. Humans can usually figure out vague instructions because they have common sense. However, computers do not have common sense and only do exactly what you tell them to. When you write an algorithm, you have to carefully think through exactly what to do and be very specific as you write it down. In the next course, we'll delve into turning your algorithm into code, as well as compiling and running the code, and testing the code to be more confident that it's correct. Then debugging it when something goes wrong. However, before we get there, we're going to wrap up this course with you writing an algorithm in English and having one of your fellow Coursera learners execute the algorithm. Of course, you will also execute someone else's algorithm and peer review their work. You want to be specific and clear when you do this so that whoever executes your algorithm knows exactly what to do. To underscore the importance of being precise, we're going to have a fun little demonstration of a vague algorithm. Genevieve wrote me an algorithm to make a peanut butter and jelly sandwich, and I've forgotten all of my common sense, so I'm only going to do exactly what she said. All right, Genevieve.
This is pretty basic. I can't imagine what could go wrong.
Okay.
1. Get out 1 piece of bread.
Okay, that seems hard to screw up.
So far, so good. 2. Use a knife to put the peanut butter on it.
Okay. This is trickier than you think. Never knew that making a peanut butter sandwich was so difficult. All right.
3. Get out another piece of bread.
Okay.
4. Use the knife to put the jelly on.
Okay. Well, she didn't really tell me what to put the jelly on, but I guess when someone tells me to like put my clothes on, they mean to wear them. So maybe she wants me to like wear the jelly? Yeah, okay.
5. Put the 2 pieces of bread together.
All right, do you want a bite of this sandwich?
Your final project in this course is going to be to write a sorting algorithm. That is, an algorithm that takes a sequence of numbers as input and puts them in ascending order from largest to smallest. For example, if you had the following input data, you would want your algorithm to rearrange them so that you have this sequence, the same numbers, but ordered from smallest to largest. Of course, what we did here just reshuffled them all at once in a way that is very hard to generalize. You will want to think of a more step-by-step way to sort your data for any sequence of numbers. Okay, so why think about sorting? Well, for one thing, sorting is an important and ubiquitous algorithm in computer science. For example, my email client lets me sort my messages by subject, date, or a variety of other criteria. Sorting data makes it easier to find what you need. When I'm on Facebook, there's a list of trending stories. How would you get the most popular stories from a list of all stories? You would sort by popularity, then take the top items from the list. Likewise, if I search Google for something, it has many search results that might match my query, but sorts them based on its ranking of them, putting the results that are most likely to be the best at the top of the results it displays. And, of course, there are many other examples. Another reason why we picked sorting for you to work on is that there are many different correct ways to do it. It is good to learn that many problems have a lot of different solutions. As you peer review other people's solutions, you will hopefully see approaches that are different from what you thought of. And lastly, it is easy to verify that the answer is correct. When you peer review someone else's algorithm, you can easily check if they got the right answer for some input data by looking to see if they put the data in the right order. So now, let's put the 7 steps to use and write a sorting algorithm. Hello, and welcome to Course 2, Writing, Running, and Fixing Code in C. Hopefully you took our Programming Fundamentals course and are familiar with the 7 steps, as well as the basics of the syntax and semantics of C. In this course, we are going to focus on going from an algorithm to a working program. We'll start by talking about turning an algorithm into C code. Then we're going to talk about editing the code, writing the code into the computer. We are going to teach you to use Emacs, which is an editor for professional programmers. Next, we'll talk about compiling the code using GCC. GCC, which stands for GNU Compiler Collection, will turn your code into a format that the computer can directly execute. Once you have compiled, it's time to run your code. But it may not work the first time. We'll talk about testing your code to find problems in it and debugging your code to fix those problems. We'll also introduce you to some very useful tools like Valgrind and GDB. Many of these tools are designed to be expert-friendly. They are used by professionals and require a bit of time investment to become proficient in them. So why are we using these professional-grade tools rather than starting you on something easier? If you work with a novice-friendly tool, it is easy to use at the start, but you quickly plateau in what you can do with it. On the other hand, expert tools may be a bit difficult at the start, but as you gain experience with them, You far exceed what you could do with a novice tool. If you start with a novice tool, you end up stuck in your comfort zone. It is hard to switch to an expert tool because of the upfront cost to learn it. However, if you start with an expert tool, you can learn to use it from the start and enjoy the power it brings you in the long run. As an example of novice versus expert tools, let's talk about recording video. If I want to record video, I just pull out my cell phone and hit record. The cell phone is a great example of a novice-friendly tool. It's super easy to use, but has few, if any, advanced features. On the other hand, a professional video setup is an expert-friendly tool. It has a variety of features that my cell phone doesn't. I don't need to do things like connect wireless mics to my cell phone, but such features are needed in a professional setup. Another subtle point about tool selection is that your tool choice sends a signal about your professionalism. Would you hire a professional videographer who just used a cell phone? I'd be a little bit skeptical. The same thing happens with programming. I've had students who have told me that they were so glad they learned these tools because interviewers noticeably took them more seriously when they found out the students used professional tools. We're going to wrap this course up with the start of a project that spans the 3rd and 4th courses. You'll be writing a program that takes a description of a poker hand and computes the odds of each hand winning. So let's get started.
As an example of the 7 steps, let us consider the problem of finding the intersection of 2 rectangles. We'll deal with only rectangles whose edges are horizontal and vertical, making things much simpler. To do this problem, you need a bit of domain knowledge, such as what a rectangle is, which you may recall is a 4-sided shape with adjacent sides at right angles to each other, and what it means to find the intersection of 2 rectangles, which is finding the area that is inside both rectangles. Step 1 is to do an instance of the problem. We've started here with a blank Cartesian plane on which we can precisely draw rectangles. Now I've picked one rectangle from -4, 1 to 8, 6. Next, I've picked another rectangle, which goes from 1, -1 to 4, 7. The intersection of these 2 rectangles is highlighted in green, which we can see goes from 1, 1 to 4, 6. We'd like to write down exactly what we did to figure this out, but our inclination might just be to say that we looked at the answer in our drawing. This happens frequently. You just know what you did, but you have trouble thinking through it step by step. When this happens, a good idea is to work through another instance and try to think about what you are doing. Here, we've taken away the grid lines so that we can't just read the coordinates off our final drawing. For my first rectangle, I chose -2, 1 and 6, 3. Then I chose -1, -1 to 4, 4 for my second rectangle. The intersection here is in green, but what are the coordinates of its corners? This rectangle goes from -1, 1 to 4, 3. Now let's write down exactly what we just did. The first question we should answer here is, how did we represent a rectangle as numbers? The answer is that a rectangle is 4 integers, left, bottom, right, and top. Next, we need to think about what steps we took to come up with this answer. First, I figured out that the left edge has an x-coordinate of -1. Next, I figured out that the bottom edge has a y-coordinate of 1. Then I figured out that the right edge has an x-coordinate of 4. Finally, I figured out that the top edge has a y-coordinate of 3. My answer was the rectangle -1, 1 to 4, 3. Okay, now we're ready to generalize these steps to any pair of rectangles. Why did we pick -1 for the left side of the answer? We might think this was because it's R2's left, but will it always be R2's left? No, it was only R2's left this time because R2's left is larger than R1's left. More generally, it will be the maximum of R1's left and R2's left. What if we had not cut this subtlety now? We should catch it later, either in step 4 when we test our algorithm by hand, or in step 6 when we run test cases on our code. If we catch it later, we would come back to step 3, correct the algorithm, and redo the later steps. So generally, our answer's left side will be the maximum of two input rectangles' left sides. What about the bottom? Why was it 1? Again, we might think that it was because it is R1's bottom, but this runs into the same pitfall we just discussed. It is actually the larger of R1's bottom and R2's bottom. We then go through similar thinking for the right, but this is the minimum, not the maximum, of the two input rectangles' right sides. Lastly, the top is the minimum of the two input rectangles' tops. Let's write that down a little bit more explicitly as directions. We will make a rectangle, which we will call ants, with the sides determined by the maximum or minimum of the input rectangle's sides, as we just discussed. And then the rectangle ants, which we just made, is our answer. Next, we should test our algorithm. It seems pretty straightforward, so what could possibly go wrong? For one thing, the only inputs that we used to construct it had the same general shape. R1 was wider than R2, and R2 was taller than R1. If we had made any of the mistakes we discussed earlier in step 3, we would not have caught them yet. A slightly more subtle case exists that we have not yet accounted for. It is possible that the rectangles might not intersect. What does the algorithm produce for this case? What should it produce for this case? It really should produce no such answer, so we need some way to represent that. Now that you have an algorithm developed, it's time to turn that into code. You can do this with pencil and paper, or typing the code into an editor on the computer. You'll learn shortly how to edit your code on the computer, as well as how to actually run the resulting program. But first, it is informative to see the translation of an algorithm to code. The first thing you will want to do is write the function declaration. You learned the syntax of a function declaration previously: the return type, followed by the function name, and then the parameter list. Curly braces enclose the body. Once you have written that, it's a good idea to write your algorithm steps as comments in the code. Remember that comments are ignored by the computer and are just there for humans to read. For the algorithm that we are developing, we first need a struct for the rectangle type. You have seen structs before, so there should not be anything new or surprising here. One question in writing this is whether the coordinates should be ints or floats. Here, we've decided to use floats so that we can have rectangles with fractional coordinates. Next, we have written the function declaration with the algorithm steps written as comments. This function, which is called intersection, takes two rects as parameters, R1 and R2. It returns a rect as its answer. The first step tells us to make a rectangle called ants. Since we want to make a new piece of data, we are going to declare a variable. To do this, we need its type and its name. Next, we want the ants' left to be the maximum of R1's left and R2's left. We want to set the value of ants' left, so we need an assignment statement, where the left-hand side is ants.left equals. But what goes on the right-hand side? It seems like it might take more than just one simple expression to figure out the maximum of R1's left and R2's left, so we should abstract the computation of max out into a function. We should call that function here and think precisely about what it does. What should this function be called? What should it take and return? What should it do? Then we can go write it later. This function should be called max, and it should take two floats and return a float which is the larger of the two floats passed in. Its declaration would look like this. So now we can just write a call to the max function and assume it will work after we write it. The last thing we need to figure out for this line of code is what parameters we pass to the max function. We want the max of R1's left and R2's left, so we just need to write those down in code. Great, now we are computing the max of R1's left and R2's left and assigning that result to ants' left. The next step is to set ants' bottom equal to the max of R1's bottom and R2's bottom. We can make use of the max function that we are already going to write to do this step. So you end up with ants.bottom equals max of r1.bottom and r2.bottom. The next step is to make the top be the minimum of r1's and r2's top. As before, we should think of a function that we want to abstract out this minimum computation into. We'll use that function now and write it later, giving us this line of code. Then we need to do to the right, which is pretty similar to the top. That leaves us with one step. We say that rectangle ants is our answer. How do we have a function give back an answer? We use a return statement, return ants. Great, now we're done, right? Almost. We have a few things left unfinished. First, we have to write max and min, which we promised ourselves we would do earlier. Second, we have to test this code before we conclude that it is finished. We'll learn about testing code soon. However, we'll do max and min now. Here's the declaration for max with an algorithm already written as comments inside of it. We did not show steps 1 through 4 to come up with these steps, but you are certainly welcome to work through those yourself. The first thing that this algorithm does is check whether f1 is bigger than f2, doing one thing if so, another if not. This translates into an if-else, as you can see here. In the then clause of the if-else, we say that f1 is our answer. As you learned earlier, you give back an answer with a return statement, as you see here. In the else clause, we say that f2 is our answer, which also translates into a return statement. For min, we would have a very similar algorithm. The only difference is that we see if f1 is smaller than f2. The fact that the algorithm is almost the same means that the code will also be almost the same. We have an if statement with a then clause that has return f1 and an else clause that has return f2. Great. Now we have translated our algorithm into code.
Okay, now you're ready to start actually writing some code in a Unix environment. We're going to take a little bit of time to introduce you to how to use this environment, how to edit files, how to use Git, and various other tools that you'll be using as you program. So here I am in Coursera on the first assignment, which is really just a walkthrough of using the environment, which will be coming up as the next item in Coursera. So you can go ahead and open that up and follow along if you want. I'm going to go ahead and sign that I'm going to obey the rules of Coursera's honor statement. I'm going to do my own work. And I'm going to click Open Tool, and it gives me this window, which basically is a Unix terminal. So this is a thing called Xterm.js. It gives you an Xterm, which is a standard Unix terminal in your web browser. Now, I'm going to make mine a little bit bigger, so I'm going to make it like 140 columns and 36 rows, just so I have a little more space to type. And you'll see that it says this is my first time here, it's setting things up, and welcomes me to the practice programming environment. Now at this point, you're probably a little unfamiliar with Unix and command lines and stuff. You'll have some readings about these. You'll get lots of practice as you go. The first thing I'm going to do is type ls, which tells Unix to list the current contents of the directory. And we'll see that there's a readme file and a directory called learn to program. And this learn to program directory is going to be where you have all your assignments. This first one is 00 hello, assignment 0. And the first thing we're going to do is just write a file called hello. It's not really a programming activity, but just to get you used to these basics before you start trying to write some code. So if I open up this file readme using Emacs, which is the editor you're going to learn to use, it'll take it just a little second to open, and then you'll see that there's a bunch of text here. So I can scroll around and read this. And as we just said, your goal is to create a file called hello.txt with one line that says hello. And we've given you some instructions here to walk you through this. So use Emacs to open and create a new file called hello.txt. And it says type c-x, c-f. So in Emacs speak, this is Control-X, Control-F. So I'm going to hit Control-X, and then I'm going to let go of X and hit Control-F. And you'll see at the bottom here, it says find file and prompts me for the file name. So it gives me the path, that is the set of directories I'm in leading up to this. And I can type hello.txt, which is what I want, and then hit enter. And at the bottom it says new file. You can see it says hello.txt here, which is the name of this file. But unfortunately, I've just lost track of my directions because they're over in that other file. Emacs has this really cool feature that lets you look at two files at once. So I'm going to hit Control-X, 2, and It's going to split the buffer in half. So I've got one buffer at the top, one buffer at the bottom. They're both in hello.txt at this point. Looking at two different places in one file can be really useful. But I want to change what's open at the top, so I hit Control-X-B. And it asks me, what would I like to switch to? README is the default, so I'm just going to hit Enter. And now I've got README on top, hello.txt at the bottom. And you can see I actually had those instructions here. And if I want to move back and forth between these, Control-X-O, you can see my cursor is jumping between the two buffers as I hit Control-X-O. Okay? So now I want to go into this and I want to write the word hello. And I'm going to hit Enter, so there's a new line. We generally end files with new lines. And then I'm going to save the file with Control-X, Control-S. And you'll see at the bottom it says, I wrote this file. It's now saved. Okay. Now I want to grade this assignment. So what we're going to do is we're going to suspend Emacs. I'm going to hit Control-Z. You'll see it says stopped Emacs README. Emacs is still there. It's just kind of frozen in the background. If I wanted to bring it back, because maybe I forgot to read the instructions that were coming up, I can type FG. We'll bring it back. And you'll see that it tells me to run some commands with git. Git is a really popular revision control system. It's used by lots of professional developers. You'll learn about it a lot coming up. For right now, what we're going to do is we're going to add, commit, and push this file, which puts the file into Git and submits our work to the grader. So I'm going to do git add hello.txt. It doesn't say anything. That means everything worked correctly. Then I'm going to say git commit-m did assignment 0. So this -m says I'm going to give my commit message on the command line. It's just a little note about what I'm doing right now. It says it committed it to master, and then I'm going to do git push, and it sends it over to a place that it shares with the grader. And so now you can see that the next thing is to grade the assignment. So if I do grade, it checks some stuff, makes sure I've submitted all my files, runs the grader, it says I've passed this assignment, and it tells me that it's releasing the next assignment and that I should continue watching videos until I've watched the week 1 video about grading, and that's going to cover the materials that we need to do this assignment. It also says if I run git pull, I'll get my grade report and the next assignment. So git pull, kind of the opposite of git push. I'm going to get assignments that were released to me. If you were developing professional software, you'd be getting code that's written by your collaborators. And you'll see that I got, now there's a file called grade.txt. In this case, it just says my file matched the expected output because there's not really much that it can tell me about this. But in general, this is where it's going to tell you which test cases you pass, which ones you fail, and something about your grade. And so then we have the next assignment. We'll be ready for you to come back and do that after you've watched some more videos. All right, so you've seen a video where we used Emacs to write a little simple file, save it, we added it to Git and submitted it to the grading system. Emacs is a really powerful editor. It has lots of features. We're going to show you some simple ones like searching, undoing, some cool features of Emacs's undoing, and a little bit more advanced features like keyboard macros. We're obviously not going to cover all of Emacs in this video, but we're going to show you some of the more useful features, and then you can learn a lot more as you go. So if I look in this directory, I have a text file and a C file to work with. I'm going to open up this text file and start working with that. It's just a bunch of text from Chapter 2 of All of Programming. You probably read most of this in your readings in Course 1. So one of the things I might want to do is search. If I hit Control-S, you'll see at the bottom of my X term it says iSearch. Emacs has incremental search, which means as I type a search term, it will start searching for whatever I've typed so far. So if I type I, for example, it goes to the first instance of I and highlights all the other ones. If I type M afterwards, it's going to refine that and start showing me things like important and sometimes and simple. If I were to type E, it comes down here to sometimes, refining that further. This is really nice when you're programming because you want to search for a function name or something. You hit Control-S, you just start typing a little bit. You'll quickly get to what you want and you generally don't have to type out the whole thing. If I hit backspace, it goes back to IM. I might want important, but not this one. So if I hit Control-S again, it will search forward for the next instance of IM, and I can keep doing that. And at this point, it needs to scroll down. In a normal Xterm, this wouldn't happen. Xterm.js has a little bit of a weird bug where it doesn't always redisplay the screen correctly. If that happens, just hit Control-L, and that'll make Emacs redraw the screen completely. So then I can just resume by hitting Control-S again and searching some more. That bug's a little annoying, but Xterm.js isn't my thing. Okay, so that's searching. You can also search backwards. If I hit Control-R, it'll say I search backwards, and I can search backwards, and it will go backwards. And I can change between these with Control-S, Control-R to move forwards and backwards through my searches. All right, so that's searching. What else might we want to do in our editor? We might want to undo things. So if I type some stuff, for example, and then realize I didn't want it, I can hit Control-X-U, and it'll undo that change. All right, now that's pretty normal. Let's just suppose for a second that I made a bunch of changes. So I do some changes here, blah, 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 some other stuff. And then I go and do some really important stuff, really important, complicated stuff I want to keep. And now I realize all that other stuff I just did, I want to undo it. Maybe this happens in programming. I might make some changes in one function and then go work on some other piece of code and then somehow realize that I messed up that function. Well, if I hit Control and then space, it's going to say mark set and start highlighting a region. And once I've highlighted a region and selected it, I can undo in that region. So if I undo, Control-X-U, it will undo in region, and it will start only undoing the changes in that area of this file and not the later changes that I did somewhere else, which is really nice when you're programming or even editing other things in general. I'm going to come down here. So sometimes I want to move to the beginning of the line. Control-A will do that. Control-E will go to the end of the line. I'm going to take out this line of text. So Control-K cuts an entire line. If I wanted to paste it somewhere else, Control-Y pastes the previous thing that I cut or copied. If I want to copy or cut a region, I can select it. Control-space begins selecting, and then Control-W will cut. Control-Y will paste. If I wanted to copy instead of cutting, I can hit Escape-W and then paste. Now, one of the other really cool features about Emacs is after you paste, you can change back through previous things you've pasted. So immediately after pasting, if I hit Escape-Y, it will unpaste what I pasted and paste in the previous thing. And I can do that again and get back to previous things that I've copied and pasted. So sometimes you copy and paste things and you want to paste not the most recent thing. That's really cool. Okay, I'm just going to revert. Actually, I'm just going to save that. It doesn't matter. The other feature I'm going to show you in this video, which I think is really cool, I'm going to open up this enum example where I've written enum a bunch of things. It has all these things in it. And what I'd like to do is write a function that takes one of these things, like takes this enum and prints out what it is. Now, I just told you how to copy and paste, so I'm going to copy. And while I'm copying, I can actually like search for curly brace and just sort of jump down here without scrolling through the whole thing. So I'm going to copy all that. I'm going to write a function, print thing. It takes enum, a bunch. That name was really long. I'm kind of lazy, so I'm just going to hit escape slash. It's going to complete that name for me. Oops, I need to give that a name. T, switch T. And now, just pasted all those things. And Emacs is telling me what my curly brace matches, even though it's off screen. And it's not lining up right because I don't have any semicolons in there, so Emacs knows something's wrong with the syntax of this. This tells me what I've matched. Also, if I hover on something, it'll match up if they're on screen. Just going to search backwards for this. Now, what I'd like to do is I'd like to take each of these names of enum cases that I just pasted in here, and I'd like to change each of them to look like case, that thing, printf, that thing, break. Now, most editors, you'd have like a tedious 15 minutes of like copy and paste and change, and it'd be really boring. But Emacs has this really cool feature called keyboard macros. So basically, I want to do the same thing to each line. So here's what I'm going to do. I hit Control-X, open parenthesis, and it says defining keyboard macro. And now Emacs is going to remember the sequence of commands I do, and let me replay that sequence of commands. So what I'm going to do is go write twice. I want to write the word case. I want to start highlighting a region to copy, so I hit Control Space. I want to search forwards for a comma, and then I want to go backwards, so I hit left, and then I want to copy, so I'm going to hit Escape W. Now I want to come over here and replace that with a colon, type printf. I'm going to paste that thing, so I hit Control Y. Let's say I want a new line, and break, and then I want to go down a line and to the start of the line with Control A. Then I hit Control X, close print, and it says keyboard macro defined. So that sequence of commands I just did to that line, I can hit Control X E, and it'll do that again to this line. And after I've done that, it says type E to repeat macro. I can just hold down E. Well, on this it makes me repeat it, but on most most terminals, you can just hold it down. And then this one isn't going to quite work because like it doesn't have a comma, but if I just put a comma there, make it look like the others, boom. And now that's syntactically legal. I might put like default printf invalid thing break. But I got Emacs to do all that work for me with keyboard macros. So there's some of the cool features. You'll read about more of them in your readings, and you'll learn a lot of them with practice. One reason Git is so popular amongst professional software developers is the features that it provides for working with others on a large project. Let's suppose that I have my Git repository here, and I want to collaborate with Genevieve.
Not only do I need to get a copy of Drew's code, but we also need to both be able to make changes and merge those changes together easily. Drew's code is on his laptop, and I want to work on it on mine. Since our laptops aren't always available, we'll make another repository on some server we both have access to.
One of us runs git init to set up an empty repository on this server. Then I need to tell Git on my laptop that I want it to work with a remote repository. You can name the remote anything you want. Here I called it XYZ, as our hypothetical server is xyz.duke.edu, and you give it the location of the remote. The only thing this does is make an association with the remote location. Now I run git push, specifying the remote's name, in this case XYZ, and the branch I want, which is called master. By default, the main branch in a Git repository is called master. The set upstream option makes this the default place to push and pull. We aren't going to go into branching, but it's an incredibly useful feature of Git. Now Git will copy not only all my files, but my entire revision history, every commit I've ever made, and the log messages that go with them over to the remote.
Now I want to make a copy of the repository on the remote, so I'm going to use git clone. I specify the location to clone from. This is the same location that Drew specified, but I'm using my own username to authenticate myself. This will create an empty repository on my laptop and create a remote called origin, which is automatically set as the default place to push and pull. Then Git copies all the commits from the remote. Now I write some more code, test it out, and add any new files I created to Git. Then I do git commit. Now my local repository has these changes, but nobody else does.
Including my repository, which doesn't have her changes. In fact, I may not even know that she's done anything.
I want to send these changes to the server, so I run git push, which will copy any new commits to the remote.
Meanwhile, I've been writing some code of my own on this project. So I do git commit and create another commit in my own local repository. Now, I'd like to make my changes visible to Genevieve, so I run git push. However, I run into a problem. When I do git push, I get this error message.
Geez, Drew, that error message is long. You must have really screwed up.
Well, let's take a look at it and see what it says. It says that the remote has work that I do not have locally.
You mean all the code I worked so hard to write, test, and debug?
Maybe I should get that first. In fact, Git suggests exactly that. I should use git pull to get Genevieve's work first. If I run git pull, Git will copy Genevieve's commit to my computer. Then it will merge my work and her work. If we've changed different files or different parts of the same file, Git will handle this process automatically. If we've both made different changes in the same area, Git will tell me that I have to manually figure things out. Now, Git will put Genevieve's commit, as well as a new commit for the merged work, into my repository. Since this is a new commit, Git will ask me to enter a message. The default message says it merged our work, which is fine with me. Now I can try to run git push again. This time, it works just fine and copies my new commits to the server.
And then I can get Drew's latest code by running git pull, which will copy those new commits to my local repository. That's an overview of the basics of working with remotes in Git. Use git pull to get commits from the remote, and use git push to send your own commits to the remote. We talked about this in detail not only because it's incredibly useful in software development, but also because it's how you interact with the grading system in this course. You push your code to a remote, and the grader pulls your code, it grades your submission, then commits your grade.txt file, and pushes it back. You then obtain it with git pull.
At this point, you can write some code in Emacs and save it to a file. But what do you do with that code? First, you need to compile it. This means you need to run a program called a compiler, which translates the code you wrote into actual machine instructions. The compiler will then produce a file which you can execute by typing its name at the command prompt, much like any other program. However, before you can compile the code, you need to add some #include directives. You'll learn more about these and the compilation process later in this lesson. Once you have added any necessary #include directives, you can run the compiler like any other command. The compiler you are going to use is called GCC, and it takes some command line options to specify things like what to call the program it creates and how much it should warn you about code that seems questionable. You will learn more about these things in an upcoming lesson. You will also learn about a tool called Make, which will simplify building large programs with many files and/or a lot of options passed to the compiler. Once the code is compiled, you can run the resulting program. In this example, we instructed GCC to produce a program called hello. We can run it with ./hello. The dot and slash specify that the hello program should be found in the current directory, which we'll also talk more about later. You can see that the program ran and printed its output, hello world. Now that you have seen the basic overview of compiling and running code, let's dive into the details.
In this video, we're going to step through the process of writing code in Emacs, compiling it, and running it. We're going to walk through assignment 4, which is to write, compile, and run a program that prints hello world. So here I am in the practice programming environment, and if I do ls, which you may remember shows me the contents of the directory, I'll see a readme. I'm going to Emacs the readme, and it's going to open up, and it says that basically what I just said, we're going to write a program that will print hello world. And so to do this, I'm going to open a file called hello.c, so I hit Control-X, Control-F, prompts me for the file. I'm going to type hello.c. I need to put my header files at the top. I need to #include them, so I'm going to #include standard io.h for printf. I'm going to #include standard lib.h for exit success. And then I'm going to write main, which returns an int and for now takes no parameters. Later on, we'll learn how to have it take command line arguments in course 4. And we want to print hello world, so I'm going to write printf hello world. And I want it to have a new line at the end, so I'm going to put \n, close my parentheses, put a semicolon. I'm going to put return exit success. I'm going to close my curly braces. And then I'm going to save this file with Control-X, Control-S. And then what I'm going to do is I'm going to suspend Emacs so I can go back to my command prompt. So if I hit Control-Z, I get back to my shell and I can type commands. We can also compile inside of Emacs. We'll show you that later when you learn about make files, and then you don't have to go in and out of Emacs. Sometimes you want to suspend Emacs anyways. So I'm going to do gcc-o hello, which is going to tell it to make a program called hello. I want to give it all of the flags that we give it so that it will be very picky about if I wrote good code. And I want to compile hello.c. Now GCC didn't print anything. That's good. That means it succeeded. If I do ls, I will see this hello there. It's green, which means it's executable, so we can actually run it. So if I type ./hello, it will run and print out hello world. So now I would add hello.c to get. I'm going to remove hello. I don't really like adding binaries to get usually. I'm going to commit, and it's going to prompt me for a message, and I'm going to say that I wrote hello world. Save that and quit, and then I'm going to push, and I'm going to grade. Now I'm going to just note that we did all of this with Emacs suspended. We didn't actually quit Emacs. It's still there. So if I type FG, we'll be back in Emacs where we were. If you're doing this and you suspend Emacs, don't start a whole bunch of copies of Emacs for other things. So if I wanted to keep editing my code, I could do that here, but I've finished this assignment, and I've passed it. And now we would move on to the next assignment, which is going to involve writing some code that prints out squares.
In this example, we're going to plan and write a function that takes one integer n and determines if it is prime. We begin with step 1, working at least one instance by hand. We might start with something like, is 7 prime? And you might just say, yes, I know this, 7 is prime. However, this is not very helpful. Just knowing the answer does not help us develop a step-by-step approach to solving the general problem. Unfortunately, when you already know the answer, it can be hard to see past it, in which case there are two things you could do. First, you could consider how you would convince someone that this is right. That is, if you said 7 is prime, and I said, I don't believe it, what would you do, step by step, to show me that it is? Second, you might think about a harder problem, where you don't just know the answer, to see the step-by-step approach you take. If that problem is too big to work through all the way, you might use the step-by-step approach you begin with to inform how you work through a more manageable size example. As an example of a harder problem, let us consider whether 29,393 is prime. I suspect most of you do not know the answer off the top of your head. We'll start with step 1. I divide it by 2 and get 14,696 remainder 1. Dividing by 3 gives 9,797 remainder 2. Dividing by 4 gives 7,348 remainder 1. Dividing by 5 gives 5,878 remainder 3. Dividing by 6 gives 4,898 remainder 5. Dividing by 7 gives 4,199 remainder 0. Because my number is evenly divisible by 7, I will answer no, 29,393 is not prime. Next, I'll write down exactly what I did, and this involves thinking through my actions and describing the steps to get the answer. I checked if 29,393 mod 2 is 0, that is, if it is evenly divisible by 2. It was not. Then I checked if it was divisible by 3, if mod 3 is equal to 0. It was not. Then I checked whether it was divisible by 4, divisible by 5, divisible by 6, divisible by 7. The answer was yes. When I found it was divisible by 7, I answered no. The next step is generalizing the result of step 2, but we may wish to do multiple instances of steps 1 and 2 first. In this problem in particular, since we have a yes or no question, it may be very useful to do an instance where we get a yes answer before we try to generalize. Now we'll return to our first question. Is 7 prime? Having already thought through how to do it step by step, we may be able to get past our mental roadblock of just knowing the answer. 7 divided by 2 is 3 remainder 1. 7 divided by 3 is 2 remainder 1. 7 divided by 4 is 1 remainder 3. 7 divided by 5 is 1 remainder 2. 7 divided by 6 is 1 remainder 1. So at this point, I'm going to answer yes, 7 is prime. I tried all of the numbers from 2 to 6 and found that 7 is not divisible by any of them. Doing step 2 for this same problem, I'm going to write down that I checked if 7 mod 2 is 0. It is not. Checked if 7 mod 3 is 0. It is not. Checked if 7 mod 4 is 0. Checked if 7 mod 5 is 0. Checked if 7 mod 6 is 0. And after doing all that and verifying that the answer was no for all of them, I answered yes. Now we're ready to generalize our steps. I've written down the result of step 2 for both n equals 29,393 and n equals 7 so that we can look for patterns across both of them. Sometimes it helps us generalize to see multiple instances of the problem solved. The first thing we might notice is that the numbers in these two columns are always n. We check if 29,393 is divisible by 2 through 7, and we check if 7 is divisible by 2 through 6. Logically, it makes sense to always test n for divisibility, so that we can update our steps to reflect this generalization and replace these numbers with n. Next, you might notice that these steps are now repetitive, except for these numbers, which count from 2 to something, and except for our answer, which is sometimes no and sometimes yes. If we get yes, as in n mod 7 is 0, then we immediately answer no, and if we get no, as in all the rest of these checks, we do nothing special. So we can make these steps slightly more general. Check if n mod 2 is 0, if so, answer no. Check if n mod 3 is 0, if so, answer no, and so forth. Each time we check if n is divisible by a number. If it is, we immediately answer no. In the case of n equals 7, after we tried all of these, we answered yes. Here you see counting. The steps are completely repetitive except for these numbers that count. On this side, we count 2, 3, 4, 5, 6, which appears to be from 2 to n minus 1. Typically in computer programming, we count the lower bound as inclusive and the upper bound as exclusive, so we'd call this counting from 2 to n exclusive. On the other side, we seem to be counting from 2 to 8, not including 8, which seems odd. What does 8 have to do with 29,393? If we think about it a little more, we see that we would count beyond this. We just stopped here because we came across something that told us the answer was no. That is, we would otherwise be counting from 2 to n as long as we kept getting n not divisible by the number we're counting. Now we can express this as a repetition of the same step. Count from 2 to n and call each number that you count I. So I is 2, 3, 4, etc. Then we take the step we're repeating and express it in terms of I. Check if n mod I is 0. If so, answer no. On the n equals 7 side, we have the same counting repetition, except for one difference. After we did all this counting, we answered yes. So we're almost done, but these have to look the same to be a general algorithm. If they're different in some way, we need to add conditions. So what about this last step? It turns out it's in there in general after we finish counting, and we haven't answered no. So we can add it to the left side. In the case of 29,393, the step was still there, but we never got to it because we stopped counting when we answered no. Now we're ready for step 4. We have a general algorithm, we think, but we may have generalized incorrectly. It may be that there was something special about the two numbers we picked, and we didn't come across something that made it have other behavior. So we want to test with values we haven't used yet, such as other yes answers like 5 and 13, and other no answers like 4 and 9 to work through this and see if we're getting the right answer. The more values we test, the more confident we will be that this algorithm is correct. We may also have missed some corner cases, numbers for which our algorithm behaves strangely. We might want to try some unusual values, such as 0, 1, 2, or -1. 2 is a good special case because we start counting at 2. 0 and 1 might be special because they're less than 2, so we wouldn't count any numbers. -1 might also be good, since we would count no numbers and immediately answer yes. We do not, however, need to worry about things like 2.75 or the string hello world, because these are the wrong types. We specified that n must be an integer, and the type system in our programming language, like C, is going to enforce this. We won't be able to call this function with any argument that isn't an int. Now that you've tested these out, you've seen that the algorithm gives the correct answer for 5, 13, 9, and 2. However, it gives the incorrect answer for 0, 1, and -1. It won't count any numbers, so it will answer yes, even though these are not prime numbers. To fix our algorithm, we repeat steps 1, 2, 3, and 4 as needed. In this case, there are no primes that are less than or equal to 1, so we add to our algorithm. Check if n is less than or equal to 1. If so, answer no. Otherwise, we do all the other parts of the algorithm. In the next video, we'll show you how to translate this algorithm to code. Now we're ready to translate our steps to code. We'll take our algorithm shown here and write it as comments so that we can translate line by line. We start with a function declaration written around our steps. If you were doing this yourself, you could add the algorithm as comments in your editor without leaving space for code. The first thing we need to do is check if n is less than or equal to 1. We're checking a condition and deciding what to do based on that, so we want an if statement. If n is less than or equal to 1, we want to do something. Otherwise, we want to do everything after it. If so, we want to answer no, and that is a return statement. We want to leave this function immediately since we know our answer and we don't want to do anything else. So we return 0. Recall that 0 means false or no, and non-zero numbers, generally 1, mean true or yes. Next, we want to count from 2 to n and call each number that we count I. Counting corresponds to a for loop. The number we want to count is I, so we're going to declare int I equals 2. We want to count to n exclusive, so we choose the conditional statement I less than n. Also, we're counting by 1, so our increment statement is going to be I++. The body of the loop will be the steps we want to take for each number that we count. The first of those is check if n mod I is equal to 0. This is again an if statement because I want to check a condition and make a decision about what to do next based on the result of that. N mod I write n% I since that is the mod operator. I want to see if it's 0, so I use equals equals. Recall that two equal signs compare for equality. Then I have curly braces around what I want to do if this condition is true. If so, answer no. Is again return 0. We would know our answer immediately is no, so we would return 0 in this case. After all of this, if we finish counting, that is after the body of the for loop, if we haven't returned and left this function, we answer yes. We put return 1. This code would work fine, but we're going to do just a little cleanup. Generally, when we're programming, we don't like capital letters for variables. All capital letters is usually reserved for a constant, so we'll use lowercase n for this variable. Now we have it, a function that will compute whether or not n is prime.
In this video, we're going to show you a really useful Unix tool called diff, which takes two files and compares them and tells you differences in them. You're going to use this in an upcoming assignment and in many other assignments to compare the output your program generates with the output that we've provided for you so that you can see if your output is right. So in this upcoming programming assignment, you're going to write a program which prints out some squares. It takes some command line arguments and prints out a pattern of squares. So if I do ls, I'm going to see that I have some files here called like ants3582.txt, which has this little pattern of squares. And I've already done my assignment and compiled it into this program squares. So if I run squares with 3582, I want the same thing. So I can look at these. They look pretty much right. Now, for big complicated things, it might be really tedious or complicated or hard to look at them and see if they're the same. So what I'd like to do is redirect the output of my program to a file. So rather than printing it to a screen, it writes it to a file. You should have seen that in your readings about Unix. And I'm going to call it like myout.txt. So if I were to cat that file, I now see what's there. But if I were to run diff myout.txt with ants3582, diff says nothing. So that's good. That means that we have exactly the same files. My output matches the expected output. Everything is good. But I've also made a version of this that's messed up called squares broken. So if I run that, so now it looks different. And if I diff myout now with ants3582, it's going to tell me that these are different. Now, this output format from diff may seem a little weird. What this means with the less than sign is these are lines that were in the first file, that is this argument to diff, but not the second one. And these were things that diff found in the second file, this one, that's why it's pointing that way, and not that one. We can get a slightly more readable version of this if I give it -y, which will give me side-by-side output. So it will show me that this and this are lined up, and this little line down the middle means that these are different. Now you might say, but Drew, like, this looks like a blank line and this looks like a blank line. They actually have different amounts of white space on them. We can tell diff to ignore white space and things like that. If we read man diff, remember man tells us all the useful things about any command or library function, and we look for white space. There we go. It's 2 words. We can see that there's a bunch of options for ignoring white space, including -w, which will ignore all white space. So if I didn't want it to treat differences in spacing differently, I can put -w. That's a little dangerous because now it thinks that this is the same as this because they only differ by a space. It thinks this line is in one file, this line is the same as this one. These lines it thinks are the same line but different, meaning it thinks the line's in both files but changed, and it thinks this line appears only in this file. So sometimes it interprets things a little bit weirdly, but it'll do a good job of that. We could use different white space options if we wanted, based on what you need. So we might want to ignore only trailing white space, for example, or something like that. But in this case, we can look at these side by side, see what it thinks is different, and figure out whether we've got the right output or not. Now you have the basics of compiling using GCC. Of course, you want to give it some flags so that it will work hard to identify potential problems in your code. But what if you have a really large program, like one with hundreds of source files and many of thousands of lines of code? You could just tell GCC that you want to compile star.c, all the C files in the current directory. But that would mean you recompile every file, even if you just make one small change somewhere. That would take a lot of time and really harm your productivity. Speaking of which, XKCD, which is one of my favorite web comics, has a great comic about time wasted compiling. You could instead try to manually pick out which files to recompile. This would be tedious and error-prone. If you miss one, you'll end up with strange errors in your program. So what should you do? You should use a tool for building large programs, such as make, which is great not only for building large programs, but for building pretty much anything. For example, all of programming, my textbook, which this course is based on, was built with make. The input to make is a make file, which specifies the targets of your build. That is, what things should make build for you. It also specifies the dependencies, which you can think of as the inputs to build a target. If one of the dependencies changes, then the target needs to be rebuilt. One target might be a dependency of another target, in which case rebuilding the first means that you have to rebuild the second. The make file also specifies the recipes to build a target from the files that it depends on. These are the commands to run to make the target from the files it depends on. To understand dependencies a little better, let's suppose you want to build my program. To build my program, you link 3 object files shown here. This means that my program depends on these 3 files. If any of them get recompiled, we need to relink my program. If abc.o is compiled from abc.c, then there's a depends on relationship between these 2 files too. Likewise, if abc.c includes abc.h, then whenever we change the header file, we would want to recompile the abc.o object file. Likewise, xyz.o might depend on a C file and some header files. We may end up including one header file in many C files as we develop a large project. And finally, main.o depends on main.c and one of our header files. Now, if we change xyz.c, we need to recompile xyz.o, since xyz.o depends on xyz.c. We don't need to recompile any of our other object files. We do, however, need to relink our program, since my program depends on xyz.o. If we change the xyz.h header file, we would need to recompile 2 object files and then relink the program. Fortunately, once we tell make about these dependencies and what commands are needed to build a target, it will figure out which targets need to be rebuilt and run the corresponding commands for us. Okay, you've been compiling programs. We've been talking about make and how it's useful for building larger programs and tracking your dependencies and changes and so forth. And I'm going to show you a little bit of compiling with a make file and so forth. So at the moment, I have here a handful of files and a handful of header files. handful of C files, a handful of header files, and a make file. And this isn't a super big project, but we want a small example. So right now, if I type make, we'll delve into the make file in a second, it's going to compile all of these things and create my program, which doesn't really do anything super interesting. Just compute some math. Now, if I were to open up file1.c and make a change in here, let's say that I realize that this really should be +1 from some testing and debugging that I've been doing or something like that, and then I go to compile again and I do make, you'll notice that this time it only recompiled file1.c to an object file and then relinked the program. This is really nice because it didn't recompile all these things. These are all pretty small files, so they compiled quickly, but in a real big project it might take a while. Okay? And in fact, now that we're dealing with things in Emacs, we may as well not even go back to the command line. We can just compile in Emacs. So if I hit Control-C, Control-V, you'll see at the bottom it says compile command, and it says make-k. So when I hit enter, it actually runs make. -k just says keep going if you run into errors. Try and make as many things as you can so you can see as many errors at once. You don't have to use it. It's the default. It finished with no problems. If I were to have a syntax error, let's say I leave off that semicolon and I compile, it's going to display my errors in Emacs. And in fact, let's make it so that we have a couple errors in here. Now if I go to these errors, it will jump to wherever in the code that error is coming from. So this is on that line. This error message is coming from the make file. It's just telling me it failed to make that thing. This is on that line of code. So this works really nicely. We can just stay in Emacs, move around, and see our errors. In your readings, you'll learn about the details of how to make the make file, starting with a very simple make file and building up to sort of a nice featureful make file that's flexible and lets you add more and more files. But this is how we can use those. In this environment, we just create a file called makefile with whatever we need in there, and then we go from there. Next, you're going to learn about testing and debugging. While these two ideas often go together, they are distinct tasks. Testing is the process of finding bugs in your code. Your goal is to discover inputs to the program for which it does not behave correctly. Once a program has failed one or more test cases, you want to debug it. Debugging is the process of fixing bugs in the program. So what makes a good test case? Many people find this counterintuitive, but a good test case is one that the program fails. Does that seem surprising? Why would we say that a test case is good if a program fails it? Well, remember that the goal of testing is to find the bugs in the program. If your program fails a test case, you've found a bug. Another way to think about why hard test cases are good test cases is to think about exams where you test students instead of test cases for programs. Suppose I had a group of students and I wanted to test their programming skills, maybe to determine who to hire to work on a project with me, or to say if they are ready to go write real software to run important systems. Would this be a good test question? Everyone would get it right, so the students would be happy. But did it really tell me anything about their programming skills? This question gives me no information about whether students actually can program or not. Likewise, if your test case is so easy that it won't identify problems in code that can't do what it is supposed to, it isn't terribly useful in figuring out if your program is right. So when you are testing, you want to come up with difficult test cases. This is often psychologically difficult because you want your code to work. You don't want to show that your program is broken, but you would rather find that your code is broken now rather than after it is controlling a self-driving car or flying an airplane and something goes wrong with it. So the upcoming lesson, you're going to learn a lot about testing and debugging. You're going to do assignments which are focused on developing test cases for programs where we have made many broken implementations. We'll also note that testing and debugging are often given too little coverage in programming classes. And one thing I keep hearing from people I know in industry is, teach more testing.
As we talk about testing, let's take a moment to look back at the 7 steps. Recall that testing is step 6, after you have devised your algorithm and translated it into code. At this point, many programmers, even experienced programmers, are eager to finish the problem. Sometimes this eagerness leads programmers to give testing much less emphasis than it requires, writing only a few test cases and saying their code works. However, testing code is really important and should not be given such cursory treatment. Let's look back to early steps for a second. In step 1, you already worked through instances of the problem by hand. This means that you came up with the right output for particular inputs. We could use these inputs and outputs as test cases, especially as we have worked out the correct answer to compare to. In fact, if we take this approach, we might apply the ideas of black box testing, coming up with test cases for what we think will be difficult at step 1. That is, we might think up difficult cases for the problem before we even begin, and use those in step 1. Why would we want to do this? Not only does it set us up to have a nice set of test cases when we get to step 6, but the earlier we think through these difficult cases, the less we have to change later. If we get them all right the first time, that is best. This idea of writing test cases first actually has a name, test-driven development, and is used in industry. This process meshes naturally with the 7-step method, as developing those test cases works well for step 1. We will have you use this idea for some assignments as we progress through this course, writing test cases first, then beginning to develop your code.
Testing is great. You're going to test your code like crazy and write lots of hard test cases so you can identify problems with your code. But testing has its limitations. For one thing, you can never write enough test cases to guarantee that your code is correct. Even if you write 1,000,000 test cases, which are all really clever and difficult, there might be that 1,000,001st test case that your code would fail. Also, testing will only tell you if your code has the right functional behavior, if it produces the right output. It won't tell you if you wrote readable code, used good variable names, wrote appropriate documentation, or a variety of other stylistic concerns. These may not sound so important now as you focus on trying to get your code to work, but when you are working on large projects with many team members that last for months or years, these concerns become very important. So another way that you can help ensure high code quality is a code review. Sit down with a colleague. In a work environment, this would be someone on your team. Go through your code with them line by line. Explain what each line does and why it does that. You might even draw a diagram of the execution of your code as you go to make sure you are both on exactly the same page about what is happening in your code. As you do this, your colleague asks you questions and identifies potential problems. They might point out cases that they think you didn't consider. If you think you did consider them, you can have a discussion about how your code handles that case and how you can make that clearer to future readers of the code. They might also point out areas where your code could use better documentation or any of the other readability concerns they see. And of course, they might see other potential problems, ranging from security vulnerabilities to poorly phrased messages printed to the user. A code review can take a variety of forms, not just the one we talked about. It may be that the case that your colleague reviews your code without you there to explain it. In fact, in many companies, someone must peer review your code before it gets pushed to certain branches like master of the Git repository. This ensures that certain quality guidelines are met with all code that is integrated into the main branch of development. The review could even happen while the code is being written, as happens in pair programming. In pair programming, one partner drives, meaning they write the code, while the other partner navigates, meaning they watch what the driver is doing, look for problems, and think about the bigger picture of where the code is going. We aren't going to go deeply into these topics, but we did want to mention them to you. If you go on to take more classes on software engineering, you will almost certainly learn much more about code reviews.
In this video, I'm going to do an example of finding bugs with Valgrind. Drew has given me the program Broken, compiled from broken.c, and he'd like some help debugging it. Let's go see what we have. Let's see, in this program, we have a function quadratic that the comment tells me computes a times x squared plus b times x plus c. It takes 4 parameters, a, b, c, and x. Then it computes a total. Later in main, We compute quadratic on two different sets of inputs, and then we print the output. Let's see what that does. Here we have 1 times 3 squared, so 9 minus 2 times 3, that's 6, so 3 plus 0.5 equals 3.5. That checks out. Next line, negative 1 times 2 squared, negative 4 plus 3 times 2, that's 6, so 2 plus 1, uh-oh, that should be 3. We can use Valgrind to get some more information about this problem. Run Valgrind, and then run the program the way you normally would. Error summary, 156 errors from 52 contexts. The program wasn't even 156 lines long. Luckily, sometimes by treating the first error, you can fix errors down the line. So let's find the first error. Here. Conditional jump or move depends on uninitialized values. The key word here is uninitialized values, and it tells us that this happens when we're calling printf. And if we go down the line, there's an error somewhere in our program, somewhere where we call main. We can get a little bit more information about exactly where this happens by running Valgrind with this option, track origins equals yes. And now let's return to our first error. All right, here it still says uninitialized values, but then we have more information. Uninitialized value was created by a stack allocation at an address, which is the address of quadratic on line 5. So let's go to line 5 in the program and see what we can find out. Line 5 is where we declare the function, but that's the address Valgrind knows because that's when the compiler created the boxes. And then on line 6, we declare a variable total. And then on line 7, we do total plus equals, there it is. We are adding to a value that we haven't initialized yet. So let's try initializing total to 0 and see if that fixes it. First line still equals 3.5, good. The next line should equal negative 4 plus 6, so 2 plus 1, which is 3, and it does. So that's good. Let's run Valgrind again to make sure. This time we see error summary, 0 errors from 0 contexts, and that's what we want to see at this point in the specialization. In later courses, you will also be interested in this information. All heap blocks were freed, no leaks are possible. Now note that for this particular problem, if we had compiled with warnings, such as WALL, and now let's go re-break our program. So go back and leave total uninitialized again. This time when we compile, we get a warning. Total is used uninitialized in this function. And then it gives you the line number of the place where you use total uninitialized. And that would be helpful information. In this case, the compiler can check our mistake, but in some cases, the compiler will miss things that Valgrind will catch. Drew has given me a program called Rotate, and he told me there's a bug in it. So let's look at the program and see what it's supposed to do, and then see if we can find the bug. Here in rotate.c, let's look at the main. Main calls test rotate, and what this program is supposed to do is take a point such as 1, 0, rotate it by an angle such as 90, and then see what point is the output. Here in test rotate, we're calling it with 1, 0, and 90, so we expect the rotated point to be 0, 1. And the function test rotate will let us know if we're getting the output we expect. So let's look at test rotate. It takes an x and y value, a number of degrees to rotate it by, and then compares it to the expected value. Here we have two assert statements. This one that compares the x value to what's expected, and this one that compares the y value to what's expected. And this function calls rotate with a point and a number of degrees. So let's look at this function rotate. Here it does the work of the rotation by calling these trig functions cosine and sine that are included in the header math.h. So let's run this program and see what the bug might be. Rotating 1, 0 by 90 degrees, that was our first test case. Assertion failed, and the assertion that failed concerns the y values. So we're having trouble transforming the y value to get the one we expect. Back in Emacs, we can run the debugger to see what the values are in this program as it runs, and see if we can find where it's doing something we don't expect. So I'll do meta x gdb, run it default, and once you start the program, it'll stop just after it enters main. And in this program, there's probably no problem in main. We're just calling test rotate. In test rotate, the work is really being done by the function rotate, and we can see that 2 lines later, this assert here is what's failing. So somewhere in this function rotate, we're probably doing something we don't expect. So one way to investigate that is to set a breakpoint just inside the function rotate. You can also set a breakpoint at a line number, but here I know which function I want to look at. And then I'll continue running. Change buffers. I want to look at the program. Okay, so here I've set a breakpoint on the line just inside the function rotate, and I'm about to execute this command that changes p.x and rotates it by 90 degrees. So one thing I can do, I'm very interested in the values of p.x and p.y, so one thing I can do is display their values, and that way each time I advance the code, it'll tell me what the values of those are, and I can do the same thing for p.y. 1, 0, those are the input values. So at this point in the program, that's what I expect. So I will step, and I've stepped into sine. That's not what I meant to do. So if you enter a function that's not useful to you, you can finish and go to the end of that function, and then I will advance to the next line. So now the values of p.x and p.y have changed. P.x is something times 10 to the negative 17th, very, very small, so close to 0. And we're expecting the output to be 0, 1. So that value of p.x makes sense. We're okay with that. Advancing past the next line, and we get a value for p.y that's also very small. That's not what we expect. We're hoping to get the point 0, 1 out of this. So let's see why this calculation on p.y might not be giving us the answer we want. The input value of p.x is 1, sine of 90 is 1, so that part should be 1, plus input value of p.y is 0, times the cosine of 90 is 0. So this line should say 1 plus 0, but somehow it's giving us the answer 0 instead. Can you figure out why? Here we're using p.x, but we're expecting it to be the value we had on input, 1. However, we've changed its value on the previous line. So how can we change that? We'd like to preserve the input values of x and y. And one way to do this is to create a new point t called answer, and then we will instead assign values to the answers x and y, and then we will return our answer. So let's save that and compile. And then And let's run GDB again. We're stopping at that same breakpoint. Once again, let's display p.x and p.y. They're 1, 0 on input. That's what we expect. Advance to the next line. p.y and p.x are unchanged. That's the behavior we want. Let's print the value we just assigned answer.x. Close to 0. Good. Advance it again. And then print the value of answer.y. 1. That's also what we expect. So I think we fixed our program. Let's go ahead and clear the breakpoint in this function and run it until the end. So here's the output from our program. It's gone through all of these test cases, rotating 1, 0 by 90 and got 0, 1. That's what we expect. Rotating 0, 1 by 90 and getting negative 1, 0. Also what we expect. You could do some of these in your head and make sure they're right, but the important thing is that none of our assert statements failed. So it looks like we fixed our program, and we can quit the debugger.
Hi, I'm Nisar Agdabi, and I'm a master's student in the Electrical and Computer Engineering department at Duke University. My advice to programmers is to keep a level head and not get discouraged. Programming is a brand new skill, and it's not very easy to a certain right way. So I would encourage you to just keep going and stay motivated. My favorite programming project was building a scientific calculator. So what I really liked about this project was the fact that it really took for granted what a calculator does and how quickly some of the operations are done when you're just using a basic calculator. When I was actually programming it myself, I realized that an operation where we just multiply really large numbers, while that might be instantaneous when I'm typing into a calculator, it's actually a lot more, it's a lot slower than you'd expect when you're programming it out. So what I really enjoyed was just being able to figure out how exactly to speed up that computation, and that took a lot of algorithm work and just problem solving in general. So my advice for people who want to work in software engineering is just to stay focused and keep programming. A lot of companies really like when you take your own initiative to build your own projects, because that shows that you put in the effort to build things on your own and you really understood something completely in order to get it to work. My advice for students who are taking this course is definitely follow the strategies and the tips that they offer. When I took this course, I definitely was resistant in accepting the methodology that this course kind of recommended. But I would just say that the sooner that you accept that that's one of the better ways to go about it, the better off you will be, and it'll definitely make you a better programmer in the long run.
And here's the flop. Those two spades and possible inside straight draw really helped Genevieve, with no help for Drew. Her odds went 32% to 55%. Drew has bet, and Genevieve called. Here's the turn. The king of spades. Drew now has 3 kings, and Genevieve has a straight. Drew needs a king, jack, 9, or a red 10, giving him only a 21% chance here.
Hit me. Ow, what was that for?
The peanut butter and jelly video. And besides, this is poker, not blackjack. Are you betting or checking?
I really wish I could see those probabilities that they put over there in the corner of the screen.
Well, that would take all the fun out of the game, wouldn't it?
Yeah, probably. But hey, you know what would make a great project for our Coursera learners?
It better not be teaching you to play poker.
No. They could write a program that reads in a description of the poker hands and does a Monte Carlo simulation to determine the odds of each hand winning. Genevieve and I are playing poker, and you all can see the odds of each of us winning the hand based on what cards we each have. How does this get calculated? When there is only one unknown card, you could pretty reasonably work it out by hand. But if there were many unknown cards, it could get complicated quickly. Wouldn't it be great to write a program that could figure this out for us? That's what you are going to do with part of the project at the end of each course. To do this, we'll need to describe the hands in a way that is easy for the computer to work with. Here's the poker table from my perspective. In this variant of poker, which is called Texas Hold'em, these 7 cards are my hand. If you don't know how to play poker, that's okay. We'll explain the rules you need to implement this program. When all the cards are played, I'll pick the best 5 of my 7 cards and say what poker hand they make. At the moment, I have 3 kings. We can represent this in a way that is easy to work with by describing each card with 2 letters, one for the rank and one for the suit. Here, I've described my 2 pocket cards, the ones that are just mine, with KH for the King of Hearts and KC for the King of Clubs. I've described the known common cards similarly. The first 3 are called the flop, and the 4th one is called the turn. The 5th card, which is called the river, is unknown, so I've represented it with a question mark and a number, in this case 2. Everywhere that question mark 2 appears in this hand description will be the same card, which will be different from question mark 0 and question mark 1. Genevieve's hand is made up of these 7 cards, her 2 pocket cards, and the 5 common cards in the middle. Since I don't know what her pocket cards are, I've represented them with question mark 0 and 1. She also has the same description of the flop and turn, since we share those, and also has question mark 2 for the river, since we will share that card once it's dealt. You'll learn how to read input from files, as well as how to dynamically allocate the memory to hold any number of hands that your program is working with in Course 4. Until then, we'll provide some compiled object files that will read the input for you. We can use this idea to describe other situations. Here are our hands before the flop is dealt. I know my 2 pocket cards, but no others. Question mark 2 through 6 represent the common cards, which are as yet unknown, but will be the same in both hands. However, for the spectators and announcers, all the pocket cards are known. Having more information gives you a different calculation of the probabilities of the hands. Genevieve's hand is actually really good, so her odds of winning are better given what her hand actually is than if we assume it is a random hand. Our input representation is flexible enough that we can represent many other common poker variations. For example, 7-card stud has no shared cards, and some that are dealt face down and some dealt face up. So that's how we'll describe the situation in a poker hand. But how will you actually go about calculating the odds? You could make your program consider every possible combination of cards. If you have 4 known cards and 5 unknown cards, as would be the case if we can see 2 players' hands and have 5 cards yet to deal, you end up with about 205 million combinations. That's not so bad as computers go. We could do it in a matter of minutes, but we'd like to be faster than that. Could we work out the formulas for every case based on the principles of probability and combinatorics? Maybe, but that would be a lot of work, especially given how many cases there are and how much these depend on what other cards each other player has. Instead, what we are going to do is a Monte Carlo simulation. So what is a Monte Carlo simulation? You will draw a large number of random hands for the unknown cards and see who wins, and count up how many times each of the players wins the hand, and use those numbers as estimates for the probability of each player winning. If you do this for a large enough number of random draws, your answer will be very accurate. 100,000 random draws is pretty fast and gives estimates that are quite good. The idea of Monte Carlo simulation is not just limited to poker or card games, but is a broadly applicable technique whenever determining the exact answer is incredibly complicated or computationally difficult. Let's head back to our poker game and see how it finishes.
And here's the river. 10 of spades. Wow. Genevieve drew the straight flush, but Drew probably thinks his hand is good with a full house.
All in.
Call.
Full house.
Straight. Blush.
And Genevieve wins the $25 million pot. What a game. Did I say million? I meant 25.
Since this project spans multiple courses, we are going to give you the roadmap for the whole project now so you can see where things are going. In this course, you're going to work on some code related to struct card T, which you will use to represent cards. You'll write some functions that print cards, create cards from either their letter pairs or an integer, and use assert to check if a card is valid. In course 3, you will write some functions that work with a deck of cards. For example, you'll write a function that randomly shuffles the deck, which will be useful for the Monte Carlo simulation since you need to draw many random hands. You're also going to write the code that figures out what poker hand a set of cards makes. Is it a pair, a straight, a full house? Once you have done that, you can compare two hands to figure out which one wins. There are a few things that can be kind of tricky about evaluating a poker hand. It would be great to have test cases before you start writing all that code. Since we cover testing in this course, we're going to have you develop test cases for the hand evaluation code now. You can do this without knowing how to implement the evaluation code yet, and we'll give you broken implementations to run your test cases against as you have done in other assignments. In course 4, you will finish the project. You're going to write the code to read input files, which you will learn how to do in that course. You'll also handle unknown cards, which we represent as $0, $1, etc. Finally, you'll put it all together, writing main to call all the other functions you wrote and print out the results. This project will bring together most of the major concepts from the entire specialization and give you a chance to showcase your newly learned programming skills. Hello, and welcome to Pointers, Arrays, and Recursion, the third course in our specialization, Introduction to Programming in C. From the first two courses, you've gotten the basics of developing algorithms, C programming, and the tools you need to compile and run your program. Now, it is time to delve into the topics that will let you work with sequences of data, enabling you to solve a much wider range of problems. First, we're going to talk about pointers, which specify the location of other data. We'll start with some of the basic mechanics and concepts before we proceed to their various uses. One important use of pointers is arrays, which represent sequences of data. Remember our closest point algorithm from course 1? Once you've learned about arrays, you'll be ready to translate this algorithm into code. Of course, you'll also be able to use arrays to solve a wide variety of other problems. After you master arrays, you'll learn about strings. You've used some string literals, but we haven't delved deeply into the details of manipulating or computing on strings. Strings are basically arrays of characters, so you'll be ready to learn all about them at this point. You'll also learn about multidimensional arrays. Two-dimensional arrays, for example, allow you to represent matrices of data, and you'll be able to work with arrays of higher dimensions if you have problems that call for it. We'll wrap this course up by talking about recursion. Recursion is another way to think about problems, where you express the solution to a complex instance of the problem in terms of the solution to a simpler instance of the same problem. There are many problems that lend themselves naturally to recursive solutions, so we want to be sure you have this in your programming skill set. So, let's delve right in.
To help you see the power of pointers, we are going to show you a piece of code that is broken without pointers. After we introduce the mechanics of pointers, we will revisit this code and see how it can work correctly with pointers. In this example, a misguided C programmer has attempted to write a function to swap two values, which you can see at the top of the example. What does this function actually do? You could figure that out on your own, since there is nothing new going on here, but let's see it explicitly. As always, we start at the beginning of main. We declare A and initialize it to 3, and then we declare B and initialize it to 4. Next, we're going to call swap, passing in A and B as parameters. We make a frame for swap, pass 3 for its parameter x, and pass 4 for its parameter y. We note that we will return to this line of code when swap returns, and move the execution arrow into swap, right before the first line of code. All of this is just the rules for calling a function that you have learned since course 1. Next, we declare temp and initialize it to x, which is 3. We then assign x equals y, so we set the value of x to 4. Last, we assign y equals temp, so we set the value of y to 3. Now we're at the end of swap, so we are ready to return. We will return to the place we called it in main, which we have noted in the frame, and destroy swap's frame. Again, there is nothing new here. These are just the rules for functions returning that you learned in Course 1. Then we print out that a is 3 and b is 4, and then the program exits. Now, notice that a and b both started out as 3 and 4 respectively, and ended up with those same values. The swap function did not really do anything to them. This result makes sense given the rules of C. The swap function was only able to operate on the copies of its own frame. It could not affect the values in main's frame. So what are pointers going to let us do differently? We'll have variables which will give us the location of other data, even if it is in a different frame. We can then affect that data through the pointer. This is just one use of pointers. We will see others once we have developed the basics.
In this video, we're going to step through some code that uses pointers to show you how to best draw diagrams to understand what is happening in a line-by-line fashion. The first line of code declares a variable x and gives it an initial value of 3. The next line of code declares a variable p that is of type integer pointer. It does not yet initialize it, so in the beginning we have a box, but we don't yet know what's in the value. But we do know that the box is called p. The next line of code will initialize the value of p to have the value of the address of x. When you see an assignment like this, it's important to begin by looking at the left side first and then look at the right side. Looking at the left side, we can see that the value is going to be placed into the variable p. When we look on the right side of the assignment statement, we see that the value we're going to place is the address of x. So when we execute this line, we're going to change the variable p to now have an arrow that points to x. On the next line, on the left side, we see the value that p points to, which is actually the variable x. We're going to set that to have the value on the right side, which is 4. When we execute this line of code, we're going to go to that which p points to and change that to have the value 4. The next line of code declares a variable y, and the value it's initialized to is the value p points to, in this case 4. When we execute this line of code, we're going to create a new box named y and give it the value 4. The next line is going to declare a variable of type integer pointer called q, and we're going to give it an initial value of the address of y. That means we're going to create a new box called q, and it's going to have an arrow in it that points to y. The next line's a little bit tricky. On the left, we're going to be storing the value we create into that which q points to, namely the box for y. And the value that we're going to store there is that which p points to, which is 4, plus 1. So when we execute this line of code, we're going to take the value p points to, which is 4, add 1 to it, which is 5, and store that at the location q points to, namely the variable y. The final line of code we have simply gives the value of p to the variable q. Q is the receiving value, and the value it's going to get is the value p has, which has an arrow. So when we execute this line of code, we're going to replace the value of q with an arrow that points to the thing p points to.
In this video, we're going to examine and step through a swap function that was written with pointers. Previously, we looked at a swap function that was written without pointers that didn't actually work. This one does, and it's been written slightly differently. First, let's examine the differences. The first thing you'll notice is that swap takes 2 arguments, x and y, which are pointers to integers. You'll see here that we have written an int star, then a space, then an x, and an int star, then a space, and then a y. You could also write it in the following way, with the x right next to the star. Both of these are correct, and you'll see both when you look at C code. Now, x and y are pointers to integers, so as we access the values of the integers that x and y point to in the code inside swap, we're going to have to dereference x and y, and so that's why we'll see these stars in front of x and y throughout the code. The final difference is how you call this function. In the main, instead of passing in a and b, we now have to pass in the address of a and the address of b. So let's step through this function. We begin in the main. We have a variable a and a variable b that have initial values 3 and 4. Now when we call the swap function, instead of passing in 3 and 4 as we did in the previous version of this function, we now need to pass in the address of a and the address of b. So we're going to create variables x and y, and x will point back to a, and y will point back to b. Let's step into the function. We're going to mark the call site location 1 and hop into the swap function. Inside of swap, we're going to make a new variable called temp, and that's where we're going to temporarily store the value that x points to, which is the value of a, which is 3. Now we can take the value that y points to, which is the value of b, or 4, and store that in the value that x points to, namely the variable a. Finally, we're going to take the temporary variable 3 and store that into the integer that y points to, which is the variable b. When we step out of the function, we see that our original variables a and b have indeed been swapped. So when we execute the print statement, we now have a equals 4 and b equals 3, which is what we were expecting to have from a correctly working swap function.
In this video, we're going to revisit our swap function, paying special attention to a few things that happen at the hardware level. Recall that memory is divided into different sections that have different purposes. In this video, because our function doesn't actually use the heap or static data, we're only going to be looking at what's happening in the stack and what's happening in the code section of memory. The first thing we'll do is imagine what the code might look like in memory. What I've done here is assume that each instruction in the program takes up exactly 4 bytes. So you'll see that each of these instruction blocks is 4 away from the next. Now, whether this is exactly accurate or not depends a lot on the machine the program is running on. You can think of this as a representative drawing. You'll notice that because memory's addresses increase going upwards, the first instruction from main, where a is being set to 3, is actually at the bottom of memory. And you always move to a higher instruction in memory as you progress through the program. At the top of memory, we have our stack, where we store all of the local variables that our program needs. So let's show you what the stack might look like here. Previously, in our conceptual drawings, we've always shown the stack frames as separate boxes, each with their own label, which was the name of the function that we were in at the time. Here, with a more hardware-centric view of memory, we're going to show the stack as it really is, which is one contiguous stretch of memory that just moves from one stack frame to the next. I'm going to use 2 different colors to highlight the sections of the stack frame for the functions main and swap. Here, the stack frame for main is highlighted in blue, and the stack frame for swap is highlighted in purple. There's another slight difference in the way stack frames are built in this video versus the way we've been showing the stack frames in previous conceptual videos. We're going to put the parameters in the stack frame for the caller instead of the called function, which matches more closely with how things happen in the hardware. We can begin executing our program now, and we'll execute the first instruction, setting the value of a to be 3. The next instruction sets the value of b to be 4. The next thing we want to do is call our swap function, and to do this we need to prepare its 2 arguments. The first argument is the address of a, so we look in memory to see what the address of a is. In this case, it's FFFC. So we store this value on the stack in the location for the parameter x in the swap function. The next argument to swap is the address of b. So we look in memory to find the address of b, FFF8. And we store that on the stack in the corresponding location. Now, we're almost ready to call our swap function. In previous videos, we would often mark a call site location with a little numbered circle, in this case a 1. We're going to be a little more explicit about how this works now that we have a better understanding of how pointers work and how code sits in memory. In fact, the last box in our stack frame is going to be dedicated to what's called the return address. What the return address tells us is what is the next instruction we should execute when we finish executing the swap function. In this case, the next thing we should execute is the line of code in which we call printf. This is located at address 4008 in memory, so we store the address 4008 for the return address, and this will tell us what to execute next when we're finished executing our swap function. Now, we can go in and execute our swap function. Recall that the swap function now has its own stack frame, shown here as a purple box, that holds only one variable. The first line of code is going to take the thing that x points to and store that in the variable temp. If we look at x on the stack, we can see it has the value fffc, which is pointing to the value 3 in memory, which is the variable a. So we're going to take 3 and store it in our temp variable. The next instruction is a little more complicated. We need to figure out both the L value and the R value of this assignment. On the left, we have the thing that x is pointing to. So once again, let's go see what x is, the address FFFC. It's pointing to the box with the address FFFC, and this is the box whose value will be changed when we execute the assignment statement. Now let's take a look at the R value, the thing that y is pointing to. Y is FFF8, and it's pointing to a box with 4 in it. So what we're going to do is take the value 4 and store it in the box with the address FFFC, namely the variable a. And now, our final line of code will finish up the swap function for us. In this case, the L value is that which y is pointing to. So if we look at y, it has value FFF8. So we're going to change the box whose address is FFF8, namely the box B. What value do we store into this box? The value of temp, which is 3. So we store 3 into the box with address FFF8. Now we've completed the entire swap function. At this point, we no longer need our stack frame for swap. So now, the only stack frame we have is the blue stack frame for main. At the bottom of this stack frame, we have a pointer that tells us the next line of code we should execute after returning from the swap function. So we're going to do exactly that. We're going to move our execution arrow to the code that has address 4008, and now we would execute the rest of the code for the rest of main.
In this video, we're going to look at an example of a function that sums the elements of an array and uses pointer manipulation to access those elements. As always, we begin in main. The first thing we're going to do is declare and initialize an array of 4 elements. We put them in main's frame with 4 boxes, one that holds 4, one that holds 6, one that holds 8, and one that holds 3. Now we call the function SUMArray, passing in data, which is a pointer to that array, and 4 as the number of elements. Inside SUMArray, we declare a variable answer, which equals 0, and an int star pointer, which points at the same place as the array parameter passed in. Notice we have 3 arrows, all pointing at the beginning of this array. Now we're going to begin a for loop. We go inside that and have I equals 0. We're going to say answer plus equals star pointer. Star pointer is the box pointed to by pointer, which is this int here, 4. So we're going to do 0 plus 4 is 4, and change answer to be 4. Now we're going to increment pointer, doing a little bit of pointer arithmetic, which is going to make pointer point at the next box in the array, 1 int later. We go around our for loop again, I is now 1, and we go inside. Star pointer is now the box with 6 in it, so answer is 4 plus 6, which is 10. We increment pointer again, pointing it at the next box for an int, and we go through our loop again. Star pointer is 8, 10 plus 8 is 18, and we increment pointer. We enter the loop again. Answer is 18 plus 3, which is 21. We increment pointer to be something. It's past the bounds of data, and we might wonder if this is a problem. Well, this is only a problem if we dereference pointer, because we wouldn't actually know which box it's pointing at. It could be pointing at sum. It could be pointing at the return address for main. It could be pointing at the return address for SUMArray. It could be pointing at anything, including something that is not actually a box we've drawn here. Maybe just some other space where the compiler needed to put things in memory. It's okay to have an arrow pointing here past the bounds of the array, but we should not say star pointer while we do that. In this case, we've just finished our for loop, so it's not going to matter because we're going to return our answer, 21, back to main and destroy SUMArray's frame, so that variable and pointer are going to go away without us ever having dereferenced it. We print our answer, which is 21, and we return.
In this video, we're going to look at another example of a function that sums the elements of an array. In the previous video, we used pointer arithmetic to access the array elements. However, in this video, we're going to use indexing instead of an explicit pointer. We begin in much the same way, declaring and initializing the array data, and calling the SUMArray function. We pass in data, which points at the first element of the array, and 4 as the number of elements. We declare and initialize answer to 0, and we begin a for loop. I is 0, and we are going to take answer plus equals array at I. That is, array square bracket 0, which would be the first element of array. So we add 4 to answer, just like we did in the previous video. We go around the loop another time, incrementing I, so it is now 1. Then we're going to do answer plus equals array at I, which is the box with 6. So answer is 4 plus 6, which is 10. We go around the loop again, incrementing I to 2. Array square bracket I is array at 2, which is the box with 8. So we add 8 to answer for 18. We go around the loop one more time. Array square bracket I is the box with 3, so we add 3 to answer. Incrementing I again, we see we are finished with our loop. Then we return our answer, 21, back to main and destroy SUMArray's frame, so the parameters and variables in it are going to go away. We print our answer, which is 21, and we return.
Now we are going to work through the problem of finding the index of the largest element in an array. As always, we will start by working an instance of the problem ourselves. Looking at this array, we see that 99 is the largest element, and it is at index 2. This is a problem where we may get stuck trying to figure out what we did because we just saw the answer. What if instead we had a 1,000,000 element array? We can't even draw that in this video, so we can only see the first few elements here. How would we find the answer here? Well, we might start by looking at the first element, which is 16, and then looking at the next element, which is 12. 16 is bigger than 12, so let's move on to the next element, which is 43, and compare it to 16. 43 is larger than 16, so we want to compare it to the later values until we find something even bigger. We can continue this process, comparing each element to the largest element that we have seen so far, and when we find something larger, updating our information about what is largest. When we reach the end of the array, we'll have found the largest element, no matter how big the array is. We don't want to write down all those steps for such a huge array, so let's go back and apply the step-by-step approach to our smaller problem instance. We will want to keep track of the largest so far and where we currently are in the array, and work through comparing element by element and updating our largest so far as we go through the array. So now let's go to step 2 and write down exactly what we just did. We started by guessing that the index 0 might be the largest element. Then we started our element by element comparison at index 1. We compared 24 to 17 and found that 24 was larger. So we updated our guess for the largest element to 24, found at index 1. Then we compared 99 to 24. 99 was bigger than 24, so we again updated the largest element we had found so far. Next, we compared 3 to 99. 3 is smaller than 99, so there was no need to update the largest element. There were no more elements in the array, so we gave 2 as our final answer. Next, we need to generalize these steps. Why is this 0? We are always going to start at index 0, no matter what array we are using. However, we should think about the possibility that we might have an empty array. This is our current guess for the largest index. We will call it largest index. Next, we might think about why this number is 24, and why this number is 99, and this one is 3. The answer to these questions is that these were elements 1, 2, and 3 of the array. We can generalize this algorithm by replacing those specific numbers with their locations in the array. Next, we should think about why we are comparing the numbers in the array to the numbers 17, 24, and 99 respectively. These numbers also come from data in the array, at elements 0, 1, and 2. So we can make the algorithm a bit more general like this. But in doing so, we have introduced another set of specific numbers that we need to think about. Why are these indices 0, 1, and 2? Our first guess might be that we are counting, but are we really counting? We have to be a little bit careful here. To see why, let's go back to our larger, more complicated example. In this example, we first compared element 1 to element 0. Then we compared element 2 to element 0. Here, we found that element 2 was larger, so we updated largest index, and then we compared element 3 to element 2. The index of the second item in our comparison is not counting, since we used 0, then 0 again, then 2. Next, we compare element 4 to element 2, and then 5 to 2, at which point we once again update our largest index. We now compare elements 6, 7, and 8 to element 5, and then once again find a new larger item at element 8. At this point, I've figured out what the pattern is. Think about it for a moment and see if you know what we are doing. The pattern is that we are always comparing the current element with the array largest index, so we can update our algorithm to reflect this understanding. These steps are looking pretty repetitive. The only thing that does not repeat exactly is that sometimes we update the largest index and sometimes we do not. We need to figure out under what conditions we update largest index. We are doing this when the current element is larger than the largest element we have seen so far. With that in mind, we can make these steps completely repetitive, so that we can then express this repetition in terms of counting. We won't always give an answer of 2, so we should think for a moment as to where this value came from, and realize that it was the value of largest index in our example. Now our algorithm says to give largest index as the answer in the general case. This algorithm is pretty general, but we might think about one corner case. What if there are no elements in the array? We would need to handle that case and give back an answer that indicates no valid answer. We will choose -1 as our answer, since it is not a valid index in an array. Next, we would want to test this algorithm. We'll leave that up to you. Try it out on a few inputs and convince yourself that it is correct before we proceed to step 5. Here, we've declared our function, findLargestIndex, and written our algorithm as comments inside the code. The first line describes 2 steps, but they should be quite familiar now. An if statement with a return statement inside of it. Next, we declare and initialize largest index. Then we have a for loop to count with, and an if statement to compare array elements to each other. If the condition is true, we update largest index to be I. And at the very end, we return largest index. And we're done.
In the previous video, we translated our closest point algorithm to code. In this video, we step through this code to make sure it works. Let's assume that before this function was called, we had an array of points somewhere in memory. Here we take a subset of our previous set S and just test our code on an array of 4 points, each a struct with an X and Y value. Let us also assume that the calling function has passed in a pointer to this array of points, its size, and a point P. Therefore, we have S, a pointer to the base value of our array of points, N with the value 4, and point P with values 1 and -1. We have our execution arrow at the start of closest point, and we can begin. N has the value 4, so we do not return null. Next, we're going to call the function computeDistance on the 0th element of the array S and point P, and we're going to store the result of that in a new variable called bestDistance. In this case, the distance is 8.06. We're also going to make a note of the fact that this distance corresponds to our best choice, which is the 0th element of the array. So best choice is initialized to be a pointer to S at 0. Now we're going to go into the for loop and continue to look through the rest of set S, seeing if we find a point that's closer than that 0th point in the array. We go inside the for loop, and we have I with the value 1, and we're going to now compute the distance of S at I, which in this case is S at 1, and point P. We compute this distance and we're going to store that in current distance. For this iteration, current distance is 7.07. We want to test whether the current distance of 7.07 is less than the best distance of 8.06. It is, so we step into the if clause. We're going to update our best choice pointer from s at 0 to be s at 1, and we're going to update our best distance from 8.06 to 7.07. We've reached the end of our for loop, so we iterate. Now I has the value 2, so we're computing the distance from s at 2 to point P, which is 7.81. Once again, we test whether current distance is less than best distance. In this case, it is not, so we pass by the if clause and iterate one more time where I has the value 3. In our final computation, we're computing the distance between s at 3 and point P. The distance is 5.66. We compare the current distance to the best distance, and 5.66 is smaller, so we enter the if clause and assign a new best choice of s at 3. Our corresponding new best distance is 5.66. We increment I to have the value 4, which concludes our for loop. When we leave the function, we'll be returning best choice, which is a pointer to the point closest to point P, which is the point found at s at 3. Assume we are returning to the calling function. Notice how clean our code is because we're able to use an array to represent set S. If instead we had had to use a variable name for each point in set S, it would have gotten really messy really fast. Imagine if set S had 1,000 points in it. It's a good thing we have arrays and that they work so cleanly with for loops, where each iteration corresponds to an integer I, and that integer can be used to index each element of an array that we're working with at the time.
In this video, we're going to look at executing some broken code that results in and uses a dangling pointer. The first thing that main does is declare an int star p and initialize it with the return value of init array of 2. We make a box for p, create a frame for init array, pass the argument 2 for how large, and move our execution arrow into the function. The next thing that happens is we declare myArray of size 2. So we get space for 2 ints in this frame. Note that these boxes are not to scale. How large would take up the same amount of memory as each element of my array. Each box would take up 4 bytes if the size of an int were 4 bytes. We enter the for loop, and I has the value 0. We initialize the 0th element of the array to 0, then go through the loop again where I has the value 1, and we initialize my array at 1 to have the value 1. The array is fully initialized, and we have finished our for loop. Now we've reached the line return my array. If you wrote this broken code, you were probably hoping it would copy the array back into, for example, main's stack frame. However, that won't work for a variety of reasons. In main, we've only asked for space to hold a pointer to an int, and not some array of arbitrary size. If we wanted an array in main's frame, we would have had to declare an array there and specify its size. We will see later in the specialization how we can allocate memory outside of the stack, which would persist across function calls. But we haven't learned how to do that yet. So when we return myArray, the value of the expression myArray is a pointer to the first element of the array. So the return value that we return to call site location 1 is just a pointer to this location. So when we return, p is going to be assigned this pointer. However, in the process of returning from this function, that frame goes away. So now this pointer points over here where nothing really exists anymore. We still assign that value to p, and p points right there in memory at whatever happens to be there. But there's no box associated with that anymore. It doesn't belong to a particular variable. If nothing has changed that memory location, it will still hold 0, but because that memory location could be reused for something else, it could change unexpectedly. So at this point, p is dangling. Notice how it's pointing at nothing in our diagram. Dereferencing p is therefore erroneous behavior. So if we were to go inside this for loop, and try to print p at 0, it would be whatever value is in memory where p is pointing. That may still be 0, or it may not be. We don't really know what we're going to get. If I run this on my computer, I get 0, and then 0 again for the second iteration. The first time, presumably it gets 0 left over from my array, but when it calls printf, printf's frame goes right here, overwriting this space. So it's going to destroy the value 1 that was in the box previously here, and this is going to read some value that happened to be in printf's frame from the previous call. Regardless of what happens, this code is broken, and we shouldn't write code like it.
We would like to write a function which can compare two strings to see if they have the same contents. That is, if they are the same sequence of characters. As with all programming problems, we can follow the 7 steps to solve this problem. We'll start with step 1 and do an instance of the problem ourselves. Here we have 2 strings. Notice how we have represented them quite explicitly, including the null terminator character, \0, at the end of each. We're going to start looking at the first letter of the first string and the first letter of the second string. These are both capital A, so we want to look at the next letter. These are both P, as are both letters in the next string. Then we have L's in both strings and E's in both strings. However, now we have a null terminator in the one string and an S in the other. These strings are not the same, so we would give an answer of no. Okay, so what exactly did we do? First, we made this arrow to keep track of where we are in string 1. It points at the first letter of string 1. It is generally a good idea to give things names, so let us call it P1. We also made an arrow to keep track of where we are in string 2, which we might want to call P2. Next, I checked if the letter that P1 points at matched the letter that P2 points at. Both of these were capital A, so I advanced P1 to the next letter after it, and I advanced P2 to the next letter after it. Then I checked if the letter that P1 points at matched the letter that P2 points at. Both were P, and so I advanced P1 to the next letter and advanced P2 to the next letter. And again, I compared the letters that P1 and P2 pointed at, and I found them to be the same. So I advanced P1 and P2. Does this seem a bit repetitive? If so, that is great, since finding repetition is one of the important parts of generalizing, which we will do in just a minute. First, we should finish step 2. Again, we compare the letters P1 and P2 point at and find them the same. So we advanced P1 and advanced P2. P1 and P2 both point at E, so we advance P1 and advance P2. However, now the letters that P1 and P2 point at are different. One is a null terminator and the other is S. So at this point, we decide that our answer is no. These strings are not the same. Here are all the steps that we just did. So now we should generalize them to work on any 2 strings. These first 2 steps are initialization that we will always do. No matter what 2 strings we want to compare, we always want to set up P1 and P2 to point at their first letters. As we noted earlier, these next steps are quite repetitive. We keep checking if the 2 letters are the same and advancing P1 and P2. When do we stop repeating these steps? When the letters that P1 and P2 point at are different. With that observation in mind, we have rewritten our steps to be a bit more general. Here we have expressed these steps as repetition that we do as long as P1 and P2 point at the same letter. These steps are pretty general. We expressed the similar steps as repetition, and we aren't using any values particular to the problem. However, we are missing something very important. Can you spot any warning signs that something is wrong with our algorithm? This algorithm always gives an answer of no, never yes. That comes from the fact that we only worked one example with a no answer and have not thought about how to get a yes answer yet. We should be aware of the fact that we never explicitly checked for the end of the string. How could we fix these problems? We can go back to step 1 and work through another instance of the problem that gives us a yes answer, such as this one. Both strings are apple. We aren't going to work through it in detail, but we will note that we would realize they are the same when we reach the end and have not found any mismatching characters. How do we know when we have reached the end of the string? We know we have reached the end of the string when we encounter the null terminator character \0. We can adjust our algorithm based on this observation. If P1 points at \0, then we have reached the end of string 0. Do we also need to check if P2 points at \0? It would not hurt anything, but we just checked if P1 and P2 point at the same letter. So if P1 points at \0, then P2 must also point at \0 here. Notice that our algorithm now explicitly checks for the end of the string, which was the other warning sign we worried about. Next, you would want to test this out. We're going to elide that step in this video, but we encourage you to try it out and convince yourself that it is right. Now, let's translate this algorithm into code. As usual, we start with the declaration of the function. This function is called string equal, and it takes two const char stars. Why do we have const in the parameter types? Because we want to promise that this function does not modify the strings passed in. This function returns an int, which will be 0 for no and 1 for yes. The first step says that we made an arrow pointing at the first letter of string 1. This line turns into a variable declaration. P1 is a new variable which is initialized to string 1, so that it points at the same place that string 1 points. The type of P1 is also const char star, since P1 is a pointer to a character, but we will not modify the character that it points at. Likewise, the next step is the declaration and initialization of P2 to string 2. Next, we want to repeat some steps as long as a condition is true. Repeating something as long as a condition true translates into a while loop. For the condition inside the while loop, we need to test if the letter P1 points at is the same as the letter that P2 points at. We want star P1 equals star P2. Next, we want to check if P1 points at the null terminator. So we have an if statement whose then clause will give a yes answer, which would be return 1. After this statement, we advance P1 to the next letter. How can we make a pointer point at the next element of a sequence? We can just write P1++, or P1 equals P1 plus 1. Likewise, we can increment P2 to make it point at the next letter in the second string. After the loop, we would give an answer of no, which would just be return 0. Great! Now we have written code to compare two strings and see if they are equal. We should then test this code and see if it works correctly.
In this video, we're going to write a function that copies a string from one place, the source, to another place, the destination. Because we don't want to risk writing past the bounds of the destination, we're also going to specify to our function how much space it has and stop writing if we go past that amount of space. In working an example for ourselves, we're going to take the string cat and copy it to this 4-element array, which is currently uninitialized. We don't actually know what's there, and our function doesn't care. So to do this, I'm going to start copying letter by letter C-A-T, null terminator, into the destination. Now I'm going to perform step 2 and write down exactly what I just did. I made an arrow, which I'll call P1 so I can refer to it more concretely, and set it pointing at the first letter of dest. Then I made another arrow, which I'll call P2, and set it pointing at the first letter of source. I wrote a C into the box that P1 pointed at, then I advanced P1 to point at the next letter, and I advanced P2 similarly. I wrote an A into the box that P1 pointed at, then I again advanced P1 and advanced P2. I wrote a T into the box that P1 pointed at, then I advanced P1 and advanced P2. Finally, I wrote a null terminator into the box that P1 pointed at, and then I was done. Now I'm ready to generalize these steps. These first two steps always happen. We'll just keep them the same, but I'll rewrite them in the imperative mood. Now all of these next steps look repetitive, and you'll note that I've only boxed C, A, and T and not the null terminator because we want to keep the pattern of writing, advancing P1, and advancing P2, but for the last step, we don't advance. These steps are repetitive, and we're doing almost the same thing, except we're writing a different letter each time. Why did we write capital C the first time, lowercase a the second time, and lowercase t the third? If we go back and think about our example, we'll see that in each case, this was what P2 pointed at. So we can just change each of these statements to I wrote the letter in the box P2 pointed at into the box P1 pointed at. Now all three of these groups of steps are the same. We have exactly the same 3 steps, which we've repeated 3 times. These steps are now repetitive, but how do we know when to stop? Are we always going to do this 3 times? Probably not. If we go back to our example, we will see that we stop when we reach the end of the string we're copying. That is, when P2 points at a box with a null terminator in it. So we specify, as long as the letter in the box P2 points at is not the null terminator, then we will do these 3 steps. After we finished this, we wrote a null terminator into the box that P1 pointed at. Since we are always going to want to do this, we can write this simply as a direction. We have finished generalizing our algorithm. Now we should test it. We're going to walk through our algorithm with a different test case. Source is once again cat, but n is only 2, so dest is an array with space for 2 letters. Walking through these steps, we'll make an arrow for P1, make an arrow for P2. As long as the letter in the box P2 points at is not the null terminator, it's C, so it's not, we go inside the repetition. Write the letter in the box P2 points at into the box P1 points at, advance P1, advance P2, then go back and continue repeating these steps. Again, it's not the null terminator, so we write, advance, advance, go back and continue repeating these steps. P2 is again not pointing at the null terminator, so we're going to write the letter in the box P2 points at, which is a T, into the box P1 points at. Unfortunately, P1 has gone past the end of the destination array and is now writing into a box it should not. We have no idea what piece of memory this is or what it belongs to, and we're going to do bad things to our program. It may misbehave in strange ways, a segmentation fault, or who knows what. This means we need to go back and fix our algorithm. Reworking steps 1, 2, and 3 to fix this problem. We're not going to walk through them in this video, but you'll see that we should only do these steps as long as the letter in the box P2 points at is not the null terminator and P1 is not equal to stop, which is going to be a new arrow that we make pointing just past the end of the destination array, that is n letters after dest. Then at the end, we're going to check that P1 is not equal to stop before we write the null terminator into the box P1 points at. In other words, we're going to draw an arrow past the end of the array and stop doing anything if we get there. In the next video, we'll translate these improved steps into code.
You've been learning about multidimensional arrays and the differences between what it means to declare them with multiple sets of square brackets versus as arrays of pointers. Sometimes new C programmers have trouble understanding the differences as well as the importance of those differences. Here, we're going to see some broken code that underscores the incompatibility of these representations and what goes wrong when we try to naively fix it by lying to the compiler without thinking about what we are doing. If we try to compile this code, we get this error message. Let's take a second to pull this apart. It tells us that we are passing argument 1 of print array, which we do here, from an incompatible pointer type. In particular, it expects an int star star, because that is how array is declared, but we actually passed it an int star 3, that is a multidimensional array whose second dimension is 3. Remember that the compiler doesn't need to include the first dimension in the type due to the way that multidimensional arrays are laid out. A naive C programmer might try to fix this code by adding a cast. Anytime you want to cast something, think very carefully about what you're doing. With this change, the code compiles, so everything is good, right? It turns out that lying to the compiler about how data is laid out is often a bad idea, so we aren't actually going to like the results when we try to run this code. Let's see what happens. We start in main and create data. Then we call print array passing in data 3 and 3. We enter the first for loop and enter the second for loop and are now ready to print array at ij. So we need to evaluate that expression. First, we can evaluate array, which is an arrow pointing at the first element of data. So what is array at I? We know I is 0, so this would be array at 0, which would be this box here. but we need an arrow because we told the compiler that array points at an int star. However, we just have a number. Furthermore, we may be on a platform where size of an int star is larger than size of an int. For example, on the system you work on, pointers are 8 bytes and integers are 4 bytes. In that case, we actually need to read these two boxes and interpret them as an arrow. What happens when we try to do that? Well, remember, everything is a number, so the program is just going to read a numeric value and interpret it as a pointer. To see more precisely what might happen, we need to look under the hood. On the left, we've listed memory addresses and the values stored in them. Each row corresponds to 4 bytes. The thin blue line divides main's frame, which is on top, from print array's frame, which is on the bottom. These values at the top are data, which is laid out with each element sequentially in memory. The return address is stored in the frame as well, even though it does not figure into our example. Array is stored in the frame. Notice how its numeric value is the address of the first element of data. Also, as a pointer, it takes up 8 bytes on this platform. Then we have width, and height, and I, and j. But let's go back to array, since we are trying to evaluate array at 0. We've told the compiler that array points at an int pointer, so array at 0 is these 8 bytes here. That is, the value of array at 0 is this pointer you see here. Where in the program does this pointer point? We didn't get it by taking the address of something. We just put some numbers together and turned them into a pointer. Remember this general picture of the layout of memory? The particular address ranges shown here are platform and program specific, but were obtained for this test program on a 64-bit architecture. If you look at this picture, the pointer we just evaluated for array at 0 lands right here in this empty region between the stack and the heap, so it points at an invalid region of memory. So if we go back to our picture with the code, array at 0 points off into invalid memory. So what happens when we try to evaluate array at ij? Well, we're going to try to dereference this pointer, which points off into an invalid portion of the address space. What happens when you try to dereference a pointer to an invalid region of memory? Everyone's favorite way for a program to crash, segmentation fault. It turns out that lying to the compiler was a really bad idea. Our program compiled, but then crashed when we tried to run it. Now, we are going to take a moment to look at the mechanics of a serious and common security vulnerability. In this code, a sloppy programmer used the getS function. You should never use getS, as it has no way to specify the maximum number of bytes it should read into a fixed size buffer. We'll step through this code with a look under the hood instead of our usual, more conceptual model. In general, when we violate the rules of C, we have to look under the hood to see what might happen and why. We're going to start with a quick tour of the stack layout as we've drawn it here. The layout of the stack frames under the hood is very platform specific, but this attack can be adapted to most platforms. This line separates the frame for main at the bottom from the frame for its caller at the top. Main gets called by part of the C library. There are probably values other than 0 in that frame, but what they are doesn't really matter. Here we have argv, which is an 8-byte pointer. It points at an array of strings, which is not pictured here. Then we have argc, which is a 4-byte integer, whose value is 1. Then we have the return address, which is an 8-byte pointer. That points somewhere in the code for the C library right after it called main. The code in that part of the C library will call exit, passing in the return value of main. Now we'll start execution at the start of main. We declare input, which will be these next 12 bytes in the stack. Then we call getS, which is somewhere in the C library. The programmer expected that the user would input something less than 12 bytes, such as hello, which would write these bytes into the first part of input. But what if the input is longer than 12 characters? getS has no idea how much space is actually allocated to input, so it will just keep writing data into the next addresses on the stack. Notice that the return address is on the stack. What happens if you overwrite that? you'll change where main returns. That seems bad. In fact, it is particularly bad if the input is carefully crafted by an evil hacker, in which case it might look like this, where I've written non-printable characters as \x and a hex value. Don't worry about the specifics of this data. I made it by writing and compiling the code I wanted to trick this program into executing and saving those bytes from the executable. So what happens? The first 12 bytes are no problem. They get written into input as we'd hoped. But this input is longer than 12 bytes. The next 8 bytes of the input overwrite the return address. Notice that the value we overwrote it with looks like a valid pointer into the stack. In fact, that pointer is the address of argc, which is important since we continue to overwrite argc and overwrite argv, and then overwrite the data in the caller's frame. Notice we finally read a new line which has numeric value hex 0a, and then getS wrote a null terminator which has value hex 00. Now getS is finished, so it returns to main, which prints from input until it finds a null terminator. So it will print some letters and then some non-printable characters. Now we are ready to return from main. Usually our program would exit, but that is because it would return to the C library code which exits the program. However, since we corrupted the return address, we're going to return to the address it specifies and keep executing code there. That address is right here on the stack and contains the carefully crafted data that the evil hacker entered. So when we return there, we will start executing whatever instructions correspond to the values that the hacker entered. This particular set of instructions was crafted to execute the command shell. Imagine if the code were part of a network service and an attacker were able to get a shell on the system from their buffer overflow. They could then execute any commands they want. The moral of the story is to never use getS and be careful to never allow buffer overflows.
This video is going to trace through the function factorial, which is recursive. Note that there is a call to factorial as part of the function's return statement. We begin in main, and the first line declares a variable x and initializes it to factorial of 3. We create a frame for factorial where n has the value 3, mark call site 1, and move our execution arrow into the factorial function. N is not less than or equal to 0, so we skip the if statement. We are now at the return statement, which has a recursive call to factorial, this time with the argument 2. I'm also placing a 2 on the call site marker to indicate that when we finish this call to factorial, we need to return to call site 2. Let's step into the function. N is equal to 2, which is not less than or equal to 0. We'll move down to the final line of the function and place a recursive call to factorial, this time with argument 1, but the same call site location 2. We step into the function, move down to the final line of code where we have another recursive call to factorial, this time with the argument 0. We step into the function, and this time n is less than or equal to 0, so we have a return value of 1. We're going to send 1 back to the call site location of the function that called this one, and return back to the call site location. Now we have some multiplication. 1 times 1 gives us the value 1, and now we're going to return 1 to the function that called this function. We return to the call site location, and now we're in the function factorial where n has the value 2. So 2 times 1 gives the value 2, which we will return to the function that called this instance. Now we're in the initial execution of the factorial function where n has the value 3. We're going to create a return value of 6 and send that to the initial call to factorial. Now we can leave the function and return to main, finishing this assignment statement, giving x the value factorial of 3, which has the value 6.
In this video, we're going to walk you through the 7 steps to figure out the algorithm that computes factorial. The first step is to work an instance of the problem yourself. So let's begin by computing 4 factorial by hand. The first thing we would do is recognize that 4 factorial is defined as 4 times 3 factorial, which now gives us the problem of solving 3 factorial. 3 factorial is defined as 3 times 2 factorial, so we figure out what 2 factorial is. It is defined as 2 times 1 factorial, so we figure out what 1 factorial is. which is 1 times 0 factorial. And 0 factorial is just 1. Now that we know what 0 factorial is, we can replace 0 factorial with a 1. Now we know what 1 factorial is, 1 times 1, which equals 1. So we replace 1 factorial with 1. 2 factorial is 2 times 1, which equals 2. So we replace 2 factorial with 2. 3 factorial is 3 times 2, which equals 6. So we replace 3 factorial with 6. 4 factorial is 4 times 6, which equals 24. So this is our answer to the whole problem. In step 2, we need to take a moment to think about what we did in step 1 and write down the sequence of operations. When we needed to figure out what 4 factorial was, the first thing we did was compute 3 factorial. When we needed to compute 3 factorial, the first thing we did was compute 2 factorial. For 2 factorial, we computed 1 factorial. For 1 factorial, we needed to know what 0 factorial was. But for 0 factorial, we didn't need to compute anything. We just knew that 0 factorial has the value of 1. Once we figured out what the value of 0 factorial was, we used it to compute the value of 1 factorial by multiplying that by 1. Once we knew the value of 1 factorial, we used it to compute 2 factorial by multiplying it by 2. Once we knew the value of 2 factorial, we used it to compute 3 factorial by multiplying it by 3. Finally, we used the value of 3 factorial to figure out the value of 4 factorial by multiplying it by 4. Let's take a minute to write down the steps we did for each of these computations. To compute 0 factorial, we simply answered 1. To compute 1 factorial, we computed 0 factorial, then we multiplied that result by 1, and that was our answer. To compute 2 factorial, we computed 1 factorial, multiplied that result by 2, and that was our answer. To compute 3 factorial, we computed 2 factorial, multiplied that result by 3, and that was our answer. Finally, to compute 4 factorial, we computed 3 factorial, multiplied that result by 4, and that was our answer. Step 3 is to generalize our process. Let's take a moment to look over the computations we performed. The first thing you might notice is that computing 4 factorial down to 1 factorial involved very similar steps, whereas computing 0 factorial was a little bit different. This is a special case called the base case, and usually it's incorporated into the definition of the thing we're trying to compute. For example, part of the definition of factorial is that 0 factorial equals 1. So the first thing we might write down when trying to generalize this process is recognizing the one case that's a little bit different. We should determine if n is 0 or not. Then, the answer is just 1. Otherwise, we need to do something a little more complicated. Let's look a little more closely at how we computed 4 factorial down to 1 factorial. The first thing you might wonder is, why are we computing 3 factorial to compute 4 factorial? Also, why are we computing 2 factorial to compute 3 factorial? In generalizing this, we would realize that every time we compute n factorial, we compute n minus 1 factorial, which is the first step in the process. We're going to compute n minus 1 factorial, and we'll give it a name. We might call it n minus 1 fact. Now that we've figured out the pattern of behavior, we can update our description below using this generalized description. Every time we compute a particular factorial, we compute n minus 1 factorial, and then multiply that by some integer value. So let's take a closer look at that integer value. When we compute 4 factorial, we multiply n minus 1 fact by 4. When we compute 3 factorial, we multiply n minus 1 fact by 3. The pattern that we see here is that the integer is always n. So we can generalize our steps to say that we are multiplying n minus 1 fact by n. And that resulting product is the answer. Now that we've written carefully generalized steps for calculating factorial, it's important to take a minute to test our algorithm using a variety of possible inputs. Try computing several test cases yourself. Does it work? Testing on negative input values is actually going to show us a flaw in our code. Consider the calculation of -2 factorial. -2 is not equal to 0, so we're going to recurse and compute -3 factorial. -3 is also not 0, so we're going to compute -4 factorial, and so on. You can see that this code is going to recurse forever since it doesn't make progress towards the base case. In fact, we have a mistake in our algorithm. We need to be testing whether n is less than or equal to 0, not just whether it is equal to 0. Now, we've written out our algorithm and tested it, even finding a bug in our algorithm. In the next video, we will translate this algorithm to code. In this video, we will translate the algorithm we developed in the previous video into code. We've included our algorithm as comments, shown in blue, and we will turn these steps into C code. To begin with, we are going to put all of the steps inside of a function, factorial. Factorial takes an integer n and returns an integer that is the factorial of n. Now, to determine if n is less than or equal to 0, we're going to use an if-else statement. If n is less than or equal to 0, we want to answer 1, which we can do with a return statement. Now we want to represent the otherwise case, which is the else part of the if-else statement. To do this more complicated case, we need to create a new variable, n-1 fact, and we're going to have to make a function call to perform a complex step and figure out what value to assign to n-1 fact. The function we want to call happens to be the one we are writing, so we place a call to factorial with the value n-1. Now that we have the value n-1 fact, we want to multiply it by n. That is the result we'd like to return, which we can do with a return statement. Now we've completed our function, and our remaining steps would be to test and debug it.
In this video, we're going to walk through the first 4 steps of the programming process in the context of Fibonacci. We'll begin by working out an example, computing Fibonacci of 4. Fibonacci of 4 is defined as Fibonacci of 3 plus Fibonacci of 2. So what's Fibonacci of 3? It's defined as Fibonacci of 2 plus Fibonacci of 1. What about Fib 2? That's defined as Fib 1 plus Fib 0. And Fibs 1 and Fib 0 are defined as 1 and 0 respectively. So 1 plus 0 gives 1. Now we need to move over to the right-hand side of the blue expression, calculating Fibonacci of 1, which, as we just said, is 1. So now we add 1 plus 1 and get 2. Since we have now computed Fib 3, we move over to the right-hand side of the top expression, computing Fibonacci of 2. Fib 2 is defined as Fib 1 plus Fib 0, and as we said earlier, Fib 1 and Fib 0 have the values 1 and 0 respectively. If we add those together, we get 1. So Fib 4 has the value of 2 plus 1, or 3, and that's our answer. In step 2, we need to write down all of the things we did in step 1 to compute Fib 4. So let's begin with the tree we just created and write down all the steps we performed along the way. First, we computed Fib 3. This prompted us to compute Fib 2, and in the process of computing Fib 2, we had to compute Fib 1 and Fib 0. Then we went back up to the blue expression and computed Fib 1. Then we needed to move over to the right-hand side and compute Fib 2, which required us to compute Fib 1 and Fib 0. Let's take a look at how we compute Fibonacci of each of these numbers. To compute Fib 0, we simply answered 0. To compute Fib 1, we simply answered 1. To compute Fib 2, we were required to compute Fib 1 and Fib 0 and add them together. For Fib 3, we computed Fib 2 and Fib 1 and added those together. And for Fib 4, we computed Fib 3 and Fib 2 and added those together. Step 3 requires that we generalize, looking for patterns in our series of steps. The first thing you may realize is that computing Fib 4, Fib 3, and Fib 2 looks like a very similar set of steps, whereas computing Fib 1 and Fib 0 looks a little bit different. In fact, computing fib 1 and fib 0 are special cases called base cases. We simply know the answer. So what we might want to do is determine if n has the value 1, and if it does, we just answer 1. Similarly, we determine if n has the value 0, and if so, answer 0. Otherwise, we're going to have to deal with these complicated cases over here on the left. So let's look at that a little closer now. The first thing you might want to do is look at the first line of each of these computations. Why is it that when we were computing fib 4, we began by computing fib 3? And why is it that when we computed fib 3, we had to compute fib 2? The general form here is that the first step for computing fib n is to first compute fib n minus 1. So we can replace this first line in each of these computations with compute fib n minus 1, which we will call fib n minus 1. We can replace this line in each of our similar steps below. Next, you might ask, why were we computing fib 2 here? And why were we computing fib 1 here? The general form is that the second step for computing Fibonacci of n is to compute Fibonacci of n minus 2. The general form has us compute fib n minus 2, and we're going to call that fib n minus 2. We can replace that in the computation below. And finally, we sum up our answers. The great thing about creating a general form is that now all of our steps for each of these calculations are identical. And so our otherwise case is simply these 3 steps, regardless of whether n is 2, 3, 4, or more. In step 4, it's important to test our algorithm. Let's see if our algorithm works to compute Fibonacci of 6 or Fibonacci of 1. How about Fibonacci of -2? When we perform the test to see whether Fibonacci of -2 is correctly calculated, we're going to discover a problem. -2 is not equal to 0 or 1, so we're going to step into our otherwise clause, computing Fibonacci of -3 and Fibonacci of -4 and adding these together. However, in order to compute fib -3, we're going to find ourselves computing fib -4 and fib -5. This process is not going to terminate. This is not good. This test case betrays a problem in our algorithm. In fact, we haven't been completely true to our definition of Fibonacci. If you look back at the original definition of Fibonacci, you can see that there are 5 cases. The case where n is 0, the case where n is 1, the case where n is greater than 1, and there's 2 cases where n is negative. We didn't handle these 2 cases, and we need to. The other thing to notice is that our otherwise clause was handling the case where n is greater than 1, even though we never explicitly said so. So we're going to have to explicitly place that into our code, testing whether n is greater than 1. And if it is, we perform those computations. Otherwise, if n is less than 0, we're going to need a few new steps. Now, normally we would suggest you go back and do steps 1 to 3 to handle the additional Fibonacci cases. For the sake of time, however, let's assume we already did that, and this is what we came up with. If n is less than 0, we're going to compute fib of -n and call it fib neg n. Then, when n is odd, that's the answer. And when n is even, we multiply fib of -n by -1, and that's our answer. We would now test the revised algorithm with the new test cases. Previously, we devised this algorithm to compute the nth Fibonacci number. Now let's turn that algorithm into code. I've written those steps as comments and put the function declaration around them. First, we determine if n is 1, which is now our familiar if-else statement. Inside the then clause, we give an answer, which is again familiar. We will return that answer. Inside the else clause, we again compare n to a value and return an answer, which will be similar to what we just did, an if statement with a return statement inside of it. We're just going to move this up to make a little more space and see now that we need to make another decision. So we're going to have another if statement. Inside of the then clause of this if statement is where things get interesting. We want to name a quantity, so we want to declare a variable. But what value are we going to assign to it? Computing fib of n-1 seems like a complicated step. We've seen complicated steps before where we have abstracted the complexity out into a function. What would this function look like? Well, it would take an int, compute the Fibonacci of that int, and return it. That sounds exactly like the function we're writing right now. So instead of making a new function, let's just call the fib function we're currently writing. This next step in the algorithm is quite similar. We are going to call the fib function to do all the complicated work of computing fib of n-2. Our next step calls for us to sum two variables and return them as our answer. So we can write a return statement for that. Now we'll just move the code up a little bit more and begin working on this else clause. We have another if statement, which we are just going to write with the else for brevity. We are again declaring a variable and want to initialize it with the result of a complicated step, where we compute fib of -n. So as before, we'll just trust the fib function we are writing to do that work for us. We're almost done. One more if-else statement. Here we are going to use mod to see if a number is even or odd. Remember that n mod 2 will give us the remainder when we divide n by 2, so 0 will mean that n is even, and 1 will mean that n is odd. Inside the then clause, we give our answer. We were a bit imprecise saying that is our answer here. Oops, what did we mean? We meant fib neg n is our answer. Likewise, in the else clause, we want fib neg n times -1 to be our answer. We've removed all the comments that we had so that we just have code. Now we might want to clean it up a little bit and make it look a little bit nicer. The variables are a little bit cluttered. We were verbose in our steps and separated out each computation, giving it a name, but we might just return fib n-1 plus fib n-2. Likewise, instead of writing -1 times fib neg n, we might just write negative fib neg n. These cases are exhaustive. We have checked if n is 1, 0, and greater than 1, so the only other possibility by the time we get here is less than 0. We can and should get rid of this extra if. In fact, if we don't, the compiler may complain that we could reach the end of the function without returning a value. Most compilers are not smart enough to reason about algebraic properties of numbers and figure out if a set of conditions cover every possible case. They do, however, understand that code will always execute either the then clause or the else clause of an if-else. We can also simplify these first few steps by realizing that if n is 0 or n is 1, we're just returning n, and write one if statement with an or in its conditional expression. We could add a comment here to help the reader understand what we were thinking. And then we're done. Most of that cleanup was optional since these two pieces of code are algorithmically equivalent. However, this code looks much nicer than the code we started with.
In this video, we're going to trace through a series of recursive calls to the function Fibonacci. Recall that Fibonacci is defined for any value n as the sum of Fibonacci of n-1 and Fibonacci of n-2. If we begin with the Fibonacci of 5, we're going to see two recursive calls for n-1 and n-2, and this will occur repeatedly until we hit a leaf node. A leaf node is Fibonacci of 0 or Fibonacci of 1, which simply have the definition 0 and 1 respectively. At the end of this series of calls, you can see that we've called Fibonacci many times. Specifically, we've called Fibonacci of 0 3 times, Fibonacci of 1 5 times, Fibonacci of 2 3 times, and we've called Fibonacci of 3 twice. So although this recursive definition is correct, it's not particularly efficient. The problem is not that recursion is slow, it's that algorithms that recompute the same thing many times are slow. Whether or not this is acceptable depends on your programming context, but you should be aware of how a problem like this can affect performance. If slow performance were unacceptable, you could rethink your algorithm to avoid repeating calculations, or you could use memoization, keeping a table of values that have already been computed and check that table to see if the answer has already been computed before doing it again.
In this video, we're going to trace through the execution of a tail recursive version of factorial. The factorial function has one parameter n, which is the number we're computing the factorial of, and it returns an integer that is the factorial of that input. The difference between this version and the previous implementation is the helper function named factHelper, which has two parameters, an integer n and an integer answer. N is the number we are computing the factorial of, and answer is a running product that gets computed with each recursive call. You can see that when factHelper calls itself, it is the last computation it does. This is called tail recursion. Let's step through the execution. We begin inside a factorial where n has the value of 3, and we're going to call factHelper. So we need to create a stack frame, and we're going to send in the arguments, n equal to 3 and answer equal to 1. We mark the call site location with a 1 so we know where to return when we leave the function. Inside of factHelper, because n has the value of 3, we skip over the base case and we're going to call factHelper once again. This time, creating a stack frame for the next recursive call where n has the value of 2 and answer has the value of 3. Now, as we step through this code, note that it does not have a compiler optimization that we'll introduce later in this video. So this is going through the tail recursive function as you would expect it to happen with nothing fancy or optimized yet. We step into the function, once again we pass the base case, then we make another frame for the next call to factHelper where n has the value of 1 and answer has the value of 6. We step into that function, pass the base case, and make another stack frame for this call to factHelper where n has the value of 0 and answer has the value of 6. This time when we step into the function, n is less than or equal to 0. This is the base case, so we return the answer 6 all the way up these calls. Returning from the recursive call to call site location 2, then repeatedly returning to call site 2 and destroying the stack frame for each recursive call. This repeats again. Finally, we return the value 6 to call site location 1 and move our execution arrow back into the function factorial. Now the thing to notice here is that we only needed to return the value 6 all the way up these calls. As soon as we placed each tail recursive call, we didn't actually need the stack frame anymore because there's no value in the frame that we're going to use again. An optimizing compiler will recognize this and perform what's called tail recursion elimination. A stack frame will not be created for each recursive call to factHelper. Let's step through the optimized version. We start inside of factorial once again with n having the value of 3. We create a stack frame for factHelper where n has the value of 3 and answer has the value of 1. We mark the call site location 1 and step into factHelper. N is not less than or equal to 0, so we're going to place the recursive call to factHelper. However, we're going to reuse the frame. First, we have to evaluate the parameters to 2 and 3 respectively. Note that we do this before we start changing any of the values in the frame since we want to use the current values. Then we are going to update the value of n in the frame to be 2 and the value of answer to be 3. Now we jump back inside of factHelper, past the base case, and once again we're about to place a recursive call. But instead, the compiler will make the code update the values of n and answer to the new arguments 1 and 6. We skip the base case and reuse the stack frame one more time, this time with n having the value of 0 and answer having the value of 6. This time we go into the base case and now return the answer of 6 one time back to call site location 1 in the function factorial. Notice that the stack frame does not need to be created for every call to factHelper. What this means is that the space you require is no longer proportional to the size of n. You simply need one frame for factorial and one frame for factHelper.
In this video, we're going to step through the execution of two mutually recursive functions, isOdd and isEven. These functions are also tail recursive, so they can have tail recursion elimination applied to them by the compiler such that we will not create a new stack frame for each function call. We assume a function is called isOdd with the argument 4. X has the value 4, so we'll pass by the two base cases because x is not equal to 0 or 1. Now we've reached the return statement and want to call isEven. Instead of creating a new frame for isEven, because this is tail recursive, we can simply reuse the frame that we have for isEven, updating x to have the value 3. Stepping into isEven, we're going to pass the two base cases once again, and now we want to call isOdd with x having the value 2. Once again, we reuse the stack frame, updating the value of x to 2. Inside of isOdd, we pass the base cases, then we want to call isEven one more time. We'll reuse the stack frame once again for isEven, this time updating the value of x to be 1. Finally, we've hit the base case, since x has the value of 1, and now we can return the value of 0. This return value is going to go to the original function that called isOdd at the very beginning of this example, and the execution arrow will return to the call site 0.
Hi, I'm Arda. I'm a software engineer at a big tech company in Bay Area, California. And I attended Duke between 2017 and 2018 in the Masters of Engineering, Electrical and Computer Engineering program. So during the summer, I did my internship in a large company in Bay Area again. And during that internship, we were given projects that had real impact. They were not just mock projects for interns to do. So my project was related to what we saw in Andrew Hilton's class that is named Engineering Robust Server Software. So during that class, we learned how to build up robust servers, how async input-output communication works, and stuff like that. And that really helped me during my internship project because my project was basically a class project, but much more harder and larger scale. I cannot really go into much detail, but I can say that there was this service that was being used by machines around the world. I got the chance to rewrite this service by using asynchronous communication, threads, event bases, futures, and everything. So that would be my best project. By the end of it, the service was serving requests around 1.7 seconds. So after I rewrote this whole thing over the summer, it got down to 0.7 seconds. So that was really cool to see that, oh, I have this knowledge and I can apply it to this project and I can get the result that I want. Oh my God, this is now more scalable, more robust, and more fast. So that was super cool to see. Like the thing that you learn while studying programming and applying them to real life problems and seeing the results of it there's just something so satisfying about it. So for novice programmers, I think that the first thing that they should learn is to be patient, because learning programming takes time, right? Everybody wants to do that, as now it's like one of the most popular job around the world. So yeah, be patient, be passionate, love what you're doing, because if you don't love it, you're gonna have a bad time. I've seen, so during my time at Duke, I've seen people on both sides, right? People that loved what they were doing, and people that wanted to learn programming because it just made, that was like the most popular choice. And people who had to do it instead of who wanted to do it kind of did not perform as well as the other people. The workload of this class is a lot. So when you're taking this class, you should know that you should also take the time to study it and read the material and everything. During this class, the hardest thing I had to do was forget how I learned programming to be able to incorporate the approach that was given by Drew. Because I knew that, like, after the first week of this class, I knew that, oh my God, this is actually pretty cool. And I was not doing it wrong, but I was doing it in a different way that was not suitable for me. So I was really glad to take this programming class. Even if you don't know anything about C, if you take this class, by the end of it, you'll be around intermediate level and you'll have a solid background and a solid foundation of algorithms, C, and data structures. also know what you want to do, because it's really, I know it's hard. It'll be hard at the first time to say, oh, I can do programming, so I can do anything that is programming related. That's kind of not true. There's a lot of things that you can do after learning how to program. So I think my first advice would be just pinpoint the thing that you want to work at, like pinpoint the problems that you want to solve, and pinpoint the things that interest you, so that you get a job that is stimulating, exciting, and that'll like keep you learning and in a studying mode, basically. And also, it's a good thing to network. If you have time, or if you have people that you know that are in the business, it's a good idea to reach out to them and see if their company is hiring. If you know if there's going to be a career fair or a tech fair, just attend that and speak with companies. And also, it's important to not forget that there are more companies other than Apple, Google, Microsoft, Facebook, right? There's a lot of tech companies that need qualified people to do work for them. So that's also an important thing to realize.
Welcome to Course 4. Your C programming skills are developing nicely, and it is time to finish out the specialization with a few more very important topics. The first thing we're going to talk about is interacting with the system and the user. You've printed output to the screen, but what if you want to read input from the user? What if you want to store data in a file instead of printing it to the screen? Or read data in from a file? How do programs that take command line arguments use them? We'll cover all of these topics, as well as some background on the relationship between your program and the operating system, which is involved in these tasks. The second major topic in this course is dynamically allocating memory. What does this mean? It means allocating space to store data when your program runs, because you do not know how much space you need when you write it. If your program will read a file, you don't know how much data will be in that file. It might be 50 lines, or it might be 50 million. Even if you made a 50 million element array to hold the data, you might find that your program needs to handle 500 million elements. Finally, we'll wrap up with a discussion of some important concepts to keep in mind as you move to writing larger programs. What you've written in this course is pretty small. Some programs have thousands or even millions of lines of code in them. We aren't going to work on anything that large, but we'll talk about important principles and work through a moderately larger example. So let's dive right in.
In this video, we have an example of reading from a file with fgetc, which reads characters one by one from a file. This example is going to count the number of letters in the file and print it out. As always, our execution arrow begins at the start of main. Now that we have command line arguments, main's frame begins with argc and argv in it, with whatever command line arguments were passed in. In this example, we're going to assume that the name of the program is count letters, which is argv at 0, and that input.txt was passed in, which is argv at 1. argc is 2 and argv at 2 is null. We start with some error checking. We see if argc is not equal to 2. We've omitted the error code in the interest of brevity here. argc is 2, so nothing special happens there. Now we're going to fopen a file. The name of the file is going to be argv at 1, whatever our command line argument is, in this case, input.txt. We'll make a box for f, and we'll call fopen. We don't have the code for fopen, so we'll just have to know what it does. It's going to open a file and return a pointer to that. We'll assume it succeeds here. The name of the file is input.txt, and it's in read mode, and the end of file is false. We have just a little bit of contrived text in this file, and the current position of the file is at the start. F is not equal to null. We've again omitted that error code, but if we were writing a real program, we'd have it there. Next, we declare a variable c. We declare the variable letters and initialize it to 0. Now we're ready to make our first call to fgetc. As you saw in our reading, we have this programming idiom of c equals fgetc of f does not equal eof. We're going to have to evaluate fgetc first because we have an assignment here. We need to figure out what this evaluates to put it into the box named by C. fgetC is going to advance the position of the file by 1 character and return the character that it advanced over. It just read A, and the next time we call it, it will read B. We then do this assignment even though it happens in the context of an expression we're evaluating. It still behaves the same way. We take A and we put it in the box named by C. Then we're going to compare that result, which evaluates to the value that was assigned, the character A, to EOF. A is not equal to EOF, so this evaluates to true, and we go inside the while loop. Now we're going to do if is alpha of C. Is alpha is a function in ctype.h that determines whether a character is alphabetic. A is alphabetic, so we go inside of this if statement, we increment letters, finish the if, and return to the start of the while loop. fgetC reads the next character, which is B, and we assign that to C. B is not EOF is true. This character is alphabetic, so we increment letters, finish the if, and return to the start of the while loop. fgetC reads the character 4, which is not alphabetic, so we skip over the body of the if and go back to the top of the loop. Now the file position is right before a new line character, so we read the new line character, which is still not EOF. New line is not an alphabetic character, so we skip the if and go back around the loop. We read a C, which is a letter, so we do the if statement, incrementing letters to be 3. We're right before a new line, which we read, then go through the loop. Now we actually are at the end of the file. fgetC returns EOF, which is what we're going to assign to C, and the status of the file that indicates end of file is going to be set to true. If we were to call feof, which is a function that checks that, it would return true now. Since the loop guard evaluates to false, we're not going to go into the while loop. Now we have a print statement. %s has %d letters in it. %s converts argv at 1, which is input.txt, and %d converts letters, which is 3. So we print out input.txt has 3 letters in it. Finally, we'll return exit success, exiting our program. We've cleared out the stack frame for main. You'll notice that these arguments are still around. That's fine. They're actually created somewhere in the C library. They belong to a different frame. This file is still around because we haven't closed it, which we'll learn how to do soon.
In this video, we have an example of reading from a file with fgetS, which reads lines of a specified length from a file. In this example, we will convert each line of text to an integer with the function atoi, add each integer to the sum, and print the result. For the purposes of this example, the array that we're going to read our characters into is going to have a relatively small size. We define line size here as a constant 5, make the array that big, and also tell fgetS that we want to read into an array of size 5. We're going to do this for the purposes of example, so we can see what happens when fgetS cannot read all of the characters on the line. As before, we've omitted some error checking, assuming that we would print an error message and exit under these two conditions. We begin with our execution arrow just inside main, where argc has the value 2, and argv is a pointer to the array of command line arguments. We assume that the name of the program is some numbers, and that argv at 1 is the name of the input file, nums.txt, which has the numbers in it. We see if argc is not equal to 2. It is 2, so we don't do any of that error code. We're going to open this file for reading, as we've seen before. The file has numbers in it, and the current position in the file is at the start. F is not null, so we don't do anything special there. We make a box for total, which is 0. Then we create the 5 boxes for line, each of which will hold a character. Now we're ready to call fgetS. It's going to read into line, filling in the boxes with the information it reads from the file. We tell it that there are at most 5 boxes that it can read into, which really means 4 characters plus a null terminator character, which it has to put at the end. The last argument tells it to read from F. As we do this, notice that the cursor in the file showing the current position is at the start, and it's going to read across the line as we fill in the boxes with the text. So we just read 123 and a new line, as well as a null terminator into line, which filled the 5 boxes. And now the current position is in the file is at the start of the next line. Remember that the function strchar takes a string and a character and returns a pointer to the first occurrence of that character if it is found in the string. If it is not found, it returns null. So this is going to check if line contains a new line, letting us know if fgetS was not able to read the entire line. In this case, it returns a pointer to the fourth box, which is not null, so line contains a new line, and everything is good. We're now going to convert the text 123 to the integer 123 and add it to total, which is 0. 0 plus 123 is 123, so we change total to 123, and we return to the top of the while loop. Now we're going to call fgetS another time. It's going to read this next line into the variable line. Notice that it wrote 1 for new line, then the null terminator here, and left the last box unchanged because it had already read the entire line. We again do strchar of line and the new line character. We find that it is not null. Then we add 14 to 123 and we get 137. We update total to 137 and we go around the loop again. Notice that the number on the next line, -56789, is too big to fit into the variable line. It has more than the 4 characters we're able to read. So fgetS is going to read as much as it can and then stop. It's going to read -567 and then it's going to stop because we told it that the array has at most 5 characters and it needs the last one for the null terminator. The position in the file is between 7 and 8. If we were to read again, we would read 8 and 9 whether we use fgetS or fgetC or any other function that reads from a file. However, for this code, it's not set up to be able to handle that, so we have error checking for not reading the whole line. If we were to make line size bigger, we would make this all succeed. Here, we do the check for the new line character, strchar returns null, and we'll do the error handling. We print line is too long, and we exit failure. Notice that we haven't closed the file, since we'll learn how to do that shortly.
Now let's take a look at some code that writes to a file. We are starting at the beginning of main with argc and argv shown in main's frame. Here, the program has been run as ./print squares with arguments 15, 17, and output.txt. First, we check for the error condition where the wrong number of arguments have been passed. argc is 4, so there's no need to execute the error handling code. Next, we convert argv1 from a string to an integer using a to I, and store the result in the variable start. And similarly for argv2 and end. Now we are ready to use fopen to open a file. Notice that we pass in argv3 for the file name, so the file we will create will be called output.txt. We pass in w for the mode, so we will create the file if it does not exist, or truncate it to 0 length if it does exist, then start writing to it from the beginning. We draw the state of f by noting the relevant details of the file, as well as its contents, and where the next write operation will occur. Next, we check if fopen failed, which it did not. Now we have a for loop, so we go into it, creating I, which is 15. The next line says to fprintf the value of I squared into f. This will work just like printf, except that instead of printing it to the screen, it will write it into the file. We have also made the file position marker move to the next line, since we printed \n too. We then go to the next iteration of the loop and write 256 new line into f. We then do one more iteration and write 289 new line into f, and then we are done with the for loop. So now we are going to fclose f and check if that succeeded or failed. Here, fclose succeeded, so the operating system accepted all of our data for writing, even if it has not yet physically written it to disk yet. Finally, our program exits successfully.
In this video, we'll look at what happens when fclose is called. A lot of this is conceptualized because we're not actually going to delve into the details of what the kernel does or how it interacts with the hardware. The important thing to understand here is that our program may have buffered up these writes, it may be holding them in the file structure the C library manages, and may not have actually written them down to the operating system yet. Therefore, they're not actually on the disk. However, when we close the file, these writes have to actually be propagated down, so the first thing that's going to happen if the C library has unwritten data is it's going to make a system call to write that into the operating system. Here we see the write system call, which takes a file descriptor, the low-level communication mechanism to specify which file between a program and the kernel. In this case, we're going to assume it's 3. We wouldn't really know unless we looked in more detail to figure it out, and we don't really care at this point. The write system call also takes a pointer to the data to write, as well as how many bytes to write. In this case, it's 12 because there are 3 lines, each with 4 bytes. Each of these has 3 numerical digits plus the new line character, so this data is going to be written into the operating system's memory. You'll notice I've written it over here as the actual numerical values of the bytes rather than the textual representation of the digits, just as a reminder that everything is a number, and because this is really just dealing with raw data. We're not really thinking of it as text anymore. It's just a bunch of bytes going to a disk. Next, the C library is going to make the close system call, passing in the file descriptor because that's how it communicates with the operating system. Then the operating system is going to decide that it should write its buffered data to the disk, so it's going to write all of these bytes onto the disk somewhere. Then the disk is going to tell the operating system that it actually succeeded. It's possible that this fails. Maybe some piece of the disk has gone bad, in which case it wouldn't be able to write the data, but let's assume that it succeeds. So the kernel is going to recognize that this file is closed and also tell the program that it succeeded in closing the file by returning 0, which is going to be the return value of fclose. At this point, the file is closed, so we can't do anything else with it, and our call to fclose will finish and we'll continue executing code.
Now let's see the semantics of malloc. Here we have a small example of code which uses malloc. It does not really accomplish anything, but will let you see what malloc does. Our first statement just declares an int star p, which is uninitialized. The next statement is an assignment statement, so you will follow the same rules you always do. Find the box named by the left-hand side, in this case p, and evaluate the right-hand side expression to get a new value to put into that box. In this case, that expression is a call to malloc, which will allocate memory. Allocating memory means that you are going to draw a new box. This new box will be in the heap, not in any stack frame. Unlike variables which reside in stack frames, this box that you will create in the heap does not have its own name. To see what the new box looks like, you need to look at the argument passed to malloc. Here, it is 6 times the size of star p, which means it will be an array of 6 elements. As p is an int pointer, those elements will be ints. So let's draw that box. Note that each element inside the array is uninitialized. Whenever you create new boxes, they are uninitialized until you explicitly place a value in them. The return value of malloc is a pointer to this newly allocated memory. So now you are ready to finish the assignment statement. Placing the return value of malloc, which is the value of the function call, into p's box. Now let's look at what happens later when the function returns. The frame for the current function is in the stack, so it will be destroyed automatically when the function returns. This behavior is exactly what you are used to from prior lessons. However, the memory that was allocated by malloc is in the heap. This memory will not automatically be freed when the function returns. So when you execute the return statement, you will destroy the frame, but not change anything in the heap. Anything allocated in the heap will continue to exist until you explicitly free it, which allows you to allocate memory inside a function and return a valid pointer to use it in other functions. Now that you can allocate memory with malloc, you also need to deallocate that memory when you are done with it, using free. we are going to start this example code to show you the semantics of free. We have declared P and initialized it to point at an array of 4 ints allocated by malloc. We then filled in the array with some data, and to illustrate another point at the end, we made another pointer Q and set it equal to P. We have a comment with ... to suggest that we have skipped showing whatever code would do some useful calculation with this data. We now show the state right here before a call to free. Let's now see what happens when we execute free. First, notice that we have passed the pointer P to free. Free P does not actually affect P, but rather the memory that P points to. Let's look at where P points. It is this block of memory, the array of 4 ints which malloc gave us earlier. Freeing this memory destroys that box and leaves P dangling. Any further use of the memory pointed to by P is invalid, as with any dangling pointer. Notice that since Q points at the same place as P, Q is also now dangling. We should not attempt to dereference Q either. All right, now let us try a slightly more complex example. Again, we're going to start at the point in the code where we are going to free things. What is the state of the program at this point? You should work that out yourself before we proceed. Hopefully, you came up with a program state that looks like this. We are just using multiple colors of arrows to help you keep straight what points where. The arrow color does not have any special meaning. First, we step inside our for loop, creating I and initializing it to 0. We are going to free P at I. I is currently 0, so the pointer P at 0 is this arrow here. We will release the block of memory that it points at here. Now we have finished the call to free. Notice that the pointer is now dangling. That is fine as long as we don't dereference it. We go to the next loop iteration and free the memory pointed to by P at 1. We execute free and go to the next loop iteration. We step inside the for loop and free P at 2. We go back to the start of the for loop again and free P at 3. Now I is 4, so we exit the for loop. Finally, we free P, which also points at memory that was allocated by malloc. Freeing P releases that memory, and now we have freed everything we allocated with malloc.
In this video, we're going to step through the following code, which repeatedly mallocs an array inside of a for loop. In the first version, we're not going to free that array, causing a memory leak. But in the second version, we are going to use free. Let's see how both versions play out. We begin inside of main and initialize a variable x, and step into a for loop where I initially has the value 10. The first line in the for loop is going to malloc space on the heap for 10 integers, and P will point to that location on the heap. Let's assume we have a function do some computation that will initialize that array and perform some kind of computation such that the value of x will change. Keep in mind that at the end of this iteration of the for loop, the variable P will no longer exist. So when we return to the beginning of the for loop, P goes away. What this also means is that we've lost our pointer to the memory that we allocated on the heap. This memory is now leaked. There's no way to access it. There's no way to free it. We've incremented I to 11, and we're going to execute another iteration of the for loop. This time we're going to malloc space for 11 integers. Now notice what's going to happen in every single iteration of the loop. We're going to allocate memory and then leak it a larger and larger amount each time. This is not what we want. Let's consider instead a version of this code where we have included a statement to free the memory that we allocate on the heap. Once again, we begin in main, we initialize a variable x to 0, and enter the for loop where I initially has the value 10. We malloc space for 10 integers, then perform this computation, which initializes the array and changes the value of x. Finally, before we leave this iteration of our for loop, we're going to free the memory pointed to by P. Now, when the variable P disappears, we haven't leaked any memory. I has been incremented to 11. We go back into the for loop. We're going to malloc space for 11 integers. Once again, we call this computation function, which initializes the array and changes x. And once again, we free the memory, pointed to by p. Now, we could do another iteration of the for loop. Notice that every time we allocate memory, we free it, so we're not amassing more and more leaked memory in the heap, as we did in the first example.
There are lots of ways to incorrectly use the function free. This video is going to walk you through 3 of them. The first one is where you call free twice for the same location on the heap. For the first line of code in this example, we're going to malloc space for 4 integers, and p points to that location on the heap. Suppose we have another pointer q, and we want q to also point to that same location on the heap. At some point later on, we're going to free the memory pointed to by q. If at some point later on in our code, we also try to free the memory pointed to by p, we have a problem. P is pointing to the same place that Q is pointing to, and that memory has already been freed. Trying to free it again is illegal and will result in undefined behavior. The second thing you could do wrong is try to free memory that's not actually in the heap. Here's an example. Assume this code here is inside of some function. We have a local variable x, and we initialize our pointer p to point at x. Now, what if later on in our code, we try to free the memory pointed to by p? This location is not on the heap. It's on the stack. This is illegal and will result in early termination of your program. Another thing you could try to do is free the middle of the block. Here's an example of that. We're allocating an array of size 4, and p points to that location on the heap. At some point, we increment p so that instead of pointing to the 0th element of the array, it points to the first element of the array. Now, later on, if we try to free p, we'll be trying to free something not using an address returned to us by malloc. Instead, we're trying to free something using an address in the middle of our allocated block. This is also illegal and will result in early termination of your program.
Now let's take a look at the semantics of realloc. You can think of realloc as mallocing new space, copying the old data to the new space and freeing the old space. Let's see that in action. We start by declaring a pointer and mallocing space for 10 ints for it to point at. Next, we're going to fill these ints with some data. In the interest of space, we have abstracted that out into a function called initValues, which is not shown here. For this example, we don't really care what the values are, but we want you to see that they do get copied. So let's initialize this data with some values. Now that we have numbers in the array, let us suppose that we discover we need to make the array larger. Such a thing might happen if you were reading data and did not know how much data you needed to hold. In this example, we decide that we need to hold 14 ints instead of just 10, so we call realloc. We pass in p, which points at the memory we want to reallocate, and the amount of space we want. In this case, space for 14 ints. Now let's see what realloc would do. First, it mallocs space for the newly requested size, 14 ints. So let's do that. Next, realloc copies the data from the old memory into the newly allocated space. Notice that it only copied 10 elements, since that is how many were in the old array. The remaining 4 are uninitialized. Last, realloc is going to free the original space, which is no longer needed. Once that is done, realloc will return a pointer to the newly allocated memory. Finishing the assignment statement will update p to point at this newly allocated memory, since the function call expression evaluates to realloc's return value. Now let us suppose we were to do some more initialization to fill in these other 4 values. Again, this code is not pictured in the interest of space. You can also use realloc to reduce the amount of memory allocated to something. You might want to do this if you no longer need some of the data and want to reduce the memory you are using. This will follow the same rules. Let's see it in action. First, you malloc space for 4 ints. Then you copy the first 4 ints into the new space. Finally, you free the memory that was allocated for the old space. As before, realloc returns a pointer to the start of the newly allocated memory. So after realloc returns, the assignment statement updates P to point at this newly allocated memory. You should always assume that realloc will move the data to a new location, both when you write code and when you execute code by hand. However, you should be aware that realloc may leave the data in the same place. Let's see the same example if realloc keeps the data in the same memory location. We start out in the same way with a call to malloc and then initializing our data. Next, we call realloc to increase the size to 14. However, this time, realloc is going to allocate space immediately after the current data, avoiding the need to copy and free the old data. As before, realloc returns a pointer to the new data. This time, it just happens to be in the same place as before. Our assignment statement will then update P to point at exactly the same place as before. That is perfectly fine. Next, we initialize these 4 new values and then call realloc again to reduce the size to 4. Realloc can choose to just free the unneeded elements at the end, reducing the size of this allocation to the newly requested size. It will then return a pointer to this smaller array, and as before, P will be updated to point at the same place. Note that whether or not realloc keeps the data in the same place or moves it around depends on the particular implementation of realloc, as well as which memory addresses are allocated and which are free when realloc is called. You cannot guess if it will leave the data in place, so you must always write code that expects realloc to move the data. If it leaves it in place, that code will work fine.
In this video, we're going to walk through an example of using a very convenient function called getLine. We begin in main, and there are several local variables we need to initialize to use getLine. We have a size variable, a length variable, and a line variable. We're going to be reading lines from a file one by one, and line will always point to a buffer containing each line currently being read from a file. The size variable will tell us how large the buffer is, and the length variable will tell us how long the actual string is that we've stored in the line buffer. We also need to open the file itself in read mode. We can see that the file contains 3 names that we're going to read from it. Now we're going to start reading these lines, one by one, using the getLine function. Usually for a library call, we abstract away the details, but in this case, we want you to learn what getLine does, so we're going to create a stack frame for it, where you can see its 3 parameters. The first one is a pointer to the line buffer, so we've passed in the address of line. We haven't actually allocated memory for this buffer, so line P is pointing to a pointer that has the value null, and that's fine, getLine can handle that. The second parameter is a pointer to the size. So we've passed in the address of size. This tells us how large the buffer is, and since we haven't allocated the buffer, it's 0. The reason getLine takes a pointer to the size variable, not the size variable itself, is so getLine can change the size once it allocates a buffer of appropriate size. The third parameter is a pointer to the file to be read, so we've passed in f. Now we're going to call getLine, making note of the call site location and moving our execution arrow into getLine. We're not going to show you the actual code for getLine. Rather, we're going to use an appropriate amount of abstraction and list the 4 primary tasks that you should know about. The first thing getLine does is allocate memory if necessary. In this case, the buffer we passed in is null, so getLine will allocate space on the heap, where it can write the first line it's going to read from this file. In this case, it allocated 8 bytes. It's getLine's prerogative to decide how much memory it's going to allocate, but we will find out exactly how much was allocated because the next thing getLine does is update the size variable. After creating a buffer and updating the size, it then reads the line of the file and stores it into the string. As you can see, we've read in a word as well as the \n or new line character which indicated the end of the line, as well as a \0 which indicates the end of the string inside of the buffer. The final thing getLine does is return the length of that string, which is 4, back to the calling function. Keep in mind the new line character, but not the null terminator, is counted in the length. Next, in this assignment statement, length will be updated from 0 to 4, and we go inside the while loop, where we print out the line. Notice that we didn't have to include a new line character in the print statement since it was included in the string itself. Now we're ready to read the next line. Once again, we create a stack frame for a getLine, passing in a pointer to the buffer, a pointer to the size, and a pointer to the file that we're reading. We note the call site location and step into the function. When it's time to allocate memory, line actually points to something, a buffer of size 8, so we don't actually need to allocate more memory. We also don't need to update size. Now we read a line from the file into the string. Notice that we overwrote the original buffer because we gave getLine the same buffer that we had been using before. If we had wanted to maintain the first string, we would have had to store it somewhere else. Now we can return the length of the new string into the calling function, where we complete the assignment statement, updating length to 6, and enter the while loop, where we print the new name. Now we are ready to read the next name from the file. We place another call to getLine. It doesn't need to allocate memory or update size, so it reads into the string, but the buffer has insufficient size to read the whole line. It is important to realize that getLine might need to reallocate memory, in which case it allocates a longer buffer, copies the existing data, frees the old buffer, and updates line to point at the new buffer, and updates size. Now it can continue reading into the string. This time there is sufficient space. So we return the length 10 and go back to the call site. We complete the assignment statement, enter the while loop, and print the name, returning to the top of the while loop. We place one more call to getLine. We don't need to allocate memory or update size. However, this time, when we read into the string, it reaches EOF and returns -1. So we leave the function without executing the other steps, complete the assignment statement, and skip the while loop since length is not greater than or equal to 0. Since we are done with the memory allocated on the heap, we need to remember to free it. Finally, we can exit our program. Note that in a real program, you would also want to close the file.
In this video, we're going to put together some of the concepts we've seen in this course, as well as previous courses in the specialization, into a slightly larger example. We're going to use getLine and realloc to read lines from a file, increasing the size of the array that holds the lines each time we read one, so that we can store them all in memory at once. Once we have them all read in, we're going to sort them, and then we're going to print out the sorted result. This sort function is not something from the C library. We've written it ourselves. It uses qsort, which you saw in the previous course. We're not going to show the details, but it will rearrange pointers in an array such that the strings they point to are sorted with string compare. Now we're going to step through the code. We declare the variable lines and initialize it to null. We declare the variable current and initialize it to null. We declare the variable size without initializing it. We could if we wanted to, but this will illustrate that getLine will give it an appropriate value. And we initialize I to 0. And then we call getLine. We set up a frame and enter the C library. getLine determines that current is null, so it allocates memory and sets current to be a pointer to that memory. Then it changes size to be the number of bytes allocated. Next, it reads from the stream passed n, which in this case is standard n, so it reads the string cat followed by a new line and a null terminator, and returns to main. The call succeeded, so we enter the while loop. We're going to call realloc on lines, which is null, passing in 0 plus 1, which is 1, times the size of star lines, so we need space for 1 char star. Reallocating null is just like mallocing, so we're going to get 1 box, which is uninitialized. Lines at I equals current, so we're going to give the 0th box of lines a pointer to the string cat. Then we set current equal to null because when we call getLine again, we don't want it to change this string, we want it to allocate memory for a new string. We increment I and return to the start of the while loop. Now, rather than stepping into getLine again, we're just going to show its effects this time. That is, it's going to allocate memory for a string, change size to be the number of bytes allocated, read in the string ant from standard in. This time we showed it allocating a different amount of space, only 5 bytes, which is exactly what it needs. We don't actually know how much space it will allocate. We just know that any space left over will be uninitialized. In fact, how much space it allocates will be platform dependent. We enter the while loop and reallocate lines to be 2 char stars now. So we create a new 2-element array, copy in the value of the previous array, leaving the second box uninitialized, and get an arrow to the newly allocated memory. Lines at 1 is going to get the value of current, which is a pointer to the string ant. We set current to null, so we will get a new allocation next time we call getLine, increment I, and go around again. We call getLine again to read the last line in the stream. We reallocate our array and update lines at 2 to be current. We set current to null, increment I, and go around the loop again. Now when we call getLine, it is at the end of file, so we skip the while loop. Notice that it still allocated some memory which is uninitialized, so we need to free that memory. We're going to call sort on the lines, however we're not going to step through it. We're just going to know that it reorders the pointers so that ant comes before bread, which comes before cat. Now we're going to enter the loop that prints each string. So we print lines at 0, which is ant, and then we free that memory. Then we print lines at 1, which is bread, and free that memory. We print lines at 2, which is cat, and free that memory. Now we're done with this for loop. Next we're going to free lines, the memory pointed to by the blue arrow, so that's going to go away. Notice that we've cleaned up our heap nicely and freed all of that memory. Now we're going to return, destroying mains frame.
Now we are ready to wrap up this specialization with a discussion of important principles as you move to larger programs. If your learning goals for this specialization are just to write moderately sized programs to analyze data, these principles will be both sufficient and critical for your needs. If you plan to go on to be a professional software developer, these principles will be essential, but you will need to go further. This will be a great launching point to go on and take other courses in software engineering, learning more design principles in greater detail.
In this video, we're going to plan the code for the moderately sized roster program. As always, we'll start with step 1, working an example by hand. For this example, my input is in the form of this file with 3 students, Romeo, Juliet, and Tybalt. I'm going to go through and read this and see that Romeo has 2 classes, Dual 300 and Romance 101. Juliet has 2 classes, Romance 101 and Poison 352, and Tybalt has 1 class, Dual 300. Next, I'm going to realize that it would be good to have a list of the unique classes. That is, Dual 300, Romance 101, which appears twice, but I only need to add it once, Poison 352, and Dual 300 appears again, but I don't need to add it. Then I'm going to go through and make the roster for each of these. Dual 300 has Romeo and Tybalt in it, Romance 101 has Romeo and Juliet, and Poison 352 only has Juliet in it. Next is step 2, to write down exactly what I just did. The first thing I did was I read the input, figuring out what it meant in some of the conceptual units we're going to use in this problem. I made a list of all of the unique class names that appeared in my input. Then I wrote 1 output file per class. Now those steps may sound very high level, but remember we want to work from the high level steps down to low level steps in top-down design. This allows us to break the larger problem into smaller and smaller problems. Now I need to generalize these steps, although they're already pretty general. In general, I'm going to read the input from the file named by argv1, and I'm going to call the result the roster. Next, I'm going to make a unique list of all the classes and give it a name of convenience, calling it unique class list. Then I'm going to write one output file per class from unique class list and the roster. Since these steps were already pretty general, we didn't need to do the nitty-gritty low-level algorithms, but that's fine. Next, you would test these steps on a different input, but we'll leave that as an exercise for you, if you would like. Translating this to code, each of these is a complex step, so we want to abstract it into a function. These few function calls, plus some error checking, make up a good main. We don't want to delve into the details of solving each of these problems. We'd like to have each one be a function, such as reading the input. Now to do this, we need to be a bit more precise with our drawing to see what types are needed. That is, if I make a function called readInput, which takes argv@1 and returns the input, what's its return type? What type should the roster be? Conceptually, readInput returns a roster. We can name this type roster_t, where _t is a convention for type names, but what would the definition of a roster t look like? This is going to be important for working through the details of these functions that we're going to write next. The conceptual representation of a roster t is this. That is, the thing we drew in step 1. Working this example ourselves. We have multiple things. What kind of thing? We'll talk about that in a second. And that suggests an array. In this example, we have 3. In general, we might have 40 or 2 or 3,000. Therefore, we need to track how many things there are, since C does not keep track of the size of an array. We might think of a roster T as looking like this. That is, students points at an array, each element of which points at one of these things, which we'll talk about in a second. And then we have a number of students, which in this case is 3. Now we need to think about what each of these things in the array is. Each represents a student, so it makes sense to call it a student T. That will let us define this struct for the roster T. It has a student T star star, that is, this pointer points at a pointer to a student T, and an int for the number of students. We can typedef this struct roster T. Now, what about the details of a student T? It has a name, such as Romeo, which would be a string, a char star. It also has classes, which is going to be an array of strings with types char star star and an int to tell us how many there are. Romeo has 2 classes, Tybalt has 1. This is a fairly small example. We could imagine any number of classes here. The result is something like this, where I've omitted the other students in the interest of space. The variable students points at this array, each element of which points at a student T, which has a name, which is a string, classes, which is an array of strings, and a number of classes. So we would define a student T as a char star name, a char star star classes, and an int num classes. Now that we have planned out our program at a high level and decided on some custom types we'll need, we are ready to plan the rest of the subproblems we've identified and begin writing our program. As we wrap up this course in specialization, it's time for you to finish your poker project. You've written a lot of code in courses 2 and 3, and now it's time to handle reading input and unknown cards and bring it together by writing the main function, which will do the Monte Carlo simulation. One of these parts may seem a bit tricky. How do you handle unknown cards? It turns out that we can do this with concepts you have learned, pointers, arrays, and realloc. Here is a small input with 2 hands. The first has the King of Hearts and 2 unknown cards. The second has the Ace of Spades and 2 unknown cards. Both hands share $0, so we have to make sure our implementation can ensure that both hands end up with the same value. Of course, real hands need at least 5 cards, but we're just going to draw a smaller example here to show you how this works. We'll make a structure to track unknown cards. Since we already have decks as a representation for sets of pointers to cards, we'll reuse that type here. Our unknown card structure will have an array of decks. Each deck will correspond to one particular variable. So $0 will correspond to one deck, $1 to another, and so on. Unlike normal decks, each of these decks will point at placeholders in the hands to show where to fill in later. Let's see this in action. Our first card is the King of Hearts. We will allocate space for hand 1 and for this card. Our second card is $0. We don't know its values yet, so we could set them to invalid values. That way, if we ever mess up and don't change them, it will be easier to catch the mistake. Since this card is unknown, we're going to update our unknown card structure. We'll allocate a deck to correspond to $0 and make a one-element array whose value is a pointer to the card we just created. The next card is also unknown, so we will proceed similarly. We'll make a deck for $1 and make its one element point at this placeholder card. Now we start on hand 2. The first card is the ace of spades. The second is $0, so it is unknown. So we will want to add an element to the deck for $0, which points at this newly created placeholder card. The last card is also unknown, so we make a placeholder. Since it is $2, we will need to make a new deck and point its one element at this placeholder card. Now we need to be able to use this structure to assign random values to our placeholder cards. First, we need to know how many random cards to draw. In this case, we need 3, but how would we know that in general? So let us suppose we shuffle our deck and look at the top 3 cards and find they are the 4 of clubs, the Queen of hearts, and the 7 of clubs. How do we set the cards in the hands to these values? Well, everything that needs to be set to the 4 of clubs can be found from the pointers in the deck for $0. So we can iterate through that array and use these pointers that we find there to refer to the cards whose values we want to set to the 4 of clubs. Once we set these to the 4 of clubs, we want to repeat the process for the other unknown cards. For $1, we would use the pointers in its deck to find the cards to change to the Queen of hearts, and then the same thing for $2 and the 7 of clubs. If we wanted to repeat the process for another set of random cards, we could. We just shuffle the deck and iterate through the unknown card structure again. With that, I think you are ready to dive in and finish your project.